Hello everyone, I'd like to show you guys a few very interesting small programs. The first one is tic-tac-toe. It's a game, a puzzle, played by two players. Basically, whoever plays his or her marks on the same row, column, or diagonal wins the game. So let's play. Oh, by the way, this game I designed always has human players to be the first one. So I'll choose the top left corner. Now the machine is smart enough to take this center square of this 3x3 grid, because a lot of columns, well, not a lot, there are columns and the rows. For example, the second column, the second row, and two diagonals all depend on the center grid. Now, if I pick this one, yeah, machine took the first column, second row. Now I have to take this second row and third column, otherwise machine would win. So let's do that. Okay. I have to do this. Now actually the game is technically end. The best outcome of this two players game is a draw. Now let's do it again. And this time I'll be just playing dumb. I'll probably just play randomly. Take this one. I'll do this one. Now I know the machine would win if I don't take the lower right bottom corner. But let's do that. Oh, machine didn't really take it. But if you think about it, the machine is just kind of playing me, because there's two squares on the board. The machine can take either one, it would win. So if I take this, yeah, machine took the right one, right bottom corner, so it still wins. Now what's interesting about this game is there is a game tray built by the computer at each machine's turn. The game tray would explore all the moves, the best moves in fact, of the human player, and then the machine's best move against the human player. So this is a simple game because it has only 9 empty squares to begin with. So there are very limited possible combinations for the machine or the computer to explore. But the machine is very capable in exploring many moves, much more than a human player can possibly do. The next program is a customer simulation. Every time I go to a grocery store or supermarket, I'm always puzzled by how many lines they choose to open or close. So that motivated me to write this simple simulation program. Now here you see there are 8 check boxes. 1, 2, 3, 4, 5, 6, 7. Each of them represents a checkout counter. If I check it, it turns green. That means this line is open. So if I check 3, now we have line 2 and line 3 open. The rest of those lines are all closed. The first slider gives you the control of simulating the number of customers arriving per unit of simulation time. So if I have the value selected at 5, that means there can be 1 or 2 or 3 or 4 or 5 customers arriving at any of your counters per unit of simulation time. Now the second slider indicates the maximum customer service time. So if I have the value selected 3, that means for each customer, it may take 1 or 2 or 3 units of time for it to complete the checkout. Now let's start the simulation. Click Start. All right. Now you'll see there are customers arriving at counter 2 and 3. So because we have customers coming faster than the counters or than the counter's availability or service, so we can open a new one, another one. Let's see if we can shorten the line. Well, not. So if we open even more, and for each customer, the service time is less, see what happens. Now they'll have to open another one. Oh, let's open another one. Because customers are arriving much more, it's queued up. So you want to open more lines. Now you say the lines are shorter now. So this is a very interesting simulation. Now I can turn this off, close these lines. So by this, you probably can optimize how many cashiers you can employ. All right, let's pause. Those 2 examples I showed you may not be very easy for beginners to learn everything of it. However, there's something you should pay attention to, such as how the UI, a simple UI, are laid out. What's the data structure being used, and how to approach a problem, a model, a real-world problem. Now, the next example, what you're looking at, is written in Python. It's a very simple program. What you see right now is just a square, a blinking square, moving at a constant speed in a straight line from the left upper corner to the right bottom. It just repeats the motion itself, moving down, blinking, and then disappears for a little bit and then reappears from the top. So this program you should be able to write after a few weeks Python study. I know this animation may not be that interesting, but what if I change something? Now this is the Python program for that moving objects. So let's change a little bit, see what happens. Comment these 2 lines and enable these 3 lines. And then run it. Now I changed a little bit of the Python program. Now it's still a blinking square. But if you really pay attention to it, it no longer moves at a straight line. And the speed is not a constant. What you see here is is a square actually following a parabola curve. It's almost like when you studied kinematics, you learned what Newton did as experiment. He threw the stone at a certain altitude, and the moving object has constant x velocity, and the y has acceleration. That's why when you say the square moving faster and faster downwards in the y direction. So this program, in fact, simulates somewhat of this a physical phenomenon. It simulates physics. So after we learned Python fundamentals, we definitely can build a lot of simulations or games or puzzles like this. Hello everyone, welcome to this Introduction to Python Programming online course. I'm your instructor. My name is Haichuan Lin. I'm not a teacher. I'm a software engineer with about 20 years industrial experience in the US. Early in my career, I did some business applications for Praxair. I worked for Cornell University, did some weather and agriculture research for a year. I worked for Siemens on medical devices. Currently, I work on the medical lab automation system for Becton Dickinson, which is another big medical technology company. Now, what is Python? Python has nothing to do with this reptile. It's a programming language. If you're interested, you can Google the name, the origin of the name. But to me, it just sounds better. Python is a high-level general-purpose programming language. We say it's general purpose is because Python is not designed just for solving a particular set of problems. You can use Python to solve a whole range of problems. It's object-oriented. This feature is much like many other languages such as C++, Java, and C#. We will learn the concept of object-oriented. It's a very high-level programming language, meaning the program you write in Python is very close to the natural language, the language we speak every day. It's interpreted basically means the Python program doesn't need to be compiled before we run it. Don't worry about all these terminologies here. We will learn gradually. Now, why Python? Well, we choose Python for high school students because it's simple. Compared to other languages, it's relatively easy to learn. It's also free. It has many library supports. It's versatile, like I said. Python is a general programming language. It can do many things, from scientific computing to program on robots. What you need? Obviously, you need to have a personal computer. It's better be Windows 10 operating system. You need to download Python 3.7. You can download from python.org. But keep in mind, the language itself evolves. So the time you go to the python.org, the latest version may not be 3.7. Maybe it's 3.8 already. So you just need to download the latest version. You also need a IDE. IDE is the integrated development environment. Basically, IDE is another software that helps you develop Python program. For our course, we pick PyCharm as our IDE. You can go to JetBrains.com to download PyCharm. You also need some high school mathematics, because in this course, I'll try to combine the programming tasks with some concepts you learned from your mathematics teachers or physics. We probably can do some simulations, from what you learned in kinematics, for example. You also need paper and pencils. This is because whenever we try to solve a problem by writing computer program, first, we may have to think about the problem and think about the solutions on the paper before we actually jump into the computer, write our first line of code. Here are a few web resources or links you may find useful. Python.org. This is pretty much for developers. And also, there's one called learnpython.org. There are several tutorials available from that link. You can find by yourself. The third link, stackoverflow.com, is an interesting one because a lot of professional engineers, developers constantly go to this website looking for answers. The fourth one, W3 Schools, actually may be more suitable for beginners. There will be a 3.7 documentation installed along with Python 3.7 installation. So this is a very comprehensive manual. This can also be our offline reference because it's installed on your hard drive. Now, this is my tentative course outline. First, we're going to cover the fundamentals about this language, starting from how to use PyCharm IDE, then learn a bit about how to do the simple tasks using Python interactive environment. We call it console. We can use it for some very simple arithmetics, such as addition, subtraction, multiplication, etc. Then we'll move on more computer science related concepts such as what are types, variables, then what are strings. After that, we can use that to build some functions and learn some of the concepts of the functions. Then we move on to more advanced concepts like decision making, loops. In this course, we are not only just focusing on the programming fundamentals. I would also like to introduce some first-year college data structure algorithm concepts. Although we may not have time to introduce all of that, but the algorithms are more interesting, such as finding the maximum number from a list, how to sort a sequence of numbers, and maybe doing some optimization. And these are all the key of the algorithms. We will explore some of that, although probably not our focus here. Classes is the more advanced concept. We will have to cover some of that in order to build more interesting software. So these are the fundamentals I have in mind. We will have to learn first before we can build some more interesting software, which I think will be packaged in projects format. The project will be much more complicated. You will have to spend more time by yourself. I mean, for the fundamental exercises, each probably will take just half an hour at most. But for a project, for example, if I give you a puzzle to solve, Sudoku puzzle, you may have to spend many hours to figure out every details. Although I will give you the algorithm, the pseudocode for you to start with, but still you need to spend a lot of time there. Don't worry, once you have all the fundamentals learned, doing projects will reinforce what you have learned in the fundamentals, and they will be much more interesting and fun. Okay, here are the instructions for install Python. The installation is not difficult. Here is the instruction for installing Python. The installation is actually pretty straightforward, but this is the first step. If you do not install that properly, it may cause trouble of using it later on. So I will give as detailed instruction as possible here. So you go to python.org/downloads, and you find the latest Python release. Like I said, the Python releases every few months. So I have 3.7.4. So when you go there, you may find another release which is newer than this. So don't be afraid, just download the latest version. So once you download the latest installation file, it's typically named Python the version number and .exe. You run it. This is the first window pops up. Make sure you check at Python 3.7.2 path, and also you want to select Customize Installation. In the next pop-up window, you select all optional features. In the advanced options, be sure select Install for all users. Once you select Install for all users, the customized install location will change to say /program file /python 37. This will make sure everyone will have access to this on your computer, regardless whether your computer is just used by yourself. Then you proceed. It may take some time to finish the whole installation. So this progress bar will show how much has been installed. Just be patient, wait until it completes. Once it completes the installation, you need to make sure disable path length limit. And then you just click close. Now you actually have already installed that Python. One place to make sure it installed correctly is go to the Windows 10 Start menu. You will find a list of Python-related stuff recently added. Make sure you have this. After we install Python, the next step for us is to install PyCharm Integrated IDE, Integrated Development Environment. Again, go to this JetBrains.com PyCharm download web page. And make sure you select Community Edition to download because that's free. The next page, choose install location. Here we can just accept the default location. In the next installation options page, select all the options. Accept this, choose Start Menu folder as is, and then click Start. The installing may take some time, just wait for it to complete. Once it completes, reboot. So after JetBrains PyCharm installed, you can go to Windows Start menu, find there should be an entry called JetBrains PyCharm Community Edition. So if you say this is there, you install that properly. And next, you want to make an icon on the taskbar. Basically, you go to this Start menu, JetBrains PyCharm Community Edition, choose More, and then click Pin to Taskbar. That way, you can just launch PyCharm directly from the taskbar without going to the Start menu every time. So once you launch PyCharm program, you should see this window. This is the window you say PyCharm runs first time. If you see this pops up on your computer, I think you're good for the first lesson. And next lesson, we will talk about how to use PyCharm to write some simple Python scripts. Hi, everyone. You have installed Python 3.7 and PyCharm IDE. Next, we want to set up a project on your computer. First, you need to create a folder on your computer and name the folder something like your name _ CS _ labs. This is the place we'll be using to store the class exercises and the projects. Next, go to taskbar and launch PyCharm as administrator. Last lesson, I told you to create the button or pin the PyCharm application on the taskbar. So this is a quicker way to launch. If you have never run PyCharm before, this is the screen you will see the first time when you launch PyCharm. It basically shows the version of PyCharm. In my case, is version 2019.1.3. And it gives you option to create new project or open existing project. In our case, we want to create a new project. So click Create New Project. Now you say on the location, it shows say/lin _cs _labs. Of course, on your computer, it should say something with your name _cs _labs. Now let's change the project location to Python sandbox. Expand project interpreter and make sure you select this new environment using virtual env. By default, it is using this new environment, so you probably don't need to change anything. Just to double check, the location is say/your name _cs _labs /Python sandbox. And also make sure the base interpreter is installed in this say program files. And now click Create. After PyCharm completes setting up the project for you, you should see a screen similar to this. Now you may have a different screen with a different background color. That's because the default theme is different from mine. If you want to change that theme, you can go to File, Settings, and Appearance. Make sure you change the theme to IntelliJ. That way you will have a similar background as mine. So, okay. Now, I also have enabled this toolbar here. Open, Save, and Synchronize. If you don't see this, I think you can go to View and select Toolbar. Now go back to File, Settings. We want to add Package. Go to Project, select Project Interpreter. Noticing there's a little plus button over here. And click it. Now this is a packages manager. Now type pygame. So this is the package we want to download for later development. It is called Python game development, but we will be using it pretty much for graphics. We also want to select a specific version. Now from what are available, we want to choose a stable release version. If you say the version appended with RC, that's not a final release version. RC stands for release candidate. And if you see the version number appended with dev 1, 2, 3, I guess they are not final release version either. They are still in development. So we want to select a release version. So let's pick 1.9.6 and click Install Package. Now it's installing. This may take a little bit. And also make sure when you launch PyCharm, you launch it in administrator's mode. That way you can install. Otherwise, you probably will see some error messages popping up here. Now we have this Pygame installed successfully. We can close it. And also click OK. Now this lesson will be using Python console to do some basic arithmetics. If you go to Tools, Python console, this will open the PyCharm console. So this right 3 arrows is the command prompts. This is the place you can type Python commands or Python statements. There are other ways of opening the Python console. For example, you can go to terminal, you type py, now you see the same prompts. We don't use the terminal for our exercise. Let's stick with this Python console. If you don't see this console again, you go to Tools and click Python console to open it. Now the Python console is activated. We can use this to exercise some simple arithmetics such as addition, subtraction, multiplication, etc. Now let's move this window up. This will make it a little bigger. Now in Python, the addition operator is plus. For example, 3 plus 4 is 7. 9 plus 6, 15. Of course, you can, if you are interested, you can really make 9999 plus a very big number. Yep, Python is very good at doing a big number arithmetic. What about subtraction? Subtraction symbol is this minus sign. For example, 5 minus 3, 2. 3 minus 6 is minus 3. Now the multiplication symbol is a little different than our daily multiplication symbol. In Python language, actually in a lot of other languages, the multiplication symbol or operator is this star or asterisk. For example, 3 times 2, you use this asterisk. 8. 9 times 4 times 2. Yeah, you can change this multiplication. 72. So that's correct. What about division? In Python, the division symbol or operator is slash. This is still the division symbol used by a lot of other languages such as Java, C#, C++. So let's do a division. 5 divided by 1 is 5, obviously. 5 divided by 2, it should be 2.5. Yes, correct. Now there's a very interesting operator in Python language. It's called floor division. The symbol is double slash. Basically, floor division gives you the integer part of the quotient. it drops the decimal part. For example, if we repeat the division from the above, but this time we use floor division. 5 divided by 2, but this time we want to just get the integer part of it. It shall be 2. Okay, yeah, indeed it is 2. And the floor division, in other words, it returns the maximum integer that is less than the quotient. Now we have covered addition, subtraction, multiplication, division, floor division. The last operator we want to exercise is power. The power in Python is double asterisk. So for example, 2 to the power of 2 is basically just 2 squared. It's 4. 2 to the power of 3 is 8. It's basically 2 cubed. All right, so these are the very simple mathematics, arithmetics in Python. Now, today's assignment for you is just to go home and get yourself familiar with PyCharm IDE. For example, you can exercise how to open the Python console. If you don't like the default theme or the theme I picked up, you can change it, but don't change other options or settings. Now, you want to probably get yourself familiar with the keyboard. Get yourself familiar with where the symbols are, and exercise some mathematics in this interactive Python console. Now, that's the end of this class. Thank you. See you next time. Let's continue our discussion about Python operators. Python operators have precedence, which means which computation is carried first given an expression. For example, 2 plus 3 times 2. How does Python interpret this? Does Python do the summation first, then do the multiplication, or does Python do the multiplication first, then do the addition? In other words, does Python do 2 plus 3, which is 5, then times 2, or does Python do 3 times 2, then plus 2? Because the order of the evaluation would give different results. Now, the table here shows you Python arithmetic operators priority, from high priority to low priority. The power has the highest priority, followed by unary operator, plus and minus. The plus is basically gives you the sign of a number, and the minus negate the number. Next come multiplication, division, floor division, and modulo. Addition, subtraction have the lowest priority. So for the example above, Python would do the multiply first, because multiplication has higher priority than addition. So Python will compute 3 times 2 first, which is 6, and then do the addition, plus 2. So the result is 8. Now let's work on a few examples to help us understand more about the arithmetic operators precedence. Open Python console in PyCharm. Like this. If you don't see this open, again, you can go to Tools, click Python console. Or if you see this Python console, but you don't see this command or console prompt, you can click this, rerun. That will activate Python console. Now let's practice some arithmetic operators with the precedence in mind. For example, 2 plus 2 to the power of 2. What the result would be? We know power has the highest precedence or priority, so it would do the power first. 2 to the power of 2 is 4, and then plus 2 is 6. Correct. Then what about minus 2 to the power of 2 minus 2? Now we talked about a little bit about the unary operator, the minus and the plus. So minus 3 gives you a negative number of 3, just negative 3. Okay. So minus 3 to the power of 2. What this result is, because the power has the highest priority again, so it would do the power first, which is 9, and then negate the number. The result shall be minus 9. Now let's check this division. You don't have to have space in between these operators, between this operand and the operator. I have space here just for a better readability. Again, division has higher priority than summation or addition. So this time it will do the division first. 2 is divided by 2, which is 2 plus 8, then shall be 10. Correct. The same thing with floor division. So if you remember, the floor division takes the integer part of the quotient. Now, 4 floor divided by 2 is 2. And then plus 8 is 10. Now, let's take a look at the last operator, modulo. 2 modulo 5. So basically this gives you the remainder of 2 divided by 5. So obviously it is 2. Now what about I do this? 3 plus 2 modulo 5. Again, the modulo, it has the same priority as multiplication, division, and also having higher priority than addition. So it would do the modulo first and then do the addition. The modular 2 modulo 5 is 2 plus 3, it shall be 5. Correct. I'm sure now you probably have questions about how to change these default priorities. For example, in the very first example, 2 plus 2 raised to the power of 2. What if we want to do the addition first and then do the power? Actually, parentheses are used to change the order of calculation in many other languages. No exception, Python uses the same. For example, if we want to do 2 plus 2 first, and then raise to the power of 2, we do this. We enclose 2 plus 2 in this parenthesis. So now it would do 2 plus 2 first, which is 4, and then raise to the power of 2. Now you see the difference. The same thing for the second example. If we do 2 minus 2 and then raise power of 2. Now this is an interesting case. It's 0. 2 minus 2 is 0. 0 to the power of 2 should be what? Well, should be 0. Next example, minus 3. So minus 3 raised to the power of 2. So we know all numbers raised to the power 2 will just give you the absolute value. So in this case, it should be 9. And then what about the next one? 8 plus 4, then divided by 2. Now, it's doing 8 plus 4 first, 12, divided by 2, should be 6. Correct. The same would apply to this floor division. And also the same for modulo. So this would give you the addition 3 plus 2 first, 5, then divided by 5, and then the remainder of that is 0. Now let's look at this arithmetic expression. This expression does not have any parentheses, so the priority of calculating this is by default. So it would do this multiplication first. This is 18. After that, it does all this addition. So 20, 25, 32. Now what if I have parentheses 2 times 3 plus 5, then plus 7. With this parenthesis, the order of computation changed. This is computed first. So 2 times 3, 6 plus 5, 11. That becomes this. Now with this, the normal priority applies. It would do this first, 33, and then do this addition again, 35 plus 7, 42. Now, let's make it a little bit more interesting. Let's have a double parenthesis. How does Python evaluate this? It's straightforward, in fact. Whenever Python says parenthesis, it would compute whatever in the parenthesis first. Now, because we have another one inside it, actually it would do this first. So 11 plus 7. Now we reduce the 2 parentheses to 1. Now it will do this again because it's a parenthesis. So 18, 3. Now the evaluation becomes something like this. Now whatever the results come from that. So you can practice this in Python console and get a feel about the parentheses. For today's homework, I want you to practice arithmetic operators priorities. Just run this expression in Python console. You can, of course, come up with more complicated expression with the summation, subtraction, addition, multiplication, power, etc. in one expression with and without parentheses. And first, I think you want to manually calculate the result and then type in the expression in the Python console and compare the result comes from Python. Today's lesson, we're going to talk about types in Python. There are two basic numerical types in Python, integer and float. The integer is a number without any decimal points, while float or floating number has decimal points. They both can be positive or negative. Now, what if you say a number like 10.0 is an integer or float? Technically, it is exactly the same as 10 without the decimal zero. However, in computer language, so long you have the decimal points defined, it is treated as a different number than integer. It is a float. This has to do with the underlying representation of numbers. We don't need to concern too much about how the numbers are represented. I just want you to be aware of the differences. A string is a sequence of characters surrounded by single quotes. For example, Baishan, grade 9, they're strings. Now, what about 100? 100 by itself is a number, but here, this number is enclosed in single quotes, so it is a string. Again, similar to integers and floats, a string 100 is stored differently in computer than number 100. You can also use double quotes to define a string, but here I think we want to just make a convention to use single quotes for strings. Boolean types is used whenever you have a condition. The condition can either be true or false. There's no third possibility for a condition. It has to be true or false. A list is a collection with ordered items. A list is defined by using these square brackets. For instance, we have a list 1, 2, 3. It's basically an integer number list. A list doesn't have to have the items of the same type. For example, the second list has 2 items. The first item is a character. However, the second item is a number, 100. The tuple is very similar to list. It is a collection with ordered items. You use these rounded brackets to define a tuple, or parentheses to define a tuple. The difference between a tuple and a list is changeable or mutable. So you can add items or remove items from list. However, for tuple, once it is defined, it cannot be changed. A dictionary is a collection with each item is a key value pair. For instance, our dictionary here has only one entry in it. The key is a string. In fact, it's the ISBN number. And the value for that entry is the book. So basically, you have a value, in this case, a book's name, associated with the key. You use dictionary to look up something. A set is also a collection. However, a set does not or cannot have duplicated items here. This set defines, well, all those Ivy League schools. For both dictionary and sets, the order of the items in it are not important. We will learn how to use each of the types, when to use which in our later discussions. We know there are different types in Python. Now I'd like to introduce you a few methods to convert from one type to another. For example, you can use int parenthesis. This is a method. Don't worry about too much about the syntax here. Just keep in mind, if you want to convert a number to integer, for example, convert a floating point number to integer, you can use this, int. If you want to convert a number from integer to float, use float. Now, if you want to convert a number to a string, you use string, parenthesis, or string method. We will not practice this at this point. I just want to give you the reference here for later use. Now let's do a few exercises in Python console to understand some of the implications of types. Let's do addition, 1 plus 2. No surprise, 1 plus 2 is 3. These are the addition of two integer numbers. Then what about I do this? It looks like the same, still 1 plus 2, but if you know what a string is defined, in fact, the first one is a string because you see the single quotes. Does it make sense for us to add a string to a number? Let's see. Well, we got an error. It's a type error. It says, oh, you can only concatenate string to a string. That makes sense. So if we really want to do that addition, you have to convert the string number 1 to an integer, and then plus 2. Now you get the correct result, or the result you want. Now let's look at another very interesting example. Suppose I have a very big number. I don't know how many lines there, but it's a lot. Let's do some addition. Plus 2. Well, it got to be correct because the ones is 1. 2 plus 9 is 1. So we verified this must be correct. Now what if I do this? Oops. Guess what the result would be? Now, you know, whenever we have a decimal points defined for a number, so it is stored as floating point in the computer. And it's a different representation than integer numbers stored by Python. So if you do the two floating points addition, it in fact will give you something. Guess what? Well, it's not quite as accurate as the integer addition. These examples I give you just for you to keep in mind the implications or the subtle differences of using different types in your program. Hi everyone. In previous lessons, we practiced using Python console for calculations. Basically, we use the console as calculator in a sense. We also covered the concept of types in Python. Now, today's lesson, I'd like to talk about the concept of variables, which are the building block for software or program. A variable is a name for storing or referencing certain type of data. In Python, in fact, a variable is more like a reference for certain type of data. There are quite a few grammar rules related to using variables in Python, such as when you declare a variable, you cannot associate that with a type. This is very different from other mainstream programming languages such as C++ or Java, where you typically declare a variable with a type. Now let's work on some concrete examples to help us understand how to use variables in Python and the naming conventions and rules about the variables and the caveats of using them. As usual, we start Python console in PyCharm. We see this Python console prompts with this blinking cursor, so we know the Python console is active. Now we can do something with this console. We can do this simple calculation. This is what we learned before. Now what about declaring variables in console? A variable is a name, a string name. So let's give a variable name A, and we want it store a value. How about 3? So this is the way we create a variable in Python. Let's enter. Now A's value is 3. Let's declare another variable. How about a B? And let it equals to 4. Enter. From this point on, B comes into being. It starts its life in Python. Python knows the existence of B now. So B is 4. What we can make use of these variables? We can do this, A plus B, because A is 3 and B is 4 now. So A plus B, it must be equal to, yes, 3 plus 4, 7. A variable's name does not have to be just a letter or this short. It can be any string started with a letter. For example, word, X, Y, Z. Okay, and we want to use this reference string. We know a string is just a sequence of characters. And hit enter. Now word X, Y, Z begins its existence in Python. From this point on, Python knows what word X, Y, Z references. So it's a string. It's the school name, Baishan. There are certain rules about creating variables in Python language. For example, you cannot use some special character, for example, this $sign for a variable name. Okay, if you do that, it says some invalid syntax. But you are allowed to create variable starting with a letter followed by some numbers. For example, A, 1, 2, 3, and we'll let it equal to 1, 2, 3. A, 1, 2, 3. Yeah, it is 1, 2, 3 now. The rationale of creating or naming a variable is make the variable's name as meaningful as possible. You don't want to have some variable in your program that very confusing or misleading. Of course, right now we are practicing very simple variables. We don't need to worry about that very much. Another thing is some special characters are not allowed in the variable names is for obvious reasons, because those special characters, for example, the slash or double slash, are used for division or floor division. Also, variables in Python is case sensitive. A lowercase and uppercase variable are different variables in the language. Now we know A is 3 now. What about uppercase A? If we let it equal to 2 or assign 2 to A, now uppercase A is 2. So the lowercase a is not the same as uppercase a. There are two different variables. Also, noticing when I declare the variable a, b, or word x, y, z, or uppercase a, or a, 1, 2, 3, I don't have the types associated with them. Although the type for those variables actually are known to Python at the time it is created. If you're interested, you can check a, because we assign an integer value to a, so the type of a is integer. And if we want to check the type of word xyz, because we assigned string to it, the type of it is a string. So even Python does not explicitly ask you to declare a variable with a type, but these variables do have types at the time when they are declared or assigned. Now let's move on. What happens if I assign a different number to a floating number to a? Well, it is allowed, but once a different type, a numerical type assigned to the same variable which is declared before, the type might change. So if you check type of a at this time, it is a float now. I restarted Python console. Now it's cleaner. And let's work on another example. Let's assign some value to variable 1. How about 10? var1 is a variable. The name is legit, starts with a letter. The number follows the letter, so it's a legit name. var1. So var hasn't been assigned. So that's why you see this name error. Var is not defined. That's okay, because what we defined actually is var1. So var1 is 10. Good. And let's assign another number. How about 20 to var2? Okay. var1, var2, 10, 20. That's what we expected. var1 now references number 10, and var2 references number 20. Now what about we do this? We let var1 equal to var2, or assign var2 to var1. What shall be the values for var1 and 2? They're the same now. They should be of the same value. Let's check it. Enter var1, var2. var1 now should be 20 as well, because we assigned var2, which is 20, to var1. Okay, 20, 20. So they are the same. That's what it appeared to be. Now what if we change var2 to 0? Nothing wrong with that. We just want to make var2 0. Let's check var2, 0. Very good. Now, what about the var1 at this point? They were equal, but we changed var2 to 0. Will var1 changes as well? Let's check var1. Wow, it's still 20. But why? So the change of value of var2 did not change the value of var1, which was the same as var2. So there's something going on here. I'll have to draw on a whiteboard to explain this to you. This is one of the caveats you encounter in Python programming and sometimes in other programming languages. When we assign 10 to var1 and 20 to var2, what actually happens is var1 points to a value 10 somewhere in the computer memory, and var2 points to a value 20 somewhere in the memory. When we make these two variables equal, or we let var1 equal to var2 or assign var2 to var1, what happens is var1 points to number 20, which var2 points to, and this is disconnected. And when we assign 0 to var2, this is the trick. Somewhere in the memory there's 0 created, and var2 points to the new 0. So var1 still references number 20. All right, let's go back to our Python console. This is where we left. The story doesn't just end here. It's more complicated. Let's say we change var1 to a list, 1, 2, 3. Remember, a list is a collection with ordered items in it, defined by using these square brackets. So var1 equals to list 1, 2, 3, enter. var2 the same, assign the same list 1, 2, 3 to var2. Enter. var1 var2. Also, by reassigning list to var1 and var2, the underlying types of them have changed. Let's do one thing. A var2 pop 0. Pop basically removes the first item from a list. So we removed the first item from var2. The first item in var2 is 1. We removed it, so it shall be 2 and 3. What about var1? Is it the same list as before, 1, 2, 3, or it is 2 and 3? Well, hit enter. So it is still the same as before, 1, 2, 3. Removing an item from var2 does not change var1 at all. This is actually not that hard to understand. Even though those two lists appear to be the same, but in memory they created at different places. In other words, var1 has its own copy of a list 1, 2, 3, and var2 has its own copy of the list 1, 2, 3. So changing the list of var2's copy does not change var1's copy. Now this gets more interesting. We do similar things as before. We let var2 equal to var1. var1, var2. What this should be, because var1 is 1, 2, 3, and we let var2 equal to var1. So var2's value must be the same as var1, which is 1, 2, 3. So both of them are 1, 2, 3. Now let's do this. Still var2 pop 0. That removes the first item in var2. And let's check var2's content. The first item in var2 was 1. We removed it. So what's left must be 2 and 3. Correct. So we modified the value of var2. Now what about var1? In the previous example, when both var1 and var2 point to numbers, changing one does not change the other, even though they point to the reference to the same value. But now, the types are different. var1 and var2 reference a list. So we changed var2, we removed one item from it. It's 2, 3 now. What should be var1? Does removing the item from var2 change var1? Let's check. Well, you see the behavior is different when we change the list of var2. var1 also changed. That actually implies var1 and var2 referenced the same underlying data. Now let me draw on the whiteboard to explain this. When we reassign var1 to a list, 1, 2, 3, it got its own copy of that list, 1, 2, 3. var2, when we reassign var2 to list 1, 2, 3, actually it got a different copy of list 1, 2, 3. It's two lists just with the same contents. When we call var2 pop 0, which removes the first item, it only changes var2's copy of the list. So it has only 2 and 3 left. When we let var2 equal to var1, essentially we let var2 points to var1's copy of the list. So this is disconnected. So far the story is the same as the previous one. Next, when we call var2 pop 0, because var2 references this, we pop 0, meaning remove the first item out of this. So essentially, we modified the list pointed by var1 as well. This is why after we use var2 to remove the list first item, var1's list also changed because this is the same list pointed by two variables. This is a different behavior for a list from integer type. Hello, today's lesson I'd like to talk about strings in Python. A string represents a sequence of characters or symbols. Some of the characters can be human readable, some may not. So in other words, a string can represent both human readable or non-readable characters. In our lesson today, we will be focusing mostly on human readable characters. Now let's use Python console and PyCharm to learn how to define and use a string. You should be very familiar with Python console by now. A string in Python is defined by using single quotes, a pair of single quotes. This, in fact, is a string. If you're interested, you can check the type of this. It is a string. And what about length? 0. This string has nothing in it. Now, since we have learned variables, let's use a variable to store a string. This will be an empty string, but let's put something in it. For example, tell me something, and enter, check as 0, tell me something. Tell me something is a string, and referenced by variable s0. At the beginning of this lesson, remember I said a string can store both human-readable and non-readable characters. Let's use an example to understand what I meant by that. Let's click this button to clear the console. All right, cleared. Still use this variable s0 that equal to some string, some \n words. Enter s0. Now you see this, there's a \n in s0. \n is a special character. If you print s0, the \n is not printed out. It does not make sense to print \n out. It's a special character. You see this line has \n is really what s0 stores. But again, when it is printed out, when you print it, when you print s0, this special character \n does not print out. \n in computer or in programming means line feed. Now, what if you do want to print this special character? You can use a special character R, and then so this time you call print s0, 0. Now you see this \n is part of the output. There are many special characters in programming. \n, for example, is a new line. It makes a new line. If it's \t, it is a horizontal tab. We will not spend much time to cover that. So let's move on. Again, let's click this rerun to clear the console. Now it's cleared. Let's define another two string. String 1, very nice. String 2, and good. Enter. If you want to check the length of this string, you can do this. len string 1, 9. Why is it 9? So if you start from the first character, V, E, R, Y, there's a space in it, and then N, I, C, E. There are 9 characters in string 1. So length of string 1 is 9. What about length of string 2? Before we hit enter, let's check. A, N, D, 3, there's a space, so that's a 4th character, and good. Good is 4-character word. So there are total 8 characters. Enter, yes, it is 8. If we want to perform string concatenation, basically means you put 2 strings together, you do this. String 1 plus string 2. That's print. Print just output the results to the console. Enter. Okay. Now the result string is really very nice, plus, and good. Notice there's no space between nice, the last character of the first string, and the first character of the second string. Now, if we want to make it make the output a little better, print, yeah, string 1 plus, this is an empty character, then plus another string. Let's see. All right, now it is very nice and good. So indeed, you can use this plus operator for 2 strings. That's the concatenation. Now there's another interesting operator that can be used on string in Python. So for example, string 1 times 3. So multiply string 1 by 3. So this, in fact, will just repeat string 1 3 times. Very nice, very nice, very nice. 3 times. Another very common usage of a string is accessing the string or the individual character by indexing it. Restart the console. School variable. Let's define a variable school and assign a string to it. Remember, the string is defined by using single quotes, and that's our convention, even though double quotes can be used in Python for string as well. To access individual character in a string, we use square bracket. For example, if we want to check what's the first character of this school, square bracket, 0. 0 actually means give me the first character in school. So it's B. Keep in mind, string is case sensitive. And what about another position in school? School, for example, let's check 2. 0, 1, 2. That's actually the third character in school. I. So the third character in this, B-A-I, it is I. Now Python provides accessing string from reverse order, from the end. What if you want to check -1? What if I want to check the first character start from the end of this string? So it should be N. Well, let's say if it is N. Oops. Why is that? Oh, I'm sorry. This is because the name I spelled wrong. It should be S-C-H-O-L. If you spell it wrong, Python thinks it is a different variable, which has never been defined. That's why it's it raises an error. S-H-C-O-L is not defined. I spelled it wrong. Now I corrected it. Enter. Yes. The first character from the reverse of this string is N. Now what about I do this. Have to make sure I spelled correctly. What about I do this? 10. Well, guess what happens? If you access something is outside of this string, because the school has total 7 characters, and you give it 10. See if Python knows this. Well, Python indeed knows this index is out of range. Let's restart Python console. Restart it. We know we can use square brackets to access individual character in a string. What about we want to retrieve a substring from a string? This is called slicing. Again, let's use school. But this time we give it 2 words, 青岛, Baishan. Enter. We want to get a substring from this. So still using square bracket, but we want to retrieve the substring starting from the first position all the way up to 7. So this, in fact, will extract a substring from school starting at the first character and up to the 7th character. So let's check. Okay, it returns a substring from school. Now let's do another one. School, what about I want to do this? So this will return, this should return a substring from index 1 to index 2. Enter. In. I is at the index position 1, and n is at the index position 2. So when you slice in school from 1 to 3, it returns from index 1 to 2. Now let's do another example. School. Now I don't give it an index. This will extract the substring from school starting at index 9 all the way to the end. You can also do slicing from the other end. sh school. You use this negative sign to access a string from the other end. This would extract a substring from the 7th character from the other end. Now let me explain the index in a string a little further. Suppose we have a string s0 equals to Baishan. Well, I need to put this single mark. The index for string starts from 0 for the first character. So B is at index 0. And then from left to right, we increment the index 1 at a time. 2, 3, 4, 5, 6. So when I access the string by index as 0, it really points to the very first character in the string. If I do 2, this is at index 2. So it will actually points to the third character in the string. This is all because the index starts at 0. Another typical operation on a string is finding whether a string contains a substring, or in other words, finding whether a substring exists in a string. For example, at 0, this is our variable. Let's give it a string. We have 3 lessons a day. Now we want to find whether a letter E exists in this string. E. S. Find E. Return. So if the substring exists in the string, it returns the index because the first E is at the second position. The second position is actually index 1 because the index starts as 0. W starts as index 0, and E, this E starts at index 1. So we find E, the first occurrence of E is at index position 1. If we want to find a multiple letter substring, for example, half, now it returns 3 because H is at index position 3 in string S0. Now we have learned strings in Python. Next, let's discuss list. In fact, we have learned list a little bit in previous lesson where we introduced the concept of variables. Today, I'd like to dig into a little bit more of the details about the list in Python, the basic operations about it. We're going to still use Python console to learn the basic operations. I promise you after this, we should be able to, and we will do something more interesting. But for now, just bear with me. Use the Python console still. Remember, a list is a collection of ordered items. Remember, a list is defined by using square brackets. It represents a sequence of items or ordered items. List 1. If I give nothing in these square brackets, so it's an empty list. We can check the length of the list. It should be 0. Now, how do we add one item to the list? Use append. List 1, append. Let's add an integer number. Append will add the item to the end of the list. Now, if we check list 1, it has 1 item. Now, let's add another one. Append 3. Enter. List 1. It has 2 items now. Let's check the length of it. List 1. Enter. 2. So far, so good. Very similar to string, list can also accessed by indexing, which is the position of the item in the list. For example, list 1, square bracket 0. 0 points to the first item in the list. It should be 2. Then what about the next item? List 1, 1. This is the second item in the list. It must be 3. Now, what about we give it an index position that is out of the range and check if Python can detect it? List list 5. Yes, Python knows the position 5 is out of the range of list 1 because list 1 has only 2 items in it. The valid index positions for list 1 is only 0 or 1. So what about we don't want to add the item to the end of the list? We want to add item to the list at an arbitrary position. Then we use insert 10. This would insert at the index position 1 with the new item 10, list 1. Now you say the new item 10 was inserted at the index position 1, and it pushed the original item to the next position. If we want to remove an existing item in the list, we call pop, give it a position. So this list1.pop1 will remove the item at index position 1. Pop list 1. Now it has 2 items left because we removed one. The one we removed was at the position 1. So 10 was at the position 1. So that has been removed. Now if someone do this, list 1 assign number 5 to list 1, position 1. Remember, list is mutable. Mutable means the list can be changed. So when we assign 5 to list 1, we modify the list. It becomes 2, 5. The second item was replaced by 5. What about we want to clear everything from the list? We just call clear. Enter list 1. Now it's back to empty list. Now so far we have used the integer numbers for the list. List is a very versatile type or collection. It can store other types. For instance, list, let's store some strings. How about some chemical elements? Hydrogen and oxygen. Now list 2 stores string. List 2. All right. And we can do the same. Do the same thing, append a new item Z onto it. Remember, append as the new item to the end of the list. So Xeon should be added after oxygen. Oh, what happened? Oh, okay. Append. I spelled that wrong. Yeah, it has to be correct. We can also insert an item at a specified position. How about we insert another element at index position 1 of list 2. Enter list 2. It should have 4 items now. And calcium was inserted at position 1. The position 1 used to be this. And calcium inserted at this position. And it shifted, the position started from 1 all the way to the right. List also supports slicing, which means extracting certain portion of the list, list 2, let's extract the list from index position 1 to 3. Position 1, index 1 is this, 0, 1, 2, 3, exclusive, so it returns only 2 items. Now let's check list 2. So it is still 4 items. Why? When we do the extraction, it actually extracts this, but it creates a new copy to it. It did not really modify list 2 in place. Now list 2 stores 4 chemical elements, which are strings. It can still be accessed by indexing to it. For example, 3. That's the last item in it. Good. Like I just said, list in Python is very flexible. You can use it to store mixed type of data. List 3, integer type, a floating point number, and another string, carbon. List 3. It's fine. You can actually have lists within a list. This probably is the single most important feature of list in Python. For example, we have list 4. Let's have it for 0, comma, another list 3, 5. So it's a list, contains 2 lists. Of course, you can even embed list within a list within a list. So this basically gives a matrix in a sense. List 4 can be accessed by index 0. That gives you the first list. Now another 0. This gives you the first item in the first list. 0, 0 gives you the first item of the first list. So the first list in list 4 is this, for 0. And the first item of it is 4. So let's check it. Yes, it is 4. By using list this way, it can simulate the array in other languages. I'd also like to mention a very similar type to list. It's called tuple. We talked this before. The difference between tuple and a list is mutable, changeable. We saw it just in the above example. However, tuple is immutable. Once it is defined, it cannot be changed. For instance, T1, 2. Well, a 2-item tuple. I always like to check the length of the type of the data, so it's 2. And you can use the square bracket to access individual items in it. Let's index to it, 0. The first one of the tuple should be 1. So very similar to the way we use list, accessing a list. But you really cannot change it. For example, if you do this, 100, now you see type error. Tuple object does not support item assignment. Basically, that tells you T1 or tuple cannot be changed this way. Now we have learned some basics in this programming language, such as arithmetic operators, arithmetic operator precedence, how to do arithmetic in Python console, And we also introduced some types in Python language, variables, how to declare variables. In the last two lessons, we learned some basic operations of string and lists. Now it's time for us to move on to a little bit more advanced concept, function. Once we learn the basics of function, we can do some interesting stuff in Python. What is a function? A function is a series of statements which returns some value. A function can accept 0 or more arguments that can be used in the execution. Now, I took this definition from Python 3.7 manual. It captures the essence of what a function in a programming language. A function in a programming language is not the same as a mathematical function, although you can make an analogy to it to help you understand. For example, the arguments you pass to a Python function can be viewed as the independent variables, and the function performs certain computation and transforms or maps the input into a value to a domain. But the difference is a function in Python can return multiple values given the same set of inputs or arguments. And also a function does not necessarily to return a value. So sometimes a function is also called a subroutine or procedure, or sometimes it's called just method. The next question we should ask ourselves is, why bother doing Python in function or use a function at all? To tackle a complex system, it needs to be broken down into small, manageable pieces. This strategy is also called divide and conquer, and functions are somewhat like that. With functions, a complex system can be decomposed into more manageable, reusable, and testable pieces. Now let's take a look at how to define a function in Python. So you define a Python function with a keyword, def, and you give it a name. Inside parentheses, you can pass 0. You can pass 0 argument or as many arguments as you want, separated by comma. And at the end of this function header definition, you need to give it a colon. Now this is the function header. Keyword def and a function name, and inside parentheses, the arguments. Once you define the header of a function, inside it, you define, well, you can write the list of statements you want the function to perform. You can return value or not return value from the defined function. Now let's work on some real examples to learn this concept. We have been using Python console for our exercises. Now it's time for us to write our program in a file. To do that, first we need to set up a directory to store our Python files. Here I have a few directories already created. For you, you probably would say nothing underneath except maybe venv. Go to the root directory you created at the beginning of this class, new, and then click directory. You can give any name you want, but I suggest we use exercises. Exercises. Now you see the new directory is created. Next, we want to add a Python file to it. Again, right-click exercises directory, new, and select Python file. Here you can give a name, for example, function underscore basics, and make sure the file type is Python file. And click OK. Well, cancel, because for you, you don't need this. All right, now you have a Python file, a blank Python file open for you to edit. Let's write our first Python function. We want this function to calculate the arithmetic average of two numbers. df arithmetic average, parenthesis, x1, x2, and then at the end of this column. So now you have a function header defined. The function name is called arithmetic AVG. It computes the average of two numeric values. x1 is the first parameter, x2 is the second parameter. Now, how do we do this? Mathematically, the arithmetic average is what? Is x1 plus x2. Remember the precedence? We need to use the parenthesis to get this summation first and then divide by 2. This is the average of two numeric numbers. But we want this function to return this value. So you add a return to it. Enter. Now, a couple of things here. First, the function name is somewhat like the variable name. You can't have some special character in it. But most time, you just follow the way we define variables, it should be fine. And the function name should be meaningful. It should tell the reader or other programmers or developers what the function is. For example, here we are calculating the average of two numeric numbers. And of course, you don't want to give the function name called square root or power. So the function name should reflect what the function does. And second, notice there's indentation inside this function body. So this is the function header, and inside it, these are function body. This defines the statements that will be executed when this function is called. The indentation is important. Here we have only one line of statement. So long you have two spaces or a few spaces, indent to the right, you're fine. Now we have a basic function defined, a very simple function. It computes the average of two numeric values. How do we use this function? Here, we define the function. To use it, we call this function by typing the name of it, and we give the number we want the function to compute for us. For example, 10, 20. And of course, we want to get the result of the computation. Now, result is a variable we learned before. And this is the function we just defined. When this is called, it will go into this function and performs the average of two numbers and then return to this result. We can check the result by print it. Now we have a very simple program. To run this program, you go to the file name and right-click and run function basics. Okay, now in the output window, you see the number 15. It is exactly the average of 10 and 20. What happens when this program is executed is, first, Python knows there's a function defined, and the function is called arithmetic average, arithmetic AVG. And at the time when the function is defined, it does not really run this statement. It does not run this line. When Python reaches line 5, it knows there's a function called arithmetic AVG defined. It will invoke this function. When this function is invoked, the value you entered here, 10, 20, is passed to x1, x2. So the first parameter you supplied here is passed to the first parameter in the definition. And the second number you passed in this, and the second number you supplied here is passed to the second argument defining this function. So when these two numbers pass to this, x1 is 10 and x2 is 20. So when Python executes line 5, it goes here and assigns 10 to x1 and 20 to x2, and then performs this addition and then divided the summation by 2. Once this calculation is done, return. The return will exit the function and returns to where it left, returns to when this function is invoked. So actually the result is returned to this. And next statement is line 6. It prints the result. Now, what if I do this? 20, I switch these two parameters in this function call and save it, right-click, and run. So the result is still 15. Well, this is obvious. The average of 20 and 10 and 10 and 20 should be the same. But the numbers here passed to the function are different. So when you supply 20 as the first argument, 20 is actually passed to x1 and 10 is passed to x2. The result happens to be the same is simply because the average of two numbers does not really depend on the order showed up in this function. But there are cases when the position of the arguments are important. Now, what if I don't have the second argument in the function call? I save it, run it, see what happens. Well, you got an error. This is not hard to understand because this function expects 2 parameters. But here, when you call it, you only supplied 1. You get an error. How about you still give 2 arguments in this function call, but this time you, for some reason by mistake, you give it a string, in fact. Remember, string is marked by this single quotes. Save it and run, see what happens. All right. An error as well. Why? Because we really cannot add a number to a string. And the first argument 20 is passed to x1. The second argument 110, in fact, is a type of a string. And this is passed to x2. So here you have unsupported operand type 4+, int and string. This basically tells you you cannot add integer and a string. It does not make sense. Now this is a function that takes 2 arguments. Certainly, like I said before, a function can have 0 or many arguments, or as many arguments as you want. What about we want to define another function, def, a function that computes the summation, compute sum, but this time we define 3 arguments this function will perform on. So this function, with this function, we want to really add all the inputs up. This should be very simple. Return. We still want to return the result. x1 plus x2 plus x3. Enter. All right, to test it, as before, result equals compute sum. How about 1, 2, 3? Enter. You want to print the result. Save it and run basic. All right, 6. This is simple. A function does not have to return a value. So let's do something that does not return a value. Like I said before, a function does not have to return a value. So let's check this. So I have this program copied from somewhere else in my project, so that I saved some time here. So you do need to import this module. And this function will just make your computer, make your laptop to beep through the speaker. And noticing we defined this function and without any return here. To run this function, play 1 octave. Enter. Save and run. See if you can hear any sound. All right, you see the function does not return anything, but it performs certain computation, or it executes a series of statements without returning anything. So this function is we defined, and inside of this play 1 octave function, we reuse the function from the WinSound module. So there's a method called beep, which takes 2 parameters. The first parameter is the frequency you want to pass to WinSound, and the second one is the duration of milliseconds. So when you call this, it will ask your computer's speaker to beep at this frequency for this amount of milliseconds. Obviously, this is not a very good way to make a sound, but it demonstrates how a function can be used. Hi everyone, today's lesson I'd like to talk about two things. First, relational operators. Second, the basic logic in programming. First, let's talk about relational operators. Relational operators are used for comparison. Sometimes you can also call relational operators comparison operators. They are used to find out whether two variables or values are equal or not, or which one is bigger or smaller. The comparison operations are not limited to just comparing two numbers. They can also be used to compare strings, lists, sets, and other complex types. But no matter what you compare, the result from the comparison returns either true or false. There are 8 basic comparison operations in Python, which are very similar to other languages. I have summarized the comparison operations in this table. The first 6 comparison operations check the equality of two variables or which one is bigger or smaller. The last 2 really checks the object's identity, is or is not. Basically, it tells you whether one thing is the same as the other. We will be just focusing on the first 6 comparison operations today. Also, please pay attention to this comparison operators symbols. The less than symbol and the greater than symbol are identical to the symbols used in mathematics textbooks. But for less than or equal, greater than or equal, equal or not equal, they are not the same as you would see in a mathematics textbook. But it's not very hard to remember this after a little bit practicing. Like I said, the comparisons are not limited to comparing two numbers. They can compare other things, but let's start with number comparison in Python. All right, here's the Python console in PyCharm. And let's see, how do we compare two numbers? 3 and 4. And remember this symbol less than symbol. This should evaluate either true or false. If 3 is strictly less than 4, which it is, it should return true. Then what about 4 less than 3? Obviously, it should be false. Now let's compare whether 4 is greater than 3. Must be true. Then what about 3 greater than 4? No way. So it is false. Now let's check if two numbers are the same. Let's check if 3 equals to 3. I'm sure 3 equals to 3, so it must be true. And notice for the equal symbol, I have this 2 equal signs and no space in between. So if you do 3 equals 3 and you have space in between, this is treated as a different symbol in the language. it's a grammar error. Can't do that. So now what about inequality? Well, if we want to check whether one number not equal to the other, definitely 4 does not equal to 3. This should evaluate true. And this is not equal symbol in Python programming language. Let's do another example. 3 not equal to 3. This can't be true, so it is false. The exercise here, I understand, is very trivial. It's just that you guys should be familiar with these comparison symbols. And also make sure you understand the comparison returns either true or false. All right, let's keep going. We want to compare two numbers and compare whether one number is less than or equal to. For example, want to check on whether 3 is less than or equal to 4. And also notice I can have space in between this left arrow and this equal symbol. And 3 is less than 4, and that implies 3 is less than or equal to 4. So it is true. Now, if we compare 4 and 4, if we check if 4 less than 4, it must be false because 4 is not less than 4, so it is false. However, if we check whether 4 less than or equal to 4, now it becomes true. The same thing with greater than or equal to. For greater than or equal to 3, even though 4 does not equal to 3, but for greater than 3, so this still is true. And 3 greater than or equal to 3. 3 is not greater than 3, but 3 is equal to 3. So 3 is greater than or equal to 3. So it is true. Okay, now let's restart Python console so that clears the screen. Like I said, we can also compare types other than just numbers. What about we want to compare two strings? Let's check if me equals me. Well, we have two strings here. The first string has two characters, M and E. The second one are virtually the same. So it has to be true. In fact, when you compare two strings, it compares each character. So if I have the second string, the first character of the second string is uppercase M, would this be true or false? The string comparison is case sensitive, so the lowercase m is not the same as uppercase M. So this has to be false. Now what about I do this comparison? Oops. I want to compare two names. And let's check whether Alex is less than Bob. Well, like I just mentioned earlier, the string comparison compares character by character, and character A comes before character B. Strictly speaking, uppercase A comes before uppercase character B. And if a character comes before another character, then it's considered less than the second. So now Alex is less than Bob, and this evaluates true. For each of the character in the string, actually there is a number encoded for it. And the encoded number are in fact used for the comparison. But for now, you can just think about the comparison of two strings is based on alphabetical order. Well, of course, in actual programming or software, you probably would not say this direct number comparison or the string literal comparison. You usually would compare two variables. For example, we can declare variable A and let it equal to 4, and another variable, and assign 3 to it. Now let's check these two variables, 4 and 3. All right. Let's compare whether A equals to B. No, they're not equal, so it is false. What about A less than or equal to B? False. And what about A greater than or equal to B? Now this time it should be true. Again, in actual program, this is what you would say a lot of times, rather than something like this. Like I said, you can also compare other types. For example, what about we want to compare two lists? Remember, list is defined by this square bracket. Now I just defined two lists, A and B, and they are empty lists. Let's check whether A equals to B. Well, intuitively, they should be equal. So you compare two empty lists, they are equal. Now it should be true. Now what about I populate the list with something? What about B 3 and 1? Okay. If we want to check whether A equals to B, should they be equal or not? And keep in mind, a list is a collection with ordered items in it. So the order is important. And when you do the lists comparison, it really compares each item at the same position. So it will compare the first one item in A, which is 1, to the second list, the first item in the second list, B, which is 3. And they're not equal. So if one of the if the elements are not equal, the two lists cannot be considered equal. Now this should evaluate false. Correct. Now if you really want to compare whether two lists are identical in terms of they have the same elements, regardless of the ordering, you can, well, one way of doing it is sort. When you sort A, it becomes 1, 3, well, actually the same because it's already ordered. Now if you sort B, it should change the order, correct, to 1 to 3. Now if you check whether A and B is equal, it should be true now. In summary, you really can compare anything and usually of the same type. The key point is, for anything you can compare, you need to have a definition what is equal, what is not equal, what is less than, or what is greater than. Now it's time for logic. We just have discussed the comparison operations. Each comparison operation returns a Boolean value. A Boolean value can either be true or false. It cannot have any value other than true or false. For numerical values, we have operations that perform addition, subtraction, multiplication, or division. For Boolean values, we have Boolean operations. Basically, there are three types of Boolean operations on Boolean values. Suppose P and Q each represents a comparison operation. So in other words, P is a Boolean value and Q is another Boolean value. So for P and Q to be true, you need both P and Q to be true. In other words, if both P and Q are true, then P and Q is true. Now for P or Q is true, you need at least one of them is true. In other words, if either P or Q is true, then P or Q is true. Not P is the negation of Boolean value P. So if P is true, then not P is false. And if P is false, then not P is true. For Boolean values, we typically use a truth table. We use a truth table to find out the results of AND or not. Again, P and Q here each represent a comparison operation, the result of comparison operation. So P is one Boolean value and Q is another. A Boolean value, remember, can either be true or false. So for two Boolean values, you really have four combinations. Both are true, one is true, the other is false, one is false, the other is true, and both of them are false. Now, if both of them are true, then P and Q is true. P or Q is true. And not P is a negate of a true, it must be false. And not Q is the same, it's a negate of a true Q, so it is false. Now the second row is if P is true, Q is false, then P and Q is false. Remember, for P and Q to be true, both need to be true. Now we have only one is true, so P and Q can't be true. If it cannot be true, the Boolean value must be another one, so it is false. Now if P is true, Q is false, what about P or Q? Since P is true, you don't care about whether Q need to be true or false. P or Q is true. At least one of them is true, so P or Q is true. Now the same thing with P is false and Q is true. It's the mirror of the second row. Now for the last row, both P and Q are false. So P and Q is false. Because none of them is true, so P and Q cannot be true. And P or Q must be false as well. Because, again, none of them is true. You need at least one of them to be true for P or Q to be true. So P or Q is false, because P and Q, both of them are false. Now, the negation of a false Boolean value P is true. the negate of Q, which is false, is true. This is called truth table. This is a logic you may learn at college. And in fact, the Boolean value, the term Boolean is named after English mathematician George Boole. Well, if you're still confused, that's probably fine. Logic is sometimes confusing. Now let's use Python console to work on some real examples to help us understand. P, a variable, let's assign it with a comparison, 2 greater than 1. And another variable, assign it with another comparison, 3 greater than 2. P, Q. Now we know the results from comparison operations are true or false. So P and Q should have value either true or false. Both of them are true because 2 is greater than 1 and 3 is greater than 2. Now what about P and Q? Now if you look that up in the truth table, it should be true because both of them are true. Then what about P or Q? One of them is true, so it is true. Now let's do a negation. Not P, false, because P is true. Now not P has to be false. The same thing with not Q. It is false. Now this is an example of two Boolean values. Both of them are true. Now what about I have one value is still true, P still true. However, Q this time we make it false, less than 2. 3 less than 2 can be true. So P, Q is false now. All right. Now let's check P and Q. Because one of them is false, so P and Q is false. Now what about P or Q? Now for P or Q to be true, you only need one of them to be true. And at this time, P is still true, so P or Q is true. All right, that's the case when one Boolean value is true, another is false. Now what about both Boolean values are false? So now this time we assign false to P and false to Q. P, Q. Both of them are false now. P and Q. This needs to be false because none of them is true. You can't have P and Q is true. Now what about P or Q? Again, none of them is true, so P or Q must be false. Now if we do the negation, you negate the false, then it is true. Same thing with P. So it is true. Okay, let's restart the console to clear the screen. Now let's do another example. Suppose we have a variable called test score. We give it a score 90 points. And another variable, piano level. And we assign 8 to it. Now, there are certain schools require both test scores and extracurricular activities such as piano, how well you play piano. And if you have both test score greater than 90 and the piano level reach to a certain reach to 8, for example, they admit you to whatever major you want. So in that case, I hope this is more a realistic example. You want to test score greater than or equal to 90 and piano level greater than or equal to 8. So if this is true, meaning the student's performance meet both of the criteria, then he or she can be admitted. So it is true. So this condition, if a student passes this condition, he or she is good. So this AND operation checks both comparisons. Now what about another school is less selective? That school only looks for one of the performance metrics. For example, if that not so selective school only needs one of them to meet the criteria, meaning as long as the student has test score greater than or equal to 90 or piano level greater than or equal to 8, this student can be admitted to whatever major he or she wants. So it's less restrictive so long the student performs well in one of these areas, he or she is good. So true, because one of them is true. Now I use the variables to practice the comparisons and the Boolean operations. You can in fact do this just to get a handle of how these operations work. I mean logical operations work. You can do true, true, so true and true must be true. Now the logical operators that's unlimited to just comparing two. You can also do true and true. If you want, you can do another one. So this basically means for this whole thing to be true, you need each comparison operation be true. Of course, here the comparison is already true, so it must be true. In real applications, you may say A and B and C and D. So each of these variables A, B, C, or D represent a certain condition. So if I do this, that means you need all of this to be true for a certain thing to happen. Now if you want just one of them to be true for things to happen, you do this, A or B or C or D. Of course, if you have many of this, like and or mixed all together, you really need to have your logic figured out first. What do you want to check? Okay, let's get rid of this because I don't have variable A, B, C, or D defined. Now, another thing interesting in Python is the logical operations or comparisons can be chained. For example, you can do this, 1 less than 2 less than 3. This is equivalent to 1 less than 2 and 2 less than 3. Okay, let's enter. So this is true. Now you can chain more than just 3 comparisons. You can do as many as you want. So if I have this means we want to check 1 less than 2 and 2 less than 3 and 3 less than 4 and 4 less than 5. Of course, normally you don't do this. This is just for example. And in applications, you would compare variables. And the values in variables are not known in advance. That's why you need this. All right. I find if we have more than 3 chain together, it might be confusing. But if you just compare 3, that looks more close to the mathematical expression. That might work better. So anyway, you can either do this, chain the logical operators, or you can do this, 1 less than 2 and 2 less than 3. Either way, it would work. Logical operators work on Boolean values. If a function returns a Boolean value, of course, it can be used by the logical operators. So here I have a script file where I define 2 functions, func1 and func2. And here for each of the function, I have the print statement. This is just for debugging purpose. So the print statement here is called when this function is called. So for example, if func1 is called, you would say in the console output, func1 called printed out. Now this argument, return value, is for demonstration purpose. So this function, func1 or func2, would return whatever the argument passed into it. Now if I want to check func1 true and func2 true, what would happen? All right, because func1 returns whatever value passed into it, and so is func2. So if I pass true to func1, func1 returns true, and same thing with func2. Because for this AND operation to be true, both this func1 and func2 need to return true. In other words, both this func1 and func2 need to be evaluated. When both of them need to be evaluated, both of them will be called. So both func1 and func2 will be called. So if you run this program, you would say func1 called and func2 called. So let's run it. All right. Okay, this is the results from the script file. So the first block here really is from here. So you can say func1 called and func2 called. Now, what about the second? The second is still AND operation. However, this time I passed false to the first function and true to the second. And keep in mind, for the whole thing to be true, both comparison needs to be true, which means func1 needs to return true and func2 needs to return true for the whole thing to be true. However, when I pass false to func1, func1 returns false. That means no matter what func2 returns, the whole thing can be true. So in fact, Python is smart enough when the first comparison, the first Boolean value returned is false, Python won't continue on to evaluate the second part. So only func1 is called. Now you see only func1 is called in the output. Now the third is I pass true to the first function and false to the second. However, this time I check the OR. I use OR logical operation, which means the whole thing is true so long one of them is true, or at least one of them is true. Now, because I passed the true to the first function, the func1 will return true. Now, Python here, again, is very smart because it needs only one of them to be true to return true. It doesn't need to check the second one if the first one returns true. So only func1 is called. So again, func1 is called. Now the last, still OR operation, but this time I pass false to both functions. Again, for the whole thing to be true, you need at least one of them to be true. Now, because I passed false to func1, func1 returns false. So the first one is not true. So Python knows it needs to continue on to the next comparison or check on the next Boolean value. So in this case, both func1 and func2 called. Yes, sometimes this is, if one of the terms in the expression is skipped, it's called short circuit. But the logic is really intuitive to me. Okay, I think we have enough logic treatment today. Thank you and hope you enjoy. Now we have learned logical operations in programming. Logical AND, logical OR, logical negation. If we want to check if both conditions are true, we use logical AND. We use logical OR to check at least one of the comparison operations is true. And logical negation will negate the Boolean value. The result from the logical operations in turn is a Boolean value, which can take on only true or false. Now the question is, what do we do about these conditions, or the results from the logical operations? Simple. We take actions depending on the true or false from the condition. For instance, if a condition is true, we do one thing. If it is not true, we do another. Now, let's see how do we do it in Python programming language. In Python, we use if-else to branch the program workflow, to branch the program execution. For instance, if this Boolean expression is true, and this following statements are executed, the first line we can call it if test. Again, if is the keyword in Python. It's intuitive. If this Boolean expression, which can be a simple comparison operation or a few comparison operations chained by those logical operators. So if this expression is true, now the following indented statements are executed. Another form is similar to the first. Still, if a condition or conditions are true, this block of code indented to the right of if are executed. Otherwise, meaning if this Boolean expression is false, this block of code next to else are executed. Alright, now let's use if-else in Python. Now I have a blank Python file under my exercise directory. If you don't have the directory, you can right-click your Python sandbox directory and new and create directory. And if you do not have any file for use, you can create a new one. It doesn't matter what file name you use. It's just for writing a temporary code here. So you can right-click exercises, new, and Python file. All right, I have already created this file. It's blank. Now let's write some if-else statements here. A simple one is this. If, let's use any comparison condition. If 4 equals 4, print something here. How about that? Save it. Now noticing the syntax here. First of all, you have this colon at the end of this if statement. And also, you need to make sure you have correct indentation after if, because this defines the associated block when the above Boolean expression is true. So you can have multiple statements here, here too. Okay, save it, and let's run it. Before we run it, we should know what the expected outputs are, because 4 equals to 4, so this must be true. We should see this two-line output. Right-click this and run this file. Okay, now in this output window, you see 2 lines are printed. That's our expected results. Still in the same file, let's do something a little different. This is too trivial. Get rid of this. Now I have this defined somewhere. I copied it here. Now we have a function. Remember, a function is defined by using def keyword. So we use this function to check if a number passed into it is an even number or is an odd number. Now if it is an even number, we just print it is an even number. If it is an odd number, we print it is an odd number. Now this percent operator is, well, in fact, modulo operator. So if a is divided by 2, or the remainder of a divided by 2 is 0, that means a is an even number. If a divided by 2, if the remainder of a divided by 2 is not 0, then it must be an odd number. Of course, here we assume a is an integer number here. So we define a function that checks whether a number is odd or even. Now this is our simple tests. Look at this. Again, the grammar for if test is same as the one I showed above. You have this if test with colon at the end of it, and this is the comparison. If this is true, this is executed. If this is true, this is executed. Now we have two tests here. First, we check if number 6 is even or odd, or number 5. The second one, we check 5. Now when 6 is passed into this function, so this becomes 6. A is 6. 6 definitely can be divided by 2. There's no remainder of it, so 6 is even number. This line is executed. It would output this. And 6 divided by 2 is 0, so this is false. So this can be printed when this is called. Now how about this? Let's just run the first test. Check even or odd V0, 6. So we expect only this should be output. Save the file, right click, and run it. Now you see in the output, we only see 6 is an even number printed. So this line is executed. Now this is how we format output. This is how we format an output using print statement. This %s is a placeholder you can use to print a string type. The S stands for a string type. And this is output as is. Now the % here separate the format and the argument you want to plug into this. So we have only 1% as here. So we only need to supply one argument after the %sign. So whatever A here, it'll be in this %s. Okay, now let's comment this one, enable this one. 5 is an odd number. So when the argument is 5, when you invoke this method, this variable A becomes 5. And 5 modular 2 does not equal to 0. It has remainder 1. So this is not executed. And 5 modular 2, yeah, we just said it does not equal to 0. So this is executed. Now let's run it. And in fact, I can click this to run it. Okay, you see 5 is an odd number. That means this line gets executed, which also means this condition is true. Some of you probably have noticed or realized, in fact, when we check whether number is an even or odd number, we don't need to test both this and this. All we need to do is just to check one of them, because for integer number, it can either be divided by 2 or not. So only one of this is needed. Now let's have another version of this check even or odd function implementation. So we call this new version of checking odd or even v1. So let's collapse this. And we still want to use the same test cases, but this time we want to call the v1 version of it. Save it. Now this is the perfect place we use if else. So if a number modular 2 equals 0, which means it has no remainder, also means it's it can be divided by 2, it must be an even number. So if this is true, number A is even. If it is not true, that comes to this else block, which implies A is an odd number. Now let's save it and run it. Now we see the same results. Here, if a number can be divided by 2, and this condition is true, this block associated with if is executed. If this is not true, which implies the else part is true, the else part will be executed. So this block of statements and this block of statements are kind of mutually exclusive. Only one of them will be executed depending on the true or false of this if test. Now the if statement can also work on a compound conditions or Boolean expressions, meaning a condition chained to another condition by logical operators. For example, here I have a simple function. I call it a filter func. And what this does is, if a number passed in that can be divided by 3 and the number is greater than 20 and less than 30, I just print this number. Otherwise, this number is not what we want. So the condition here really has 3 comparisons. The first one, we check if A can be divided by 3. The second one, we check whether A is greater than 20. The third one is we check whether A is less than 30. And remember, in Python, you really can chain the comparison. So this basically means A is greater than 20 and A is less than 30. And it's pretty concise here. We have 2 test cases here, 10 and 20. We are expecting 21 should be printed out as 21 should pass the filter. So 21 should be printed in this string, meaning 21 is multiple of 3 and greater than 20 and less than 30. And when 10 is passed into this function, it does not satisfy the condition at line 3. So line 6 will be executed when 10 passed into this function. Save it and run it. Okay, 10 is not the number we want, and 21 is multiple of 3 and greater than 20 and less than 30. The if-else statements can be more complicated than we just saw. A if can be embedded with another if, and you can nest if within if. For instance, here, if this Boolean expression true or Boolean expression 0 is true, it executes these statements. Inside it, you can test another condition, Boolean expression 1. And if Boolean expression 1 is true, you execute something, and then you can test another Boolean expression 2. And of course, we know the if statements does not have to have else with it. So this if will be, if this if executed, then that's the end of this whole thing. Now let's take a look at a semi-real example. Suppose we are operating a robot. the first thing when we start a robot, for the robot itself, it needs to do some initialization work. So we have a function, we define it as robot initialize. And the first thing the robot wants to do is to check its battery. So if check battery works, the check battery function returns true, meaning it passed the battery check. It will do load memory, reload something from its past, and start a communication and initialize vision, for example. So you need the battery to work, and then you can initialize vision. So if the robot is able to initialize its vision, it can take action to scan surroundings. Otherwise, initialize vision fails. It just log a message. It can keep moving on to the next initialization work, initialize motion. I don't know, maybe the robot can really move without the vision. It's not entirely impossible. So initialize motion. If initialize motion succeeds, it will exercise motion. If initialize motion fails, which means it returns false, we just log something, whatever you want. Now we go back to this. If check battery fails, the whole block here associated with the true of check battery will not be executed. The else part will be executed. So if check battery fails, meaning it returns false. Now line 15 and 16 will be executed sequentially. So first it would send a message and then go to sleep. Now you see in this stopped code, I have if else nested within another if. And the things can be even more complicated if necessary, meaning you can have many if nested within if. There's no limits of how many if you can nested. Although there's a readability issue if you have too many ifs embedded within another if, or too many levels of nesting the ifs. So here I have only two levels. Now let's review a little bit of this if else again. So when this condition is true, the whole block of code from line 3 to 13, which associated with the true of check battery at line 2, can be executed. And the execution is from the beginning, from line 3 to line 13, one at a time, one by one. So if this becomes true, if line 2, if check battery is true, it would do line 3, reload memory first, then line 4, start communication, then executes line 5. Line 5 is another if test. So if it is true, we execute 6. Line 6. If it is not true, we execute line 8. After that, we move on to line 10 to check if we can initialize motion. If it is true, we exercise motion. If it is not true, we just log. Now if line 2 is false, the whole block will not be executed. Also keep in mind the indentation. The indentation here, meaning the start of each statement in this block must be the same. So this defines a block associated with this if. And this is really associated, this is scan surroundings. Noticing it is indented after this if, after line 5's if. So this surrounding, this scan surroundings statement is associated with this if. By the same token, these two lines, they are aligned at the same column. They are indented to the right of the else. So these two lines are the block when the else part is true. The else part is true when check battery returns false. And when else is true, first thing it executes the first line in this block, send a message, and then the next line go to sleep. Now I think this concludes our discussion about the basic usage of if-else statements. Numbers can be expressed by using any base. We are more accustomed to base 10 numbers, which are decimals. For each digit in a decimal number, it can have only a number from 0 to 9. For binary number, each digit can be either 0 or 1. We use decimal numbers every day. However, we use decimal numbers every day. In fact, we use binary numbers every day as well, just in an indirect way, because computers use binary numbers, and your cell phone is a computer. You use your cell phone every day. For any number, depending on the base, it can be expressed by summation of each of the digit times to the base to the power corresponding to that digit. The rightmost digit is at position 0. And from right to left, the position increments by 1 at a time. So for a decimal number, dn minus 1 to d0, it equals to dn times 10 to n plus dn minus 1 times 10 n minus 1 plus, and all the way to d0 times 10 to 0. Again, the rightmost digit would denote its position 0, and for decimal number is 1's position. And the position increments from right to left 1 at a time. So the leftmost digit we denote as position n. Now for binary number, it can be expressed the same way, except the base is 2 instead of 10. Now let's do this step by step using a few examples. Now suppose we have a 4-digit decimal number, 1990. Well, let me have a subscript here, D. So it denotes this is a decimal number. Like we said, from the right, starting from the rightmost to the leftmost, the position starts from 0. So the 0, the ones, is at position 0. And the tens is position 1. And 9, position 2. And this, the leftmost 1 is position 3. So this decimal number is equal to the leftmost position, 1, the digit at the leftmost position, 1, times, remember it's a decimal number, so the base is 10, and raised to the power of 3. 3 is really the position of the leftmost digit. Then keep going, plus 9, this hundredths 9 times 10 to power 2 and plus 9. This 9 is really this, tenths, times 10 to power 1 plus 0. Now this digit is 0. Again, base is 10 to power 0. So this equivalents to 1000 plus 900 plus 90 plus 0, and it is 1990. Now, what about a binary number? For example, a binary number 1010. And again, the position starts from the rightmost 0, 1, 2, 3. And also keep in mind for binary number, each position can be either 0 or 1. So it's impossible for a binary number. So it's impossible for you to see a binary number has a number other than 0 or 1. What this equals to is, let's start from the leftmost digit. It is 1 times, now you know the base of binary number is 2 to the power of what? 3, because this is really at the third position, plus this one, 0, times again base 2 to 2, plus this digit 1 times 2 to 1 plus 0 times 2 to 0. Now this equals to 8 plus 0 plus 2 plus 0. And this is 10. Let me put a subscript here. So 1010 binary equals to or equivalent to a decimal number 10. Make sure the numbers are in binary, otherwise 1010 may be confused as 1010. So here I have a subscript B here to denote 1010 is a binary number, and it is 10 in decimal. So if you're interested, we can work on another example. 1111 equals to 1 times 2 to 3, 1, 2 to 2, 1 times 2 to 1, 1 times 2 to 0. This would be 8 plus 4 plus 2 plus 1. So this is 15. So 1111. Yeah, let me better put a subscript here. So it is a binary number. 1111 binary number is 15 in decimal. So in other words, a number 15 decimal, in computer, you will say 1111. For decimal number 10 in computer, you actually would say 1010. Also here, for the binary numbers, here are positive numbers. There's no sign involved because negative binary numbers are represented differently. This table shows you the same number represented using different base. The first column is the usual decimal, base 10 numbers. The second is the binary we just talked about. And the third column is hexadecimal number. The hexadecimal number is base 16. So for hexadecimal number, each digit can have a number from 0, 1, 2, 3, 4, 7, all the way to F. So here for hexadecimal number, A, B, C, D, E, F, in fact, is a number. So if you say in a number, hexadecimal number, a digit A, it represents a decimal number 10. B is equal to a decimal number 11. And F is equal to a decimal number 15. In computer programming, we use both binary and hexadecimal. The hexadecimal probably is more succinct. For example, decimal number 15, you need to write 4 digits. However, if you use hexadecimal, you only need to write 1 letter. Now, the next question is, how do we represent a negative integer number in binary? We need a sign in the binary to tell us whether it is a positive or negative number. Now, the sign bit we use is the most significant bit, which is the leftmost bit. If the leftmost bit is 0, it is positive or 0. If the leftmost bit is 1, it is a negative number. And for a negative number, the formula of converting it to a decimal is the same. A negative number, a negative integer number, is represented by using 2's complement. One of the reasons for using 2's complement is for ease of arithmetic by hardware. Okay, now I have a few numbers here. Each of these integer numbers can be stored in 1 byte. A byte in computer equivalents to 8 bits. And each bit is really a single position in the binary, which can take 0 or 1. For number 0, the binary representation is all zeros in each of its bits. Now for positive number 1, remember we said the first digit, the leftmost digit, 0 means it's positive. So this is positive 1. Then how to store a negative 1? A negative 1, remember, first thing is the sign bit should be 1. 1 indicates this integer number is negative. And we said for negative number, we use 2's complements to store it. 2's complement is really 1's complement plus 1. Now, number 1 binary is this. Its complements, it's just the flip of each of the bit. Okay, so this is positive number 1, and this is the complement of number 1. And the 2's complements is really the 1's complement plus 1. So negative 1 is this number, 1, 1, 1, 1. This is negative 1 in binary format using 2's complements. Now, what about negative number 2? Very similar. This is number 2. And its complement is the flip of each of the bit. And then 2's complement plus 1. Now 1 plus 1 in binary, 0. Then we carry 1 here, 1. All the remainings are still 1. So for negative 2, the number is 11111110. Now what about negative 127? Interesting, you see, for the positive 127, this actually is the largest positive number a byte can store, because the first bit has to be 0 for the positive number, and all the rest of the bits are 1. That makes the number the biggest. You can't have a positive number more than 128 in a byte. Now for negative 128 is the complement, 1's complement, then plus 1. So this is negative 127. So far, for the 1 byte integer numbers, the positive and negative are symmetric. So you have a positive 127 and you have a negative 127. But for the negative numbers in 1 byte, you got one extra number. That's negative 128. The negative 128 is really 1,0,0,0,0,0,0,0. For a byte, which has 8 bits, with each bit has only 2 possibilities. So the total possibilities is really 2 to 8 equals 256. So in other words, you can store 256 distinct numbers by using 1 byte. And here, for the integer numbers, for 1 byte, we can have from 1 to 127. That means 127 positive numbers, and 10, and from -1 to -128, that is 128 negative numbers. The nice thing about using 2's complements is, if you notice, if I plus 1 and -1, it is 0. So in other words, the subtraction is essentially the addition. So we almost convert the subtraction to addition. That's the purpose of using 2's complements. Now let's do some binary numbers arithmetic. It's not very different from decimal numbers. So the first one is 001 plus 0010. And I have the subscript B denoting these numbers are binary. So we align the digits, and then we add each of them. 1 plus 0 is 1, and 0 plus 1 is 1. And then these two are 0. So 0011, and this is decimal 3. So there's no carry involved in the first addition. Let's look at the second one. Again, 2 binary numbers, 0001 plus 0011. We align the digits or the bits. We start from the rightmost bits. 1 plus 1 is 0, but we need to carry. Okay, there's 1 carried to the next bit. So this 1 plus this 1 is 0, and again we have a carry. And the carry plus 00 is 1, 0. So this is decimal 4. Why is this decimal 4? Remember, we can convert from binary to decimal by using each of the digit times the base to the power of that corresponding to that digit. So this is really 2, 2. So which is 4. Now the next one, a negative number, minus 2 plus 1. The first bit is 1, indicating this is a negative number. And remember, negative number is represented by using 2's complements. And a decimal minus 2 is really 1110 in binary. So minus 2 plus 1 decimal in binary is 1110 plus 0001. This is 1111. So this is minus 1 in decimal. Now, again, minus 2 plus 1 is the same as 1 minus 2. So like I said before, the subtraction becomes addition. That's the nice thing about using complements. We now know how integer numbers are represented in binary format. And what about non-integer numbers, meaning number with fraction portion? Floating point numbers represented with 3 parts. This is a 4-byte floating point number. The first bit, the leftmost bit, is the sum bit, very similar to the integer number. If it is 0, this number is positive or 0. If it is 1, this number is negative. From bit 30 to bit 23, these are the exponent. So the next 8 bits from following the sign are for exponent. From bit 22 to bit 0, these are the significant. So this is the format for 4-byte floating point. So we will not go to the very detail of this. We may come back to this when necessary. We have learned string and some of its basic operations in previous lesson. And we know each letter in a string is a number, in fact, in the computer. For instance, a lowercase a lowercase character a, the number for it is 97. So in computer, 97 is for a character A. Now this way of encoding these letters are called ASCII encoding. So this table also called ASCII table. It has the mapping of each of these English letters or symbols to a number. And the number in the computer, in the end, is still a binary format. When you compare a string letter by letter, in fact, it's comparing the underlying encoded number. Next, I'd like to talk briefly about bitwise operations. When we do bitwise operations, we are not really concerned about if there's a sign in the byte. All the bits in the byte are treated the same. The first one, we are doing bitwise AND. The bitwise AND operator is this ampersand. For bitwise AND, when 2 bits are 1, the result is 1. Otherwise, the result is 0. We align the bits of 2 binary number, 0010 and 1010. We can start from the rightmost bit. 0 and 0 is 0. 1 and 1 is 1. Both bits are 1, it is 1. 00 is 0. 0 and 1 is 0. So the result of this bitwise AND is 0, 0, 1, 0. Only when 2 bits are 1, the result bit is 1. Now the next operation is called bitwise OR. The symbol is a vertical bar. For bitwise OR, the result bit is 1 as long as one of them is 1. We start from the rightmost bit. 0, 0 is 0. 1, 1 is 1. One of them is 1. 2 ones, still 1. 0, 1, 0 is 1. Now the next operation is called bitwise exclusive OR. The operator is this upper arrow. This upper arrow, you can find this upper arrow in number 6. For bitwise exclusive OR, the result bit is 1 if the 2 bits are different. 0, 0, the same, so it's 0. 1 and 1 is the same, so it's 0. 0, 0, the same, 0. Now this last bits, one of them is 0, another one is 1, they're different. So the result bit is 1. This is called exclusive OR. The next bitwise operation is called invert. Invert basically flips each of the bit. So 0 becomes 1, 1 becomes 0. 0 becomes 1, and 1 becomes 0. There are 2 shifts operators. One is called left shift. It's double left arrows. If I shift by 1, this shift 1 to left by 1. This becomes 0, 1, 0, 0. So this one shifted to the left by 1. Now this 2 right arrows is called right shift. If I shift by 1, this would shift this one to this position. So this becomes 0, 0, 0, 1. Now you can keep shifting it. If you keep shifting it, for example, if I keep shifting it by another 1, this becomes 0, 0, 0, 0. So this one shifted out. So there's no circular in this case. Now I want this whole lesson for you is just for knowledge-wise. The bitwise operations are used a lot in automations. And each bit here may represent a state of a sensor. Hi, I'd like to keep talking branching in Python programming in today's lesson. Suppose we want to have a function that returns the day of week in a string. Because in computer program, sometimes we store the day of week as a number. The reason of doing that is for ease of computation. Numbers are good for computation. However, when we want to display the day of week back, we want to display them as a string. For instance, 1, we should display Monday, and Tuesday for 2, and Wednesday for 3, etc. We have learned if-else, and one of the ways of doing that is obviously using if-else. So here I have a function. I define it as day of week underscore v0. v0 basically means this is not our final solution. It takes one argument day, and the valid range of this argument is from 1 to 7. Now inside this function block, first we check if day is equal to 1. If it is 1, we print Monday. If it is not, we check if it is 2. If it is 2, it is Tuesday. If not, we keep checking. The last, we check if day is 7. That means if the days we have checked are not one of 1 up to 6, then last we check for the 7. If it's 7, it is Sunday. If it is not, that means we have checked from 1 to 7, and none of that equal to the input argument, and then we have to say this day is not defined. All right, let's run this function. Day of week underscore v0 1. Let's check 1 first. Click this button, and sometimes I think you can right click on this file, the tab. You can also find the current active tab is the file, and you run it. Monday, so the output is Monday. And let's check another day. How about 6? It should be Saturday. All right, it is Saturday. Then what about 9? We know 9 is out of the valid range. Run it, not defined. Everything seems all right so far. And if you want, you can check all the other inputs. They should be all good. If all we know is if else, this might be the only way of doing it. However, if you really look at this program, even it has only how many? 24 lines of code. But you see there are so many if-else nested within another if-else. This definitely doesn't offer a good readability. So in Python, there's a slightly better way of doing this, given a case like this. I see slightly better way of doing this is because for a task like this, you actually have a third option. But let's look at this second, slightly better way of doing this. Now let's take a look at the second way of doing this day of week. And I have the function defined as day of week underscore v1. It's an improved version of getting a string representation of day of week. It still takes only one argument, a number. The valid range of this argument is from 1 to 7. Obviously, there's only 7 days in a week. The difference here is really, instead of nesting if-else within else, we use elif. What that means is if the above condition are false, then it moves on to check this elif. For example, when we come into this function, we first check at line 27 if day equals to 1. If it is equals to 1, that condition is true. And this block and this statement is executed. It prints Monday. If this is true, the rest of this will not be executed. If this is not true, if day is not equal to 1, it moves on to check the next elif. It checks if day equals to 2. If day equals to 2, it prints Tuesday. If day is not 2, so this condition is false, it moves on checking the next elif. Once it finds a match, once a condition is true, the whole function ends, or this whole if-else block ends. So, for example, if day is 5, it would come to here, and because day is 5, then this is true, and this prints Friday, and it exits or it goes to the end of this whole if, elif, else block. Now we have the last else. That's kind of a catch-all condition. Meaning if the day is not in 1, 2, 3, 4, 5, 6, 7, it goes to this else part, not defined. So if you really think about this is not very different from if-else. Then you embed another if-else. But this does offer a much better readability. And the whole block becomes much more clear. So this if, elif, else, multi-way branching sometimes very helpful. It manages your code in a much better way. The key point here is once one of these if or elif condition is true, the rest of these conditions are not checked. Now let's test this new def week implementation. All right, so this time it's gonna be V1. And let's test 1. Run it. Okay, Monday, correct. What about 3? Wednesday. Now let's check 8. This should go to that else part. Not defined. This is our expected results. The second way of doing this indeed provides a better readability, and the second function has less length of code. It's much more easier to read than the first version. However, like I said, there's a third option. That probably is the best. The third one, in fact, is using a dictionary. Remember, a dictionary is a collection of key-value pair. So in our case, the key would be the day in numeric format, and the value would be the string representation of the day of week. So using a dictionary, you can very efficiently to retrieve the string day of a week given a number, given the day as a number. But since we are talking about if-else, the multi-way conditioning branching, we will skip the dictionary part. Now let's look at another example using if, elif, else. And this time what we want to do is to have a function that converts a numerical score to a letter grade. The score could be the overall score of one of your courses. If your overall score is greater than or equal to 100, your final grade is A+. And if your overall score is from 95 to 100 exclusive, then your letter grade is A. And there are several grades from A+ to D or D to A+, and depending on where your overall score falls in the interval. Now here's the function. The function name is getLetterGrade. It takes one argument, score, and the argument should be a numerical type. The implementation seems to be very simple. We can just basically follow the rules defined above. So if your score is greater than or equal to 100, then your letter grade is A+. So if this condition is true, this block, this statement gets executed, and the rest of this will be skipped. And if your score is not in this range, it moves on to check if your score is greater than or equal to 95. So the order of checking the score here actually plays a role. Because if your score is less than 100, the first condition is false. It moves on to the second elif. So when it reaches to this line, when it checks this score, the score already less than 100. So you don't need to check the score in the line 5 elif if it is less than 100. It's already checked before. Okay, so if score is greater than 95 here, it basically means the score is greater than 95 and less than 100. So it returns A. So if this is true, we return A. Now, if this is not true, it moves on to the next elif. It checks the score if the score is greater than 90. The check here is sufficient because when you reach to line 17, checking whether a score is greater than or equal to 90, that means the above two conditions are false, which means the score can't be greater than 95. So here, in fact, it implies the score is less than 95. If this is true, that means your score already falls into that 90 to 95 range. So you can return a -1. I'm sorry, you can return a minus. The following are all the same. So here you still use if else, but the trick here is the order of the checking, somewhat important. This is no surprise because each elif only gets executed when the above conditions are false. Okay, let's test a few cases. So I have already typed in. So let's save us some time and let's run it. Okay, the first one is A+. 101 is A+, 98 A, 91 A minus, 85 B+, 82 B. Well, that looks correct. We have learned variables and functions. We know we can use variables to store data, and we have used variables in some simple functions. Now we need to learn the concept of variable scopes. Without a good understanding of this, it may cause mistake and confusion later. Now I have a blank Python file. It has nothing so far. Let me do something. Print x. If we run this, obviously we know the x has not been defined. It would cause name error because x is not defined. Now what about if I define x after that? X assign 20 to x. If I run this, would this print still error out? Let's try it. Run it, still. Because Python is interpreted, it's not compiled. So when it executes the first line, the x is not assigned yet, so it doesn't know where to get x, even though x is assigned later. Now if we print x after, comment this out, this should be fine. If we run it, yeah, x is 20, because at line 3, the x has been assigned and known to this file. I added 2 more functions in this file, func0 and func1. Func0 has a local variable a, and we assign 10 squared to it. Coincidentally, func1 has a variable name also called a, and we assign 10 cubed to it. The variable a here, we see it as a local variable. It is only visible within the function. So this a at line 6, after it is assigned 10 squared, it can be only referenced in function 0, of course, after line 6. And this a at line 10, after it is assigned 10 cubed, it can only be referenced within func1. So if you comment this line out, func1 will not work. The a is not defined. Even you may argue, oh, there's a defined in line 6. But like we just said, this a is only visible by function 0, only visible within func0. So let's remove this comment. And again, both this a in func0 and this a in func1 are local to their respective function. And if you print a here outside of func0 or func1, it would not run because a is not defined anywhere in this file outside these two functions. You run it. Yeah, you see name a is not defined, line 13. All right, let's comment this out. And if you're interested, you can run this func0 and func1 and run it. So func0a is 100 and func1a is 1000. I added another function, func2 here. Func2 is simple. At line 18, it checks a variable called x. If it is greater than 100, it prints func2 x is greater than 100. Otherwise, it prints x is less than or equal to 100. Now notice at line 18, func2 can directly reference a variable called x without any problem. That's because this x is defined at the very beginning of this file, at line 2. When we have a variable defined outside of function in a file, we call this variable has a global scope, global in this file. So everywhere after line 2 in this file, this variable should be able to be used. That's why we can do this here without error. So if we run it, it should print this because x is 20, it's less than 100. So let's run it. Yep, x is less than or equal to 100. So in other words, within a function, it can reference a variable defined outside of it, so long that variable is at a file level. It has a global scope. And what about if we have another function, func3? Within it, it assigns a value to a variable x. Now we have a global variable named x. We also have a local variable named x. This local variable x, by assignment, it hides, it shadows the global one. So x at line 26 is 200, and x is greater than 100. We should see this line printed out if we run func3. The difference between line 26 and line 18 is line 18 references a variable directly, and that variable is at a global scope. And line 26 assigns a value to a variable the variable happens to be the same name as a global variable. This x shadows the global x. And within func3, the x after line 26, it is the value 200, and it should print this. However, at line 26, this variable is still kind of local. It just shadows and hides the global one, but it doesn't replace the global one. So after func3, if we print x, this x is still the global x. So let's run it. Func3, because x is 200, now this is true, it prints this, x is greater than 100. Now after that, we print x. Now this x is still the global one, which has not been changed. Now we know a function local variable with the same name as a global variable hides that global variable. If that is your intent, meaning you just want to use the name of the global variable, not the value of the global variable, it is fine. It hides the global variable. You use the same name inside the function. You do whatever you want. And the global variable is not affected. However, what if you do not just want to use the name of the global variable, you essentially want to reference the global variable directly in the function? You use this global keyword. That way, whatever you do inside of this function after this global x, this x is no longer a local variable to func4. It is the global x defined at line 2 at the very beginning of this file. So if you reset or you modify the x, it actually changes the global x value. So let's run this program. All right, func4x is 0. That's this line. We set it to 0. And the global one, this x, becomes 0 now. Next, let's discuss loop in Python. Suppose we need to print 10 different numbers using print statement, and we are asked to print one number at a time. Obviously, one way of doing it is write 10 print statement. However, this doesn't seem to be very appealing, because what if we are asked to print 100 numbers or even more? And to make things worse, what if we don't know the numbers in advance? Like other general programming language, Python provides a loop language construct to deal with situation like this. With a loop, you can repetitively execute a block of statements. Now, one type of loop in Python is called a while loop. To be exact, is while else loop, because there's a else part following the while part. Now, here's our simple while loop example in Python. The while loop starts by testing a Boolean expression. As long as that Boolean expression is true, a block of statements will be executed repetitively. So in our case, at line 3, we test a variable x, if x is less than 10. If x is less than 10, the execution goes into this while body, goes into this while loop, and executes the first statement in the while loop, which is line 4, and then line 5. After line 5, the execution goes back to line 3. As long as line 3 evaluates true, line 4 and line 5 are executed repetitively. If line 3 is false, the execution jumps to the else part by executing the first statement in the else part. That's line 7. And then line 8. Then exits the while-else loop, execute the first line after the while-else loop, which is line 10. So the execution goes like this. At line 2, we assign 1 to x, local variable x. X is 1 now. Then the execution goes to line 3. At this time, x is less than 10. So it enters this while loop. And first it prints the current x value, which is 1. And of course, we don't want to print a new line after it prints 1. And we append a blank space after the print. After that, we increment the variable by 1. So x becomes 2 now. After line 5, it goes back to line 3 and tests that condition again. At that time, x is 2, it's still less than 10. So the loop keeps running. It prints 2, and then increment 2 by 1, x becomes 3. And then it goes back to line 3 again. So as long as x is less than 10, it will keep printing the number and then increment. So you can say when x is 9, it will still go to the inside this loop and print 9. After 9, x increments by 1, it becomes 10. Once it is 10, it goes to 3, and 10 is not less than 10, and that condition becomes false. So it enters this else part, print a new line, and also print another line telling you the end value of x, which is 10. So we can, without running this, we should be able to say this one executed 9 times. It prints the number from 1 to 9. This is printed only once. Okay, let's run this example. Run it. Okay, exactly that's what we said. It prints 9 numbers. These 9 numbers came out of this loop, this while part. And then we see another line printed after that. That's exit loop x is 10. That's this one. This is executed only once. The second example is about using while loop to iterate through a list. And this time, we don't have the else part because the else part is optional. Now first, at line 13, we initialize a list. This list contains 10 elements. At line 14, we get the length of the list. Line 16, we initialize a local variable index to 0 because that's the first position of the list. And the list in Python is 0 index based. Line 17 to line 19 defines this while loop. As long as the index, which is the position pointing to the list, as long as that position is valid, is less than the length of the list, we can retrieve the element at that position. All we want to do is, like the example 1, just print it. After we print it, we increment the index by 1. That will move the position to the next. After line 19, it goes back to the beginning of the while and test this expression again. So long index is less than the length of the digit of the list, line 18 and 19 are executed repetitively. Now, important thing here is we keep increment index at the end of each loop, so that would guarantee at a certain point of time this condition becomes false. If the condition never becomes false, you end up in an infinite loop. Of course, for our first lesson about the while loop, we are not so worried about that. Now let's run this example, while loop example 2. Run it. All right. You see, the elements in the list are printed one by one. All right, another simple while loop example. While loop example 3. It's a while loop without the else part. First, it prints a blank line, and at line 23, we initialize this local variable to 0, and line 24 to line 27 defines this while loop. As long as height is less than 5, we print a number of characters. The character is asterisk. How much to print depends on the height. If height is 0, 0 plus 1 is 1, the number of characters is 1, so this character times 1 is 1. That means you print just 1 asterisk. After that, you increment height. As long as height is less than 5, line 25 to line 27 are executed repetitively. Now this while loop is executed 5 times. The first time height is 0. Second, height is 1. Third, height is 2. Four times the height is 3. When height is 4, it executes 5th time. After the 5th time, height becomes 5. And then line 24 evaluates false. It exits the while loop. So this while loop executes 5 times. And each time it prints a different number of asterisks depending on the height. Let's run it. Okay, it prints something like a right triangle. There are 2 statements can be used with a loop. The first one is called break, which allows you to exit a loop at any point. Another one is called continue, which moves the execution to the very beginning of the loop. Now let's take a look at how we use break and continue in the loop. Here I have a function called collect random numbers. It has one argument, time interval seconds, which has a default value 1. With the default value, that means when you invoke the function, for example at the line 30, without supplying the argument, the function assumes this argument has a value 1. This function uses a while loop, and inside this while loop, it keeps generating random numbers and put it into the sum numbers list until the loop has been running for more than time interval seconds. In other words, this function generates random numbers within this given time interval. The first thing before entering this while loop is to record the current time, because we need to know how long the loop has been running. Time.time returns a floating point number which represents the total number of seconds since the epoch. The epoch on Windows is January 1st, 1970. So starting time is a floating point number which represents the total number of seconds since a certain point of time. Now here's the loop. The first thing when we are in the loop is to check the current time, because we need to know if the running has elapsed the given time interval. Line 14 does exactly like that. So current time less start time. If it is more than the time interval in seconds, we are done. At line 16, it exits the while loop. When it exits the while loop, it goes to the first statement after the while loop, which is line 28. Another condition that will exit the loop is when the length of some numbers equals to 100. The internal list, the some number list, starts as empty. So whenever the list has accumulated 100 numbers, we are done. We also exit the loop. If we don't have enough numbers collected or we still have time, now we go to 18 to generate a random integer number. Random.randint 099 returns an integer number randomly from 0 to 99 inclusively. Once we have the number, we check if it is a multiple of 3. So if it is a multiple of 3, that is x modulo 3 equals 0, meaning no remainder, it calls continue. Continue moves the control, the execution, to the top of the loop, which is line 11. And then loops again. If x is not a multiple of 3, it checks if x has been added to the list at line 23. If x has not been added to the list, we just simply add it to the end of the list. Line 26, we simply call time.sleep to pause the execution for a certain number of seconds. This would just limit the numbers in the list. So again, at line 14 and 15, if one of the conditions evaluates true, meaning if either the loop has been running for more than this amount of seconds or our list has enough numbers, we exit the loop. The break, in fact, would exit the nearest loop associated with it. What that means is if I have a loop within a loop, the break would only exit the nearest loop. In this case, the loop started at line 11. The same thing with continue. Continue only goes to the top of the nearest loop associated with continue. Let's collapse this. When the loop ends, we simply return the list to the caller. Line 30, we call this function, and then 31, we print the result. So let's run it. All right, pause for about a second. And now you see there's a list with 10 different numbers in it. You run it again, you get a different result. And this time, it has only 9 numbers in it. This is for obvious reason because we only generate we only put unique numbers into this list. And there's no guarantee within this time interval we would have generate 10 different numbers. It's random. There is another type of loop called a for loop in Python. For loop is great for iterating through a list or collection in general. Here we have a digits list, and at line 3 shows how we use for loop to iterate through it. Now x is a variable. When used in this way, it will be assigned each element from the digits list. So for each element in digits list, what do we want to do? At line 4, we simply just print it. Of course, if you want to do more, you can have multiple statements within this for loop. Here, I overwrite the end argument with empty space. That means we will print each element at the same line instead of at a different line. So let's run it. All right, here's the output. Let's take a look at another example of using for loop. This time we use the built-in function range to give us a sequence of numbers to iterate through instead of using a list directly. The range function takes 3 arguments: start, stop, and step. All the arguments must be integer numbers. The first argument tells the range the first element to generate, or the first integer to generate. And the second argument tells range when to stop generating the number. And the step is the offset to each preceding or previous number. So in this case, range 1, 10, 1, it would generate numbers from 1 up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. So let's run it. It has 9 numbers because the step is 1. So each element is 1 offset to the previous one. If you make the step to 2, that will skip 1 number from the previous one. So if you run this again, it should be the result should be 1, 3, 5, something like that. Yep, 1, 3, 5, 7, 9. Also notice the stop argument is not included. Now let's look at another example of using range in for loop. But this time, notice the start is less than the stop and the step is negative. So this actually makes sense. So the first number generated by range is 30. The next one is 30 minus 5, which is 25. The third one is 25 minus 5, which is 20. And until the number is 0. Actually, 0 is not included. As long as the number is greater than 0, it would keep subtracting 5 for the next number. So let's run it. Yeah, the first number, 30. The next number is 5 less than the previous one. And so the third is 5 less than the second one. And the last one is 5. Because 0 is our stop argument, so 0 is not in the range. You can, of course, use continue and break in a for loop. So for this example, we still use range to give us a list of integer numbers. And this time, first we check the value, the x, if it is 3 or 4. If it is 3 or 4, we continue, meaning it would go back to the top of the loop. And for this case, it would retrieve the second element from the range and assign it to x, and then goes into this again. If x is not 3 and not 4, then it checks if x is greater than 8. If x is more than 8, it exits the loop. So what this for loop produces should be a list of numbers without 3, without 4. And also the number produced by this loop should not have a number more than 8. So let's run it. 1, 2, 5, 6, 7, 8. Correct. We don't have 3, we don't have 4, and we don't have a number 9, which is more than 8. All right, our last example of using for loops. And this time, what we see here is a for loop inside a for loop, which is nested in another for loop. It's a triple for loop. Before we go into this triple for loop, let's run it. Well, from the results, you see it's a different permutation of number 1 to 3. And we know the permutation for n is n factorial. So if the total different numbers is 3, and the total different permutation would be 3 factorial, which is 6. So we have exactly 6 different permutations showing here. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. That's all the possible permutations from number 1 to 3. Well, this is a very naive way of permutating numbers. However, still worth looking into it. And in this example, continue makes great use here. The first for loop uses range 1, 4. That means I will take on a number from 1 to 2 to 3. So the possible values for I is 1 to 3. And each time we enter the first for loop, I changes from one number to another, starting from 1. Same thing with the second loop and the third loop. The trick here is the first number, the first position in the permutation is from the very outer loop, the first for loop. So you see here 1, 1, 2, 2, 3, 3 is from this loop. And the second position is from this loop. And the number for the third position is from the innermost loop. Of course, the permutation would be printed in the innermost loop. The trick here for the permutation, you can't have the same number for the position which has been used for the previous positions. For instance, if the first position's number is 1 and the second position's number is 2, the possible number for the third position must be 3. It can be 1 or 2. That is exactly what line 26 does. Meaning if we have the permutation for the first positions fixed, we have to make sure we don't repeat the numbers used by the previous positions. Now, the line 23 has a similar role here. So once the first position is determined, for example, if the first position has number 2, when it comes to the second loop, it checks J. J can't have 2 here. It can't repeat what the number has been used by all the previous positions. So if J is the same as I, it would continue. It would skip that number. Anyway, this is just an illustration of using a continue, and also you can nest a loop within a loop. To really do a permutation, we should use some algorithm. And in fact, with what you have learned with the loops, the lists, and all the basic operations you can apply on a list, you should be able to come up with an algorithm that permutates any numbers. Let me explain this triple loop step by step. For each of the loop, it needs to iterate 3 numbers. For I, it starts number 1. Then starts the second loop. The first iteration for J gets the number 1. And line 23 evaluates true, 1 equals 1. So continue moves the execution to the nearest for loop. It continues to the next value for J, which is 2. Now, line 23 is false. It goes to 25 and starts the iteration for K. The first value for K from the range is 1. And line 26, it checks whether K equals to J or I. At this point of time, K equals to I, so continue back to the for K loop and gets the next number for K, which is 2. And 2 still equals to 1 of I or J, so continues again, get the next number from the range, it is 3. Now, line 26 is false, execution goes to 28. 28 prints our first permutation, 1, 2, 3. After that, the innermost loop ends. Now for each loop, it needs to loop through 3 different numbers. For the innermost loop completed, but the second loop not yet. It needs to move on to the next number, 3. And 3 is not equal to 1, so the innermost loop, execution goes to the innermost loop, the K loop, and it starts all over again. The first one for it is 1. Too bad. 1 is the same as I. Then next number 2. All right, 2 is not the same as I or J, so we can print this combination, 1, 3, 2 now. After 2 is done, K gets the next number from the range, which is 3. But 3 is the same as J. So it continue, but it's already the end of it. The innermost loop finishes. Now it goes to, the execution goes to the second loop, J loop. J loop completes, and then it goes back to the outer loop. Outer loop gets its next value, 2. For each of the outer loop, the next loop will iterate 3 times. When I is 2, J starts from 1 again. And 1 is not equal to 2, and k starts its iteration. 1, not good. 2, not good. 3, okay, it is good. Then we print 2, 1, 3. Now the second number in the second loop, 2. 2 equals to 2, continue. And next number, 3. Now, line 23 is false. We can go to the innermost loop and start all over again from 1. 1 is good. So we can get 2, 3, 1. What about 2? No good. 3, no good. You can't have the same number that repeated that's already showed up in the previous positions. All right. The last number in the first loop is 3. Again, for each number in the outer loop, you have 3 numbers in the next loop. So the first loop has 1, 2, 3 to iterate through. And for each of this, the second loop will iterate 1, 2, 3. The same thing for the third iteration for I. And for each of the second loop, it gets another 3. 1, 2, 3 for k. 1, 2, 3. So without this checking at line 23 and line 26, you actually would end up having 27 permutations, and most of them are duplicates. I hope this helps you understand this triple loop. We have learned the basics of functions, and we know a function can take 0 or more arguments. Now today I'd like to discuss more about arguments passing in Python. First of all, the general rule about arguments passing in Python is arguments are passed by assignment. For instance, I have a simple function here, func0 with 1 argument. And assuming this argument is a numerical type, what this function does is simple. At line 2, it doubles x. Now this times equal to 2 is a shorthand of x equal to x times 2. At line 6, when func0 is invoked, when we pass a to func0, x is assigned the value of 10, or x is assigned to the value pointed by a. So that is called passing by assignment. And also pay attention, the x is really a local variable. So at the time when x is assigned the value of a, both x and a are 10. But inside it, x is a local variable to func0. At line 2, x is reassigned to a different value. So what that means is 10 passed to x, x doubles itself, is 20. The print at line 3 would print 20. However, because x is a local variable and reassigned to a different value, what changes here at line 2 doesn't really affect the value of a. So we can run it. Let's take a look. All right, so the 20 is from line 3. It's 10 times 2, which is 20. And this 10 is from line 7, which is still the value of a. So what in this case, the caller, the variable passed to the function, is not affected by what's going on inside this function. Another example, func1. Again, with just one argument, but this time we assume the x can be accessed by the indexer, or accessed by using this square bracket. Now at line 13, we pass a list to func1. And then we modify the first item in the list to 100. Now this time, let's see whether A will be changed by func1 or not. So let's run it. All right, now you see the list A has changed. It was 358, but now the first element of A is 100 now. So this implies when you pass a list to func1, still x at the time you pass A to func1, x is assigned to A, meaning x points to the same list as A points to. And when you modify the x, the first item of x, because it's a list, it's a mutable. Mutable meaning changeable. A changeable object, it actually, what you modified inside the function affected was the value outside of the function that passed into it. So the difference between func1 and func0 is really the func0's argument x is an immutable type, a number, but for func1, it is a mutable type, a list. So depending on the type you passed into the function, the value passed into the function may be affected. So if you don't want the function to modify the value passed into it, what you can do is make a copy before you pass it into the function. So here we still have the list A equals to 358, and we call func1 as usual, but this time we use slicing to make a copy of A. So this, we call this creates a copy of A. It's a different version of A and pass it to X. So the modification done inside the func1 will be on this copy, not the original A. So let's run it. Now you say A is still 358. So this is important. If you don't want your function to modify the value passed into it, especially the value is a list type of value or mutable type, you can make a copy before you pass it into the function. We have seen functions with multiple arguments in previous lessons and homeworks. And we know we match the arguments by their positions. And this is the most commonly used way of matching arguments, and it's virtually the way most languages use. For instance, func2 with 3 arguments, x1, x2, x3, and when we call func2 at line 4 with 3, 1, 8, 3 arguments, and 3 is passed to x1, and 1 is passed to x2, and 8 is passed to x3. So the numbers are matched from left to right by their position. And in fact, if you miss one argument in func2, you would get an error. So let's run this example. Now you see the printout, x1 is 3, x2 is 1, and x3 is 8. So the arguments are matched by their position from left to right. Another way of matching arguments to functions is by the argument's name. At line 6, I still pass 3 arguments, but this time I specify which argument takes which value. So first one, x1 equals 3, x3 equals 1, x2 equals 8. So that means 3 is assigned to the variable x1 and 1 is assigned to variable x3 and 8 is assigned to the argument x2. So this way you don't really need to match the argument from left to right because they are matched by the keyword, by the variable name. So let's run it. x1 is 3 and x2 is 8. So it knows because we said x2 is 8 and then x3 is 1. Well, you can actually mix the arguments passing by position and the keyword or the function the argument's name. So for example, at line 8, I invoke this function first by passing a value directly. This should match to the first argument in this function, and the remaining arguments are matched by their name. So 1 is passed to x1, and 8 is passed to x3, and 3 is passed to x2. So if we run it, x1 is 1, x2, 3, x3, 8. Yeah, that's exactly what we passed. One catch here is though, when you mix matching arguments by position and keywords, you need to start by matching. You need to start matching by the position first, and then specify matching by the variable names. So if you have the name started first, and then you change it to matching by the position, you would get an error. We know if a function has 3 arguments, and when we invoke the function, typically you need to pass 3 values, 3 arguments for it. However, with a case like func3, when I specify x3 equals to 0, that means you don't have to supply the argument for the third parameter for func3. This is called a default value. Default value with a parameter with a default value. Now at line 4, when I invoke func3, I can only pass just 2 arguments to it. 2, 1, and 2 will be passed to x1 and 1 to x2 because I don't really specify the third argument, and x3 assumes the assumes 0. And important thing here is for arguments with a default value, they have to be defined after non-default arguments. So you cannot not have x2 having a default value and x3 does not have a default value. So let's run this example. Okay, you see x1 is 2, x2 is 1, and x3 assumes the default value with 0. Python also has a way of matching arbitrary number of arguments. The syntax is using this asterisk args. So what this really does is when you invoke a function func4, the first argument would be passed to x1 or matched to x1. The remaining will be matched to argument, will be matched to args as a tuple. So at line 7, when we call func4 with 4 arguments, the first argument string start will be passed to x1. And the remaining arguments 2, 3, 4 will be assembled as a tuple and passed to args. And at line 8, if we just supply 1 argument, start, which is a string, the start will be passed to x1. and nothing will be passed to args. So let's run it. All right, so for line 7, we pass 4 arguments to it. So the first one, x1, is a start. And then we iter through this args tuple, and we print each of them. You see it's 2, 3, 4. And also this end is a default argument for function print. And we match it by the keyword. So we want to append a space at each of the print. Another way of matching arbitrary arguments is using this double star args. That actually maps the arguments into a dictionary. So when you call it, you have to specify the arguments by name so that it knows it can be created as a dictionary. With the key is the variable name, and the value is the value for that argument. So if you run it, now this is a dictionary. All right, I just want to let you know there's another way of matching. We probably will not use this at this point, and we will be using this matching by tuple, the remaining arguments by tuple, like this, star args. Next, I'd like to talk about exceptions in Python. You can think exceptions as error. And when error occurs, what do you want to do? In Python, it provides this constructor try except to do just that. For instance, at line 3, if we have a statement print 100 divided by 0, obviously a number cannot be divided by 0. They must have an error there. In fact, Python will raise a zero division error. So if we want to deal with that type of error, we do this except following this try block. And we know 100 divided by 0 will raise a zero division error. Now, it's really up to us what we want to do in case of that error. Of course, here we just want to display it or print it. So if we run it, yep, it just simply prints the error message out. But in real application, if you indeed have a zero division error like this, you probably want to catch it and do something, or at least log it without crashing the program. Now you can actually have multiple catch blocks after this try block. So you still have your attempted statements or execution in the try block. And after that, you can have one or more except or catch block. But the important thing here is whenever you have multiple catch blocks here, you need to have your most specific exception dealt with first. Then you move on to the more general one. So here, zero division error is more specific than this general exception or generic exception. So you want to have this except generic exception at last. And this time, notice the argument here is really a number. I mean, the denominator is a string. You really cannot divide a string by 0. We don't have a definition for doing that. So it cannot be this zero division error. It must be some other error. So this should provide a catch-all place for catching any type of error. So if you run it, all right, you got unsupported operand types for string and int. So that's this type of error we get. And again, here we just print the error message. Now, the application of using try except is it provides a somewhat uniform way of deal with errors. Because think about if in the try block I have 100 lines of code, or maybe more than that. And also inside the try block you have functions nested within functions. If you want to deal with errors using a branching if-else, that would make the code much complicated. However, if you use try except, so you can simply throw or raise error from anywhere and deal with the error at a unified place. And in fact, this type of error handling is very common in virtually many mainstream programming languages. Although how to use it properly, there are some debates. We will not focus on this in our discussion today. What I want you to learn as minimum is to know how to raise an error inside a function, because we need to validate the arguments, the inputs to a function. For instance, this function compute sum, which takes a variable number of arguments, we know is matched to a tuple. However, if that argument has nothing in it, how do you compute the sum of those numbers? There's no number there. So in that case, from this function's point of view, it's an error. You can't proceed. So you can simply, at line 3, at the entry of the function, you check whether this argument has anything. If it doesn't have anything, you just raise an error. Arguments contain no elements. And then this way you can let the caller to deal with it, because it's the caller's responsibility of dealing with such error. And once you have this minimum validation and it passed, you can continue on to do your arithmetic. Because here this is a tuple, you can iterate through it, use this for loop. So you can have a local variable s initialized to 0, and then you keep adding the value from x to it, then you get the sum of it. All right. Now, if you call this function and pass it with 5 arguments, and remember this guy really takes some arbitrary number of arguments, you should be able to deal with this. And it would add 1, 2, 3, 4, 5. You run it. Yeah, exactly. It passed the very simple minimal validation, and it returned this summation of these 5 numbers. And if you call this function without any argument, you would get this error. Last, I'd like to show you Python assert statement. This can be very useful to validate your test cases. So assert could take 2 arguments. The first argument evaluates to a Boolean, and the second argument is optional. That basically means if the first argument evaluates false, what the error message should be. So here what I want to validate is compute sum with the 3 numbers. If this function is implemented correctly, then the sum of 1 to 3 should equal to 6. And then this assert should pass. So if we run it, yeah, there's nothing printed out. That means it's okay. It passed. Now, what if for some reason the function is not implemented correctly? Now, I commented this, so that means no matter how many numbers you pass into compute sum, it would always return 0. Certainly, it's not a good implementation. This function is faulty. Now, we still do this assert. This should fail. Let's run it. All right. Now you see we got an assertion error because compute sum 1 to 3 should be 6. Now this tells you there's something wrong with this function. Or maybe sometimes it's really your assertion is not designed properly. But in this case, it's really the function is not implemented correctly. We are not going to introduce new concepts into this lesson. We'll be doing more exercises with a focus on how to use computer programs, help us do some calculations or computations. The first example I have here is a function to compute geometric series. For example, here at line 23, I have a geometric series 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 until to infinity. So this is an infinite series. And we know there's a closed form of doing it. However, here we want to exercise how to use a program to add one term at a time until the sum reached to a certain precision defined by this epsilon. So this function has 3 arguments, with the last argument with the default value 0.01. The first argument is the first term of the geometric series, and the second argument, Q, is the common ratio. Once we know the first term and the ratio, we know all the rest of the terms. And all we need to do is to have a loop. For obvious reason, to add one term at a time until the sum reaches to the precision we need. And one thing here at line 4, we know if the ratio is greater than or equal to 1, the series won't converge, because we cannot have the term keep increasing for it to converge. Now, inside this while loop, the termination condition is to check whether the difference between the current result and the previous result is less than epsilon. The difference is really the sum between the sum with one extra term. So if the series already converges to the precision we need, we exit the loop. To begin with, we assign the first term to the result. Of course, at that time, the previous result is 0. And the previous term also is the first term. And the term added is 1. So at each iteration, we calculate the current term. The current term is really the previous term times the ratio. That's from the geometric series or sequence formula. And then you add it to the sum, to the result. Once you have it, now the previous term points to the current term, or the current term becomes the previous term, and we have one more term added. And then we check whether the difference is less than epsilon. If it is, we exit the loop. If it is not, the previous result becomes the current result. And then we go back to the loop and keep adding extra terms until the difference is less than epsilon. At the end of the loop, we return the result and also the terms used for that result. Now let's run it. Use this example. Here the first term 1 and the ratio 0.5, and we use the default precision epsilon 0.01. So let's run it. All right, see, the result from the function is a tuple. The first one is really the sum of the sequence of the series. It's 1.99. So it's already, the precision is up to 100th now. And only 8 terms is involved for that calculation. In other words, with only adding 8 terms, the series is pretty close to the actual value 2. The 2 is really the limit of that series. So 8 terms added is pretty good. Now if you want, you can change the precision or the epsilon to more, for example, to 1,000th. Now you run it. All right. See, the precision is up to 1,000th, and you need 11 terms to add that. Now we know the ratio does not have to be positive. So if I comment this one and run this, this is the same series basically, however, the ratio is a negative. So really, the series is 1 minus 1 over 2 plus 1 over 4 minus 1 over 8. And we know the limit of the series is 2 over 3. So the sign alternates. And let's see if our function covers that. So run it. Well, close. This is 2 over 3, and you have 15 terms. You only need to add 15 terms to reach to this precision. Let me explain this program one more time, step by step. We know a geometric series can be expressed as this: S equals to A0, which is the first term, plus the second term, A0 times Q, where Q is the common ratio. And you keep adding until A0 times Q to N. And we know if N approaches to positive limit, this becomes an infinite series, and that can converge to a certain number provided the common ratio is less than 1. Now for computer to calculate the series one term at a time, first we initialize this result variable to the first term. So that's this line. And at that time, the previous term also initialized to the first term. And the previous result is 0. We don't have any value for that yet. Now we enter the loop. The first thing we do is to get the current term, calculate the current term. The current term is really in the next term you want to add to the sum, add to the result. And by the property of the geometric sequence, we know the term is really the previous term times the ratio. So the second term is the first term times Q, and the third term is the second term times Q, so on and so forth. So the current term is the previous term in our program, A0 times the ratio. So the current term the first iteration is A0Q. And you get the current term, then you add it to the result, A0Q. Now the result has 2 terms added. Once you get the result calculated, you update the previous term with the current term, A0Q. Kind of you move on to the next term. So this is this line. Once that is done, you increment the counter that tracks the number of terms added. After that, of course, you do the comparison, see if the difference is less than the epsilon. If it is less than, we break the loop. If it is not, we do this. That is assign the result the result we have here to the previous result. Now this is A0 plus A0 Q. That's the first iteration. And then we go back to the top of the while loop. And we do the current term, calculate current term again. The current term is the previous term times Q. Now the previous term is this now. So the current term is previous term times Q, which is Q squared. And once you have that, you add it to the result. You add it to the result, then you update the previous term. You update this previous term to current term, which is A0 Q squared. And after that, you compare the result, this, with the previous result. So the result, the difference between this is just the extra term, the value of the extra term. If the extra term is less than the epsilon, we break the loop. Otherwise, the loop keeps going on. Our next example is about calculating the nth term of Fibonacci sequence. This famous sequence is almost used by any computer science data structure and algorithm textbook because it is a classic example of using recursion. However, we are not doing this in recursion. We just want to use a while loop to calculate the nth term, and we want to use this example to learn some Python programming techniques. Fibonacci sequence can be defined recursively. The nth term equals to the sum of previous two terms. For instance, I have the sequence printed out here. Starting from the third term, it is the sum of the first two terms. The first term is 0, the second term is 1, so the third term is 0 plus 1, which is 1. And the fourth term is 1 plus 1, so it is 2. And the fifth term is 3, which is the 1 plus 2. Now, the interesting fact about this sequence is as the terms moves on, the sequence goes on, the ratio between term n to term n minus 1 converges to golden ratio. Now, let's look into this function that computes Fibonacci sequence. This function has only one argument, and it assumes integer type. And first, at line 7 and 8, we validate if the input is less than or equal to 0. It must be a natural number. It doesn't make sense to calculate a negative term. And by definition, the first term is 0, and the second term is 1. So we assign 0 to fn underscore 1 and 1 to fn underscore 2. That represents the first and the second term. And also, if the caller asks for the first term or the second term, we just return directly. That's what line 14 and 17 does. Now, we only need to calculate the term when n is greater than or equal to 3. And in order to know nth term, we must know the previous two terms. For instance, if we want to know term f5, we must know f3 and f4. In order to know f4, we have to know f3 and f2. Now, for us to calculate the term up to n, we need to start by calculating the term f3, because we know f1 and f2 already. So we initialize at line 20 I to number 2. And the first iteration at line 22 calculates the third term. The third term is the sum of first term and the second term. That's what the first iteration does. After we calculated that term, we move on. We assign fn underscore 1 to fn underscore 2. And then we assign fn to fn underscore 1. So in other words, after the first iteration, fn underscore 2 points to term 2, and fn underscore 1 points to term 3. That way, we are able to calculate the next term, the fourth term. So that's the mechanism of this loop. Every iteration, we calculate the current term based on the previous two terms. Once we have the current term, we move on the previous two terms reference so that we can calculate the next term until we calculated the nth term. Now line 29 to 31 is our test. We want to print the first 15 terms of a Fibonacci sequence, and this is the output. Our third example is a function that tests whether a number is prime or not. If it is a prime number, it returns true, otherwise it returns false. And we know a prime number has no factors other than 1 and itself. And a prime number cannot be even number unless it is 2. So first we do some quick check. At line 4, if number is less than 2, it cannot be a prime number. And if number equals to 2, it is a prime number. Next, at line 10, we test whether this number is an even number because we already tested at line 7 whether it's 2. So when the program reaches to line 10, it can be number 2. The number cannot be 2. So we can test whether the number is an even number. If it is even number, then we know it can be a prime number. It is a number it's an even number greater than 2. And we return false directly at line 12. This gives us a quick way to cut half of the possibilities. Next, from line 14 up to line 24, this is the key implementation of using trial division to find whether a number is prime. The basic idea is we start from a factor 3 and we'll try if it divides the number. We don't have to start the factor from 2. We know all the prime numbers must be odd. We don't need to test whether that number can be divided by 2. We already tested that. So we start the trial factor from 3. And also we don't need to test the divisor from 3 all the way to the given input number. We only need to test up to half of it. Line 17 starts the loop, and line 18 is pretty straightforward. We just test whether this factor divides the number. If the factor divides the number, we know the number has a factor of that trial factor. So we return false because it is not a prime number. Otherwise, line 22, we add 2 to trial factor. So we skip one number. We don't need to test whether this number can be divided by an even number. So keep running the loop. If there's nothing up to the trial upper bound, divides the number at line 24, returns true, meaning it is a prime number. Now this is our test case following. We want to test a few small numbers. We know they are prime numbers or they are not prime numbers. So we use assert to test that. And here, line 34, we test a pretty big number. And this, in fact, is a prime number. So let's run it, see what happens. Run it. All right. It knows 4 has a factor 2, and 8 has factor 2, 9 has factor 3. And what about this pretty big number? Well, in fact, it is true. It took the program about 1 second to find out it is a prime number. If you are interested, you can Google it. This number is indeed a prime number. All right, our last example. And this time, we're using Python to do some statistics. Line 1, we import a random module. And line 3, we assign an empty list to variable examples. Line 4, 5, we populate the examples with 15 floating point numbers from a normal distribution. A normal distribution is a bell-shaped distribution, and we give the distribution mean 85 and a standard deviation of 5. And this could represent a test score of a certain subject for a class of students, and the average score is 85, and the standard deviation is 5 points. In other words, most of the students' test scores would fall in the range of 70 to 100. That's not too bad. And line 7, we calculate the sample mean. The sample mean is the sum of the values, the samples, and divided by the number of samples. Line 8, we print the sample mean. Next, we want to calculate the sample variance. The sample variance, to calculate the sample variance, we need to loop through each sample in the samples and do this. This is a direct translation of calculating a variance. The variance is a measure of how far each sample deviates from the sample mean. Of course, we need to raise it to the square to get the absolute value. And then at last, we take the square root of the sample variance. That gives us the standard deviation. Now let's run this program. Okay, so we got sample mean 87 and a standard deviation 4.7. Let's run it again. Now this time it's a different number because we are using random. Each time we run the program, the numbers from random.gas give us a different value. However, the value follows the distribution with mean 85 and a standard deviation of 5. Now, if you don't know the basics of statistics, it's fine. And this is just an illustration how the program can be used to do certain simulations and how the program can translate the mathematics. And a lot of cases, the translation is pretty direct and straightforward. I'd like to introduce modules concept in Python. Python module is simply a file. You can think about the module is a self-contained program which provides certain functionality. And a software can be made of one or many modules which work collaboratively. It is very hard to imagine software nowadays is written in just one big giant monolithic file. Now let's take a look at one example. Suppose we have a function called findMedian, which takes one argument. This argument is a list. To find the median in this array, a list-based array, first we want to make a copy at line 3 because we don't want to modify the input. And then we sort it from small to big. And we know the median number depends on the number of elements in the array. So if the number of elements is even, then the median is simply the average of the two middle numbers in the array. Otherwise, it's just the middle number. For instance, if we have an array like this, A, which has 8 elements, after sorting it, it's this, and the median of this array should be the average of 3 and 4. So let's run it. All right, so the median is 3.5. And also we print the original array here just to show, okay, this function indeed did not change the input argument. Now the next question is, what if there are other programs also want to use this function? Other programs also need this feature findMedian. One way is straightforward, it's just copy and paste, and this is a very short program after all. However, that's not very desirable. A good way of doing it is simply package this function in a separate file. For example, I have a file here, statistic helper. I copy the entire implementation into this. Of course, I added only one line just for demonstration purpose. And to use this function in the program, all we need to do is call import statistics helper. I'm sure we have seen this import statement before. And here we import just one file, one module. And to use it, we cannot just call this function directly now. We need to prefix this function with this module name, statistics helper dot findMedian. And this module also serves as a namespace purpose. There are other ways of importing, but here let's keep it simple. And today's lesson, we're just going to cover the basics. This is the preferred way of importing a module, in my opinion. So now you say, in the demo file, which we want to reuse on this findMedian, we simply import the module, and we can reuse it. We don't have to copy the entire code here. Now let's run it first, see if it works. First, let's clear the results from the previous run and run it. All right. You see, this is the debugging message from this statistic helper file. That just tells us, indeed, this function is invoked from that file. The same result, and the same, we did not modify the original input. Now you see the beauty of having certain functionality encapsulated in a module, such that you can reuse it in other places. You can test this module before you ship it to other users. Now, how about we do one more test, and this time we append one extra number, then we find it again. Now we append one more number, this list becomes, this list has odd number of elements in it. So this find medium is supposed to return the middle one. So run it. 4. Now we know how to write your own module and use it in other places. And one thing here, I have this module file at the same level with this demo file. This is not necessary. As long as in demo, when you import it, it knows where to find your module file, it shall be fine. But here, when this file is at the same location, the same directory as this demo, that's the first thing Python searches for. Regardless where you have your module file stored, so long the main file knows where to import it, it's the same way of using it. Next, I'd like to introduce two great Python libraries. One is called NumPy, another is Matplotlib. These two Python packages are great for scientific computing and visualization. Now, to install these two packages, you can do it in PyCharm terminal and type in pip install matplotlib. Matplotlib actually installs NumPy as dependency. In other words, if you install matplotlib, you will have NumPy. Now, as we said before, in order to use a module, we have to import. Now, this time when we import NumPy, the difference is a package. We are importing a package. A package contains a set of modules, many Python files. When we import NumPy like this, meaning import NumPy as NP, NP becomes an alias for NumPy. So to use it, we first import it, and let's say some very basic use of NumPy. And here, I'd like to just cover very basics and pretty much just use the array from NumPy, which is more efficient than Python list. So first, let's see how do we create a NumPy array from Python. Line 4, we can initialize array from a Python list. In fact, this list is empty, so the array, NumPy array is empty. The next way of initializing a Python array is called np.zeros by supplying the size of the array. So if we call np.03, we create one-dimensional array with 3 elements in it. Now, if we want to specify the type, we can do something like this. At line 9, np05, this time is a one-dimensional array with 5 elements, but this time the type we want it to be integer instead of the default floating type. Let's run it. NumPy demo. Okay, so this is from line 7. It prints that floating point array, 3 elements. And this is from line 10. So this array has 5 integer numbers in it. There are many functions features from NumPy library. Here, I like to just cover the basic way of using NumPy. One thing is how to populate a NumPy array, because we want to use it for plotting curves using Matplotlib. So let's comment this out. We don't need this anymore, and paste this here. So here at line 13, we define a variable number of points, 20, and we want to use NumPy linspace function to populate an array. The first argument, -3, is the start point, and then second argument 3 is the end point, and the number of points, basically we use linspace to create the number of points evenly spaced between this start and end points. So if we do this, np.linspace minus 3 to 3 number of points, it would create 20 points evenly distributed from minus 3 to 3. And next, what we want to do is, supposing this is suppose this is the independent variable, and we want to pass this to func and to get dependent variables. How do we do it? So we create the Y array, which has the same size as X array. We use the for loop to call this function 20 times and populate this dependent variable array. Okay, let's run it. All right, this output is a little bit big. So first of all, we have 20 numbers floating points array. That's the X array. So that's the output from line 15. And next output this is this Y array, which is X array squared. You can use NumPy to do many things, including some linear algebra. You can manipulate metrics such as transpose, multiplication, and calculating matrix determinant, inverse. But here, I just want to show you one example of using NumPy to solve linear equations. Let's comment this out. Copy this here. Suppose I have this linear equations. How do we use NumPy to solve it? First, we can create the coefficients array np.array from Python lists. Like I said at the beginning of this class, you can basically use Python list within list to represent two-dimensional array, and np.array can recognize this as a two-dimensional array. So this way we can create a two-dimensional array from Python list. So this would be our coefficient array. And next we create the array H, array 5, 6. Well, that's actually the right-hand side of the equation. Now, how to solve it? We simply call np.linealg, linear algebra, solve AH. Then the X would be our solution. It's so interesting. You don't have to do all the hand calculation. Run it. All right, now you get the solution. If you want, you can verify X is 1, Y is 1, 3 plus 2, 5. X1, Y1, 2 plus 4, 6. Of course, this is a very simple example. I'm sure if you have a big, complicated equations, you can solve the same way. Again, to find more uses from NumPy, you should go to numpy.org to look at documentations. Next, let's see how to use matplotlib to plot some interesting curves. First, we need to import those required libraries. NumPy, we need that to create the dependent variables array and independent variables array. And second, we want to import the pyplot module from matplotlib. As I said, matplotlib is a package that can contain many modules, and pyplot is one of those many modules from matplotlib. And as above, we give pyplot module, and alias. We call it plot. The functions we want to draw are polynomials. The first one is func. It takes only one argument. That's the x. It returns 3 times x squared. And the next one, func2, is 3 times x cubed. So these are two polynomials. And the first one with the degree 2, the second one with the degree 3. Now let's see, how do we plot it? Actually, the comment is not accurate here. It's 50. And we want to draw from -2 to +2. So here we want to generate 50 points evenly distributed from -2 to 2. This would be the points on our x-axis. Line 14, we allocate 15 points to y array. We, of course, zeros all of them. The same thing with y array 2. The y array and y array 2 will store the dependent variables from a func and a func2 respectively. Like I showed you before, we use for loop to compute the number of points times for each of the function. So the func1 we call from -2 to whatever, the numbers generated from line space. The same thing with func2, and we assign that to this dependent variables array. At end of line 18, or after the for loop finishes, we would have all those dependent variables calculated. So the calculation is done. The next part is using the plot to visualize the data. The title is the graph's title. We give it a label. We want to show the grade. Now we want to plot two curves. The points, the first argument is the points on x-axis. And the next argument, the second argument, is the corresponding y points. So the same thing for the next curve. Now this is the legend. The last, we want to show the graph. It's very simple. And let's run this demo. All right, now you see we have two curves. The title, polynomials, and these are the legends. And we know we want to plot from -2 to +2. So the number of points are automatically calculated. And we will also want to show the grade. It's simple and straightforward, and these curves, they plotted pretty nicely. Now we have seen how to use matplotlib to plot curves. What about another type of graphs? For instance, bar chart. And of course, matplotlib can do that. So here, I want to plot a bar chart with 5 bars at position 1, 2, 3, 4, 5. And what I want to print out, what I want to plot is, at those positions, I want to plot the counts. This bar chart I gave here is just for illustration purpose. You can use this for a template to plot other type, to plot bar chart with other data. So here I define 5 positions. That will be the positions for 5 bars. And for each bar, I have the counts. 10, 20, 30, 15, 8. Well, you can think about maybe this 10 is for the counts for this letter A. Maybe A appeared in a certain paragraph or phrase 10 times, or E appeared 20 times. Bar width plot.bar, the first argument, that's the position you want to draw the bar. And for each bar, the height, the counts. And you want to override the width with bar width 0.3. Now this is the label below each bar, because we don't want to use the default label for it. We want to use the label from the characters. Next, we also want to label the bar chart at each bar, at the top of each bar. So let's run it, see what it does. Okay, you see, this is a very nice bar chart. A, E, I, O, U. A counts 10, E counts 20, I 30, O 15, U 8. Again, this is another example of using pyplot to plot a different type of a graph. There are many other features, functions available from matplotlib. This just scratched the surface of it. The point is, whenever you think you need certain functions, you first probably want to look for, you first probably want to find out if there are available implementation. I have an array that stores a list of numbers, and all the numbers in the array are ordered from smallest to the largest. That is, this array is ordered ascendingly. Now, one question to ask is how to find a number from this array. Now, I want to point out finding a number is not much of use by itself. You have to think about each of the numbers as a key, and the key has association with a certain piece of information that may be more important or more useful. By finding the key, you are retrieving that associated information. For example, each of the key could be a person's ID, and by finding the ID, you can retrieve the associated person's information. Now suppose we want to find the key 12. How do we do it? One way is very intuitive and straightforward. We need to have a loop that iterates through this array from the left to the right until we find it or not. So the first iteration, we would compare the key to the first element. If they're equal, we are done. If not, we move on, and we keep moving on, and we keep comparing to the next element until we find it. So 5 iterations, we find the key. Now, what if we have another key to search, 9? Still the same. We start from the left, compare the key to the first element, not equal, we move on to the next element, not equal, then the next element, still not equal, then keep going until the last element, well, still not equal. So we made total 8 comparisons, and we know there's nothing equal to the given key 9, so we know 9 does not exist in this array. Now, one thing you should notice is for searching the key 9, once we pass comparing element 10, there's no need to compare this range anymore, because all the numbers after 10 are greater than 10 because they are ordered from smallest to the largest. So if 9 is less than, if the key is less than 10, you really don't need to compare the range beyond 10. And similarly for 12, comparing the key 12, you probably can try to compare a number not starting from the very first element. For example, you may want to start from index 2 when comparing a given key. So if the key is less than the element, for example 8 here, so we only need to compare this subarray that is left to the element 8. If the key is greater than 8, we can compare the subarray that is right to number 8. So in other words, we compare a number not starting from the first, we can shorten the search range. One systematic way of finding a key from an ordered array is by comparing the key to the middle element of the search array. So it is an iterative type of algorithm. So the first iteration, obviously, we need to search the entire array. The search range is the entire array, of course. Like I said, we pick the middle element to compare. So the first iteration, we would pick, in this case, element 10 to compare to the key 12. And we know 12 is greater than 10. The range, the subarray from 0, 1, 2, all the way to 3 cannot possibly contain the key. So the key must exist to the right of the mid element. Now we move on to the next iteration. We shorten the search range by half. The range is start from index 4 to the rightmost index 7. Now the search repeats itself. Again, we pick the middle number, we pick the middle element of this subarray. So this time, the middle element is this. It's 13. And 12 is less than 13. So in other words, the array that is right to the middle element, that is this range, cannot possibly contain the number 12. They are all greater than 13, and 13 is greater than the key, so we can drop the right subarray for comparison for the next search iteration. So we move on to the next iteration, and this time the search range is on the left of the previous middle element. And in fact, because we know this is greater than that, this range is reduced to just one number, 12. And you see only 3 comparison we can find the key. All right, let's find another number, this time 14. The first iteration, the left index starts from the left of the whole array, and the right index points to the very right index of the entire array. That's our first search range that covers the entire elements in the array. And the middle number, middle element, points to index 3. And then we compare 14 to 10, and 14 is greater than 10. So we can safely drop the subarray left to the middle element M. We don't need to compare any elements here to the search key. We know the search key must exist, if it exists, must be in the subarray that is right to the middle element. And the next iteration, we would move the L, the left index, 1 position to the right of the middle element. and that gives us the new search range. The search range is reduced by half from the previous one. And the iteration is again to find the middle element, which is index 5 now. Now 14 compared to 13 is still greater than the key. So we keep moving the search range and reducing the search range. The search range now reduced by half again. It started with 8 elements and then reduced by half to 4 elements, and now it is only 2 elements we need to compare to search from. And 14 compare this new middle element, 14 compared to 15, that is less than 15, and we know it must, if it exists, must be in the subarray that is left to the M, and we want to update the right element and move it 1 position left to L. However, at this time, it is not a valid search range. We can conclude this key does not exist in this array. So we only did 3 comparisons, and we detected this number does not in this array. It is much quicker and efficient than you scan the whole array from the very beginning to the end to find whether the number exists or not. This binary search is a very efficient algorithm. It scales very well. Suppose we have 10 to the 6, that's a million keys to search from. At each iteration, we reduce the range, the search range by half. At worst case, that means we keep reducing the search range by half at each iteration until the search range is shrunk to only 2 elements in it. We only need to do log base 2 of a million number of times. That's about 20. That is, we only need to compare at the most 20 times out of a million numbers to find the key or not. And of course, the keys must be ordered for this algorithm to work. Once we know the theory of binary search, it's pretty straightforward for us to write a Python program that implements this search algorithm. The function binary search takes 2 arguments. The first argument A is an array. The second one is the key to search from the array. And the first, at line 2, we do very simple validation of the argument. If the array length is 0, we just return -1. -1 means the key does not exist. So the function actually returns the index of the key. We know for Python array, well, list-based array or array from NumPy, the index starts at 0 and all the way to the length -1. We return the index of the key if the key exists in the array. Otherwise, we return -1. The input argument array A must be ordered. However, that's not the responsibility of this function itself. The caller needs to make sure the array is ordered ascendingly before passing it to this function. Line 5, 6, 7 initialize the left index, right index, and the middle index. That's what we explained in the previous slides. So at the very beginning, or the first iteration, the left index is the leftmost element. The right index points to the rightmost elements. We can just give the mid index the first one. Next is our loop. The condition for the loop is as long as the left index is less than or equal to the right index, we can continue. And at each iteration, like we said before, we find the middle element in the search subarray. The search subarray is defined by the left index and the right index, and the mid index is really the floor division of left index plus the right index. That gives you the middle index of the search subarray. Once you get this middle index, you do the comparison. You compare the element at the middle of the subarray to the key. If they are equal, you're lucky. You just return the mid index right away, and you found it. Otherwise, you compare whether the key is less than the middle element or the key is greater than the middle element. If the key is less than the middle element, that means the next search subarray should be on the left of the middle element. You want to move the right endpoint to the left of the middle index. That's why you need to do this mid index minus 1 and assign it to right index. That moves the right index to the left if the key is greater than the middle element. That means the next search subarray should be on the right of the middle element. For that to happen, you need to move the left index to the right, just beyond the middle index. So you do this, mid index plus 1. And then you go back to the loop, and you compare the left index to the right index again. If the left index is still less than or equal to the right index, that means you still have a valid search subarray, and you continue. If not, that comes to the else part. The else part means this while condition is false. That is when you move the left index beyond the right index, and you still couldn't find the key. So you return minus 1. That tells you the key does not exist in this array. If the key is not in the list, and when this routine returns at the line 19, the left index would be greater than the right index. Next, let's design some test cases to test our binary search function. We have this keys array. That's the keys we used in our previous explanation. Now we want to test a key exists in the array and the key not exist in the array. So first we test a number 3, and this function should return the index of that key. For the element 3, the index is 0. And for element 8, the index shall be 2. And 15, the index is 6, and so on. And also we want to test one element that does not exist in this array. For example, number 9. Number 9 does not exist in this array. And number 2 is less than the smallest element in this array. It still does not exist in the array. It should still return minus 1. So this should give us reasonable good coverage of our binary search. And let's run it. Because we're using assert here, if there's an error, we would see some error here. We don't see any error here. That means all the tests pass. Let's work on a problem where we can use binary search. Suppose we have a water container. This water container has a very odd shape. We don't know exactly the volume at a given height. That is, we don't have a closed formula to describe the volume of height. However, we can measure the volume manually at a given height. And we choose a set of heights strategically from a height somewhere close to the bottom of the container to some height close to the top of the container. And we record the volume at each certain height. For example, here we measure the volume at height 1, 2, 3, 4, 5, 6, 7. At height 4, we got volume 3.5. At height 5, we got volume 4.1. We shall not worry about the units here. Now, if you want to know the volume at height 4, since we have measured volume for it, we can just retrieve it. That is 3.5. And if we want to know the volume at height 5, we know the measured volume of it is 4.1. We can just get it directly. But then the question is, what if we have a height 4.7? We want to know the corresponding volume at that height. One way of doing that is called linear interpolation. It assumes the volume at a height between this measured two heights, 4 and 5, lies in the line segment defined by those two measured points. So 4.7 must be somewhere on this line. And all we need to know is to calculate the slope, which we can get from these two endpoints we already measured. We get the slope, and then we know the distance from 4.7 to the h at the left endpoint, and then we can get the offset. The offset is the volume at 4.7 to the volume at height 4. And we know for line segment or line x1, y1, x2, y2, suppose there are 2 points on this line, the slope is very simple, y2 minus y1 divided by x2 minus x1. So that is a slope. So when we plug into this, we know the slope is 4.1 minus 3.5 divided by 5 minus 4. That is the slope of this line. And this distance is 4.7. That's the height. We want to find the volume. And 4.7 minus 4. Minus 4, that gives us this distance. And times this slope, that gives us this volume offset to this position. And this is volume 3.5. So we plus 3.5, then we know the volume at 4.7. So this is called linear interpolation. Any points can be calculated this way so long we know that point falls into which interval. Now, one question we need to answer is, what if the point is beyond the two ends? For example, if a point is somewhere here, is the height is after 7, is higher than the height, we have the measurement. So we can use the slope of this interval. And for a point less than the smallest height we have the measurement, we use the interval of this. Now for a given height, we need to find the interval that covers it. So if a height falls in between 1 and 7, that's straightforward. We need to find the left endpoint of the interval that covers it. So if we want to calculate the volume of a height in between 2 and 3, we get this index, this interval, the left endpoint of this interval, 2 and 3. if the height is in between 3 and 4, anywhere in between 3 and 4, we get the left endpoint of interval 3 and 4. For points for height beyond the largest height, we actually get the second to the largest height as the left end index, left end point. And again, for any height less than the smallest, we use the first index, the first h position or height position for calculating this volume. This actually would work. So for this point, it would be the extension on this line, and for this point, it will be extension of this line. Next, let's take a look at how we do that in Python. We define a function called linear interpolate. This function takes 3 arguments. The first 2 are arrays, and the first argument is the independent variables array. And the second argument, y, is the dependent variables array. And the third argument is a number. And we need to make sure when we pass in this argument, the x is sorted ascendingly. That's the responsibility of the caller, and we don't need to sort inside interpolate method. However, if you do want to do it, you need to make sure when you sort x, you also need to sort y accordingly. Now, the first thing inside the function is to validate the input arguments. We need to validate, at least we have 2 points. So this is this. If we don't have 2 points, we cannot do linear interpolation. We need at least 2 points to define a line. And also we want to make sure the length of these 2 arrays are equal. For each independent variable x, there is a corresponding y. If we pass the arguments validation, we go to the next statement here, find the left endpoint of interval for px. So what this means is, like we described before, suppose px falls into interval defined by this idx and idx plus 1. So this function returns the idx, the interval's left endpoint. Once we know this interval that covers this to be interpolated position, we can get the slope for the line defined by these 2 known points. And once we have that, we can calculate the offset from this to this. That is the formula. So we have these 2 points. We can get the slope of it. Let me write down the coordinates of this. For this, the coordinate would be x at idx plus 1 and y idx plus 1. These values are known. They are from the input array. And for the left endpoint, the coordinate is x idx and y idx. So the slope is direct translation. We just plug in these coordinates, y idx plus 1 minus y idx divided by x idx plus 1 minus x idx. And the interpolated value is this. And that is the slope times this distance. This distance is really the px, because this point is px minus this times the slope, and then plus the y value at this, you get this interpolated value. Once we get it, we return it. And also keep in mind, once we know the interval for this, it would work when the px is at this end or at this end. I mean, at the extension of this line segment, it works the same way. The left endpoint index function is a slight modification of the binary search function we saw before. Two arguments are the same. A, the first argument is an array, and the key is the number or the key we want to search from the array. And a simple validation, if the length of the array is less than 2, we throw an exception. I know we validated the arguments at the outer function interpolate, but for this function itself, it's still worth to test the length of the array. This is sometimes called a defensive programming. Now, the difference between this left endpoint index function and the other binary search function is we are not just want to know whether the key exists or not in the array. We also want to know if we don't find the key, what is the index that ended the search. So in other words, we want to return the interval or the left, we want to return the interval's left index that closest to the key. What I meant by that is, suppose we have a list of points in the input array A. Now, if we find the key, we find one, we can just return the index of this. This would be the interval's left endpoint with a catch, because if the key equals to the last one, we actually want to return the index left to it. That is what this does. Index -1, decrement by 1. Another is if the key is outside of the range of this array, meaning the key is somewhere here or somewhere here, we treat it similarly. If the key is greater than the largest element in this array, we still return the second largest index in this array. And if the key is smaller than the smallest number here, we return the index 0 to calculate. Like we explained before, this interval would work for points left to it. The left point is just still on the extension of the line defined by this segment. Similarly for this. Now, if the key falls here, meaning if we don't have a direct match for the key, so the key is somewhere between a certain interval, and at the end of the search, that is, we don't find the key, we will not have a direct match here. So the mid-index, that's the left, that's the index, it ended the search, would be either here or here. And if the mid-index points to here, we are done. So we get the interval's left endpoint for the key, so we can use that to do the interpolation. But if the mid-index is here, so the key is less than the last search position, we need to move the index back by 1 position. That is the interval's left end index. So that is still the mid-index here -1. At last, we also want to make sure we get a valid index at least 0. That is because if the key happens to be here, we -1, we get a minus index. That's an invalid index. So we need to bring it back to 0. Now the rest of the program are very similar. Here we do the same initialization, almost no change, and the same loop condition. So long left index is less than or equal to right index, we have a valid search range. We can keep searching. We compare the key to the mid index. No change. Now, because we are not only interested a direct match, we don't want to return right away if we find a match. So if we find the key, we just break the loop. We break the loop. We go here. We check where the key is. So if the key is less than the mid index, we do this. We bring the index one position to the left. That's that's when this equals to this, and it goes here and do this adjustment. And also we can terminate the loop when left index is equal to right index. So we can terminate that a little earlier. So that is when the search range is reduced to one element. No need to do the next if-else check. So we still go here, go outside of the while loop. We do this if check. If the key is less than that, we decrement the mid index, and this is when the mid index is with the mid index points to the last position. So we know we need to move the mid index left by one position. We need to use this, the second largest index for the interval's left endpoint. Now, if we find a key or we already end our search, when the search range is just one element, we break the loop. Otherwise, we keep going. So we don't find the key, but we still haven't reduced the search range to just one element. We do this block. This block is no change from the binary search. If the key is less than the mid element, we move the right index to the one element left to the mid index. If key is greater than the middle element in that search range, we move the left index one position right to the middle index, meaning we search the right subarray of the middle element. We need to design our test cases to cover the boundary conditions and all possible execution path. So if I have the x value 1, 2, 3, 4, 5, 6, 7, you can think about it as the height for that water container I used as example, and the corresponding volume array. Now the test case should be designed like this. We should test, interpolate at the points we have already we have known value. For 1, at height 1, we should have a direct value recorded, 0.5. So we assert this height volume at height 1, it's 0.5. Similarly, at height 7, the volume is 8.75. That is this volume. Now, if I have a height 1.5, that's in between 1 and 2. Now, the volume should be in the range of 0.5 and 1.25. So that's this validation. And for volume, for example, 9, that is out of the range. That is greater than the largest height. For height 9, that is larger than the largest height we have known. We have the measured volume. All we know is the volume should be greater than the last one. So this is what we can validate. If you are interested, you can also validate volume. You can also validate a height that is less than 1. This linear interpolation will give you any value you plug in. Whether it makes physical sense, you have to make your own judgment. Many modern programming languages support recursive function calls. A recursive function is a function that calls itself. For example, I defined a function factorial recursive, which takes one argument. And inside the function, the last statement, the return statement, it calls factorial recursive again. And this method and this factorial recursive is exactly the same as the above defined. When you call it again, you adjust the argument, you subtract 1 by the argument, then you call the function again. This recursive function resembles the mathematical definition of n factorial very closely. We know n factorial equals n times n minus 1 parentheses times n minus 2 and all the way to n to 2 times 1. Now, in fact, this terms is n minus 1 factorial. In other words, n factorial equals n times n minus 1 factorial. Now you say n factorial is somewhat defined recursively. It is equivalent to n times n minus 1 factorial. To know the n factorial, we need to know n minus 1 factorial. And if we say n factorial is the product of all the natural numbers from n to 1, then it must be true n minus 1 factorial is the product of all the numbers from n minus 1 to 1. Now, in the last return statement in this function, this is almost the same as this mathematical term, n factorial equals n times n minus 1 factorial. Let's see how this recursive function actually works. Supposing we are doing 4 factorial, f4. Well, I just use f to for this longer factorial recursive function name. So the first time we call factorial recursive 4, we basically pass 4 to n, and we do certain arguments validation. That's the first if block. Second if block checks if n equals to 1. If n is 1, we return 1, and we know 1 factorial is 1. This is intuitive, and this is called base condition. So if we don't have this, the whole recursive would not work. You cannot have a recursive function without finally return something, not just the call itself. Otherwise, you end up in an infinite loop. Now, the first time we pass 4 to the argument n, and we pass the 2 if blocks because n is not equal to 1, then we come to the return statement. The return statement is 4 times factorial recursive 4 minus 1, 3. So it doesn't return immediately because we are calling this exact function again. That means it goes back to the function, but with the parameter 3 this time. And 3 would come to the last return statement again. That becomes 3 times factorial recursive 3 minus 1, that is 2. And then this becomes 2 times factorial recursive 2 minus 1, that is 1. Now when 1 comes into this function, it goes to this basic condition, and n is 1, and then this one returns 1. So 2 times 1 is 2. Meaning when we finally meet the base condition, f1 returns, and 2 times f1 returns to another function, 2, and 3 times 2 returns to f3, that is 6. 4 times 6, that's 24. It returns this f4. When you call factorial recursive f4, it doesn't return immediately. It would continue on to call 4 times f3, which doesn't return. It would continue to call 3 times f2, then 2 to f1. Return one by one. The function returns one by one. f1 returns, you get f2. The f2 times 3, you get the return of f3. Once you have f3, you can do 4 times f3, that returns f4. The key to remember here is when you invoke this function factorial recursive, first time you pass the argument 4, it doesn't return immediately. It breaks the function into two parts. One is the constant 4, another is the same function call with the argument one number less than the caller. And that is the definition of this. It keeps going until the last call when the argument reduced to just 1. It must be 1 for us to return here. All the previous calls, the argument n are greater than 1. The last one must be 1, and we return 1. This is very important. Without this, you would end up keep calling the same function again and again, and in the end, this would blow up the program. This is referred as stack overflow. Let's run this factorial recursive function in PyCharm. I added a few print statements in this function to help us understand recursion. Right enter into this function, we print call factorial recursive. And this is a nice way of formatting a string. You use f and a single quote, whatever string you want, but you use this paired curly braces to include the variable. And this variable n will be replaced by whatever value passed to n. And there are two places we return from the function. One place is at line 8 when we hit the base condition. When n equals 1, we return 1, and we print this return factorial recursive before we return. Another place is the last return statement. Before that, we print return factorial recursive. And whenever we invoke a function like this, the n becomes local variable to that invocation. So this call factorial recursive and this return should be paired. We should say a pair of that for each invocation. Now let's run this function. All right. First of all, the result is 24. 4 factorial is 24. The result is correct. Second, let's look at the calls. First call is factorial recursive 4. That's our initial invocation at here. But it doesn't return immediately, like I explained. It keeps calling the same function with a different argument, with a different number passed into the argument. That's because we subtract 1 and then pass to the next recursive call. until we hit this base condition, which is n is 1. And then we return one by one until we return the initial function invocation. And this is the call stack. This is the original, the oldest call, and this call is the latest call. As you can see, if we don't have a base condition or termination condition for the recursion to end, to return something concrete, you would end up with this call step keep growing until it hits the memory limit or the stack limit of a program. That is the stack overflow. Second recursive function example. We know Fibonacci sequence can be defined recursively. Starting from the third term, the nth term of Fibonacci sequence can be defined like this: Fn equals to Fn minus 1 plus Fn minus 2 for n greater than or equal to 3. And n is the nth term of a Fibonacci sequence. It is the sum of the previous two terms. And the sequence goes like this: 1, 0, 0. 0 is the first term. The 1 is the second term. The third term is 1. It is 0 plus 1. And the fourth term is the sum of the previous two terms. And 5, something like this. We have used the loop to compute the nth term of a Fibonacci sequence. But let's take a look at how we do it recursively. And this is a nice format for us to use in a recursive function, almost like how we did with n factorial recursive function. To compute the nth term of Fibonacci sequence, we actually recursively compute n minus 1 and n minus 2 terms of Fibonacci sequence. So that is this. So Fn, that's the nth term of Fibonacci sequence, equals n, the previous two terms, the sum of the previous two terms. As usual, for the recursion to work, we need to have the base condition. And we know the first term is 0, and the second term is 1. And the recursion is only applicable when it starts from the third term. So we need to set the base condition for it. If n is 1, we return 0. If n is 2, the second term, we return 1. Once we know the first term and the second term, we establish the base condition. Contrast to the n factorial recursive function, inside this compute Fibonacci recursive function, we recursive on two calls at this line. So for the nth term, we actually invoke two exact compute Fibonacci recursive. So how does this work? If we want to compute the fourth term of Fibonacci sequence, the first time when we call it, we pass 4 to it, 4 to this n. And it comes to this line because 4 is not one of the base conditions. So it goes on to this line and continues on to the recursion, which is F3 and F2. I write it this way is for you to realize when you call when you call compute Fibonacci recursive with argument for, it actually needs to invoke two functions, but it can only invoke one at a time. The first is the left recursion, which is 3. After 3, it would invoke f2. That is this. But it won't invoke this until this returns. So this would keep going. So f3 is invoked, and f3 would come to this beginning of the function again. That's 3. It's not one of the base conditions, and it keeps doing the recursion. That's f2 and f1. So the program remembers for Fibonacci 3, it actually needs to invoke two exact functions. One is f2, another is f1. And f2 would be invoked first. And f2 and the argument 2 passed to this again. And 2 is the second term, and we know the case for it, it should return 1. So the first return is f2. Okay, and I have this the same debugging print statements here. So the first, really, you would say return f2. Once this returns, the program knows there's another function needs to be called. That's the f1. f1 returns, and when both of them returns, it returns f3. Once this is returned, now it invokes f2. f2 still is the second term. That's the base case. There's a base condition for it. So it returns f2. Now let me label the returning call in order. So the first is this. We call f2. Well, we return f2, and then we return f1. We have this. Now we return f3. And after that, we return f2. After f2, now we are able to return 4, which is the fourth term of Fibonacci sequence. Let's run this computer Fibonacci recursive function in PyCharm. Run it. We are doing the fourth term of this sequence. It's 0, 1, 1, 2. So the fourth term of it is 2, correct? And if you're interested, you can verify the call stack, what I showed you before. So first, the initial invocation is 4, and it keeps doing the invocation, the recursion. The first recursion return occurs at here, return 2, and then return 1, then return 3, and then return 2, finally return 4. You can compute a slightly bigger Fibonacci sequence, a slightly bigger term of Fibonacci sequence recursively. You can see a more complicated call stacks. However, none of this recursion implementation of factorial or Fibonacci sequence computation is efficient. Let's do some performance tests about this recursive version of compute Fibonacci sequence. We want to find out the 30th term of it, and let's run it. It's less than a second. It's about 1/3 of a second. And what about 32? Run it again. Now it's close to a second. 35. Run it again. Well, it's over 3 seconds now. This is considerably slow, and if you run your loop version of the Fibonacci sequence, it's much faster. Then the question is why? If you enable my debugging print statements here, I disable them for our testing so you get a cleaner output. But if you are interested, you can re-enable them. You will find there are repetitive recursions occurred for the same number. For example, if you're doing recursion f4 here, f4 equals f3 plus f2, and then for f3 it equals to f2 plus f1. It computes f2 one time, and then this f2 computes another time. It doesn't remember the value it's already got. Now let's see how we can improve this. The inefficiency of our first version computed Fibonacci recursive implementation comes from it keeps computing the terms it already knows, it already computed. Intuitively, if we can remember those terms we have already known, we should be able to improve the performance. With that intuition in mind, we have another version of recursive computing Fibonacci sequence. Let's give a name computer Fibonacci recursive V1. The first term n represents the term of the Fibonacci sequence. The second one is NumPy array that stores the numbers we have already computed. Well, to work with NumPy array, which starts at 0 as it's 0 index based, so the n we allow n to take on a value 0. 0 is first term. N here really means n plus 1st term in Fibonacci sequence. In other words, if you call this version with 3, comma, fn, it really returns the 4th term of Fibonacci sequence. That way we can align with this zero index based array very well. The first term, like I said, is 0 based now. So if n equals 0, we return the first term, which is 0. However, before we return, we record the first term value, which is 0. We put it into the first position in this array. For the second term is 1, and we know the second term is 1, we return 1, but before returning it, we record the second term's value in the second position in this array. Now this is the trick to improve the whole thing. So if we know the previous 2 terms, we have already computed the previous 2 terms, we use -1 to represent whether a value has been computed or not. So if we know the previous 2 terms have computed, have values, meaning they are not equal to -1, we can just do the direct computation. Fn, the nth term, is the sum of the previous 2 terms. We return. We don't do recursive calls here. If we don't have the values recorded, we do the recursion as usual. Now I have refactored the test into a test method. This is our first version, and we want to test how long it's going to take to find the 35th term. And this is our improved version of recursively computing nth term of a Fibonacci sequence. And we know it's 0 based. So if we pass 34 to it, it really returns the 35th term of that sequence. And we need to create an array that stores 35 elements. And we know the Fibonacci sequence is type integer. So we specify the type is an integer, and we initialize the array elements to -1. We don't know each of the terms value when we start. And as usual, we time it. We print the duration in the end. Now let's run it. Okay, see the first recursion, as before, it took about 3 seconds. Actually, this time it's 3 seconds and a half. And for the improved version, it's virtually 0. So the performance is close to the loop. Now for these two examples, they do have some values in terms of introducing the recursive concept in programming. But in practice, they do not provide good performance. Whenever you use recursion, you need to balance the performance and the ease of understanding. In most cases, a recursive functions can be replaced by using just loops. That way, you avoid the potential of Stack Overflow issues. Let's discuss how to sort an array of elements today. By arranging elements in a certain order, we can retrieve the relevant information quickly, such as using binary search. There are many ways of sorting. One simple sorting algorithm is called selection sort. The idea of selection sort is at each iteration, it finds the smallest key from a given array and make it to the correct position. And in the next iteration, it repeats the search the same. It finds the smallest key again, but in a reduced range of the array. For example, if we have an array contains keys like 5, 1, 82, 706, 7 keys. The first iteration, by using selection sort, we want to find the smallest key from the original array, that is from the index 1 all the way to index 6. And the smallest key is 0. We find the smallest key, we swap it with the keys at the first position, because the first position is supposed to store the smallest key of the original array. So we swap 0 and 5. The remaining elements are not changed. After the first iteration, the first position at index 0 would have the smallest key of the entire original array. The next iteration, it works the same. However, it searches the smallest key from the remaining subarray from index 1 to index 6. Let's mark the index here, 0, 1, 2, 3, 4, 5, 6. The array is 0 index based, so you have 7 elements. The index starts from 0 and ends at 6. The second iteration, just like the first one, it finds the smallest key, and this time is this guy 1. There's nothing to swap, or you can say it swaps with itself. So 1 is still here. That's the second smallest number in this array, in the original array, but it's the smallest one in this subarray. You can put it here. After the second iteration, we have the first 2 positions store the 2 smallest keys from the original array that's ordered ascendingly here. Okay, the remaining elements are not sorted yet. The third iteration works the same, but in a different range of the array. So we want to find the smallest array from this range, from index 2 to index 6. And once we find it, we still want to swap it with the element at the first position of the subarray. Okay, this time the smallest key is 2, and we want to swap 2 and 8. The remaining elements now changed. So the third iteration, we have this first 3 elements fixed. The fourth iteration, the search range is this. The smallest key is 5, and it swaps with 8. These are now changed. 6. So this is the fourth iteration. Fifth iteration searches in this range, and the smallest key is 6 in that range. 6 swap with 7, and this becomes 8. These are the first 4 already sorted. After fifth iteration, the first 5 elements are in good order. Now the last iteration in this range, and the smallest one is 7. 7 swap with this 8, becomes this 5, 6. All right. After 6 iteration, we have the array in the order we want. We sorted in ascending order from smallest key to the largest key. And we used 6 iterations. Of course, in each iteration, we make a comparison to find the smallest key from that search array. Now, the purpose of learning the sorting algorithm is not like you need to hand implement a certain sorting algorithm by yourself at work. You almost never need to do that, because virtually all the libraries for each major programming languages have the sorting function built in for you. We learn this is for us to understand how the algorithms performs, and sorting is very good to give us insight at each step how the algorithm produces, and help us understand the complexity of sorting of an algorithm in particular. So in this case, we have 7 keys to be ordered. In this selection sort, it's simple-minded. Regardless what the keys in the array, whether they have been ordered or not, in each iteration, it always tries to find the smallest by doing the comparison. The comparison is conducted in such a way it compares all the elements. For example, the first iteration, it would compare 1, 2, 3, 4, 5, 6 times. And the second iteration, it would compare 5 times. Even though some of the numbers or keys have been already compared. So the selection sort doesn't use much information from the array itself. Let me repeat this again, because the way we are finding the smallest is by comparison. So if we want to find the smallest from the original array, for example, 5, 1, 8, 2, 6, 2, 7, or 6, what we will do is we compare this element to 5 first. It's less than that, so the 1 is the smallest. And then we compare each of the remaining elements to the current smallest we know. So we make 1, 2, 3, 4, 5, 6. 6 comparison. And for the next iteration, we are selecting from the 6 elements to find the smallest, we need 5 comparisons to find it. So that is, we compare 8 to 1. So 1 is the smallest. Okay, we move on to find to the next element. 2 compared to 1. Okay, it's not smaller than that. 7 to 1, 5 to 1, 6 to 1. Okay, 5 times. And the third iteration, we are finding the smallest from the remaining 5 elements. So we are comparing, we have to compare 4 times to find it. 2 compared to 8, all right? So we know 2 is the smallest. But we have to compare the rest of the elements to 2, see if there are any elements less than 2. So we compare 7 to 2, 5 to 2, 6 to 2. Plus the original comparison 2 to 8, we have to compare 4 times for the third iteration. And all the way down to this. So you need all this number of comparisons. If we have an array of contains n elements, then all the number of comparison would become n minus 1, n minus 2, all the way to 1. And the total number of comparisons in that would be to, I think it's this. But no matter what, as n increases, this n minus 1 and n becomes same or very similar. And using computer science terminology, this gives you a complexity of n squared. And sometimes they use big O to denote that. Now you don't have to know much details about this, but this just gives you an idea. The sorting algorithm is used for analyzing the complexity of an algorithm. And because we know sorting very well, we know how many comparisons or operations need to be performed at each iteration. So we can give a pretty precise estimate of how much time the algorithm would need to produce the desired result. The next simple sorting algorithm is called insertion sort. We still have the same elements, 5, 1, 8 to 706, 7 keys to sort, and the index is from 0 to 6. We want to sort them ascendingly from the smallest key to the largest key. Insertion sort works iteratively as well. The idea is at each iteration, we insert the element to an existing sorted array. Let's see how it works. The first iteration. Now, before we sort, I want to point out we are sorting these elements in place, meaning we are not moving or copying these elements to a new array. We are just exchange or swap or shift the elements in the same array. And after the sort, the elements in the array are already reordered. In other words, the original array is modified. We are not using new array, we just do the whole operation in the given array to be sorted. Okay, now the first iteration for insertion sort, what we want to do is, suppose we have an array which has only one element, 5, and that can be considered sorted. Okay, let's say how we insert a new element 1 into that. We compare this to this. We want to find the position to insert. Okay, 1 is less than 5, so we move 5 one position to the right. That will make room for the 1. Now there's no more elements to compare. Okay, we insert 1 here. Now after the first iteration, the array becomes this, and the first two elements in the array are sorted. Of course, this is not done yet. We want to continue on and insert the third elements in the original array, or the first element in this subarray. We compare 8 to 5. Okay, there's no need to compare more. 8 is greater than 5. There's no place to insert before 5, and that is the position for that sorted subarray 1, 5, 8. So after the second iteration, it becomes this. Third iteration, let's insert 2 to this ordered array. We compare 2 to 8. Well, 8 is greater than 2. We move 8. We shift 8 to this position because we need to insert 2 at a position before that. And then we compare to 5. Still, 5 is greater than 2. We move. Okay, that means the room or the position for 2 must be before 5. Okay, and then we compare to 1. All right, that's it. 2 is greater than 1. Now the room left for 2 is this. All right, now we inserted 2 to the right position. After the third iteration, the array becomes this. Let's go on. Fourth iteration, insert 7. 7 compared to 8, well, let's move 8, shift 8, 1 position to the right. And 7 compared to 5, 7 compared to 5, well, greater than 5, okay, no need to compare more. 7. So after fourth iteration, the array becomes this, and this subarray has been ordered. Fifth iteration, we compare 0, or we want to insert 0 to this existing ordered subarray. 0 compare 8, well, 8 is greater than that, 7 is greater than 0, and 5 is greater than that. 2, you see we need to shift all the elements in this ordered array to the right and make room for the 0, for the insertion position for 0. So after fifth iteration, this is ordered. Now the last one, that's the last iteration. 6 compare 8, no place for it. Compared to 7, okay. Now 6 is greater than 5, okay. Then this position is the right insertion position for 6. So after 6 iteration, we have a sorted array from smallest key to the largest. Now you can see this algorithm indeed improves from the previous simple-minded selection algorithm, because at each iteration, it does not need to compare all the elements to find the insertion position. And this is good. Suppose we have an array that's already ordered, meaning it's already ordered from the smallest key to the largest key. So already ordered. So you only need to scan once from this. You're done. That's the best case for insertion sort, meaning it sorts on a sorted array. Of course, this array has been already sorted ascendingly and you want to sort it ascendingly. If you want for each insertion position at each iteration, you can use binary search. That may improve the algorithm a little bit. Now, the worst case for this is for each insertion position, you would still need to do all the comparisons and also need to shift all the elements. Then that becomes no better than the selection sort, or maybe even worse. Average case, though, you can argue the insertion position to find the insertion position from this ordered subarray, you only need to compare and shift half of them. As the number of elements increases, the insertion sort performs not significantly better than selection sort, although it is a better version of simple sort. Let's take a look at how we write selection sort and insertion sort in Python. Selection sort function takes two arguments. The first one is an array supposed to contain the keys ordered or not ordered. The second argument with the default value false. If this flag is true at each iteration after the or at the end of this outer loop, we print the content of the array. That gives you the result of the array at each iteration. Of course, if by default, if you don't specify the value, it would not print anything. This selection sort, like I explained, works iteratively. It starts from finding the smallest key from the original array. So we start from 0. And at each iteration, we find the smallest key from that given array. Once we find it, we copy it to that index that's supposed to store the smallest element for it. And of course, we do that by swapping, like explained. The smallest one will come to that position. The first time, the smallest one will come to I, which is 0. And after the first iteration, I becomes 1. It moves to the next index position. And then once you find the next smallest one, you copy it to index position 1, and the next time index position 2. So it keeps moving the smallest, copying the smallest key to the next position. That's the outer loop. The inner loop, while loop, finds the smallest key from a given array. The inner loop finds the smallest key from a given range in the array. This procedure can be translated into other programming languages very easily. All right, let's look at insertion sort. Well, this is actually smaller than selection sort. The same two arguments, array that contains the elements to be sorted, and the optional argument with the default value false. Simple validation again, and still double loops here. The outer loop, the for loop, retrieves each element starting from index 1 and all the way to the last element. And the inner while loop finds the proper insertion position for the value to be inserted. And remember, as we explained, we're comparing that to be inserted value to that ordered subarray. And if that number is less than the preceding number or immediate number in that ordered subarray, we want to shift. We want to shift the number to the right to make room for the value to be inserted. So this way you copy array I to array I plus 1 effectively shifts element I to the next position. So we keep shifting until the value is no smaller than the value at the previous position. And then we find that position to insert. And of course, you want to make sure you have also have the index invalid range. Once you find the insert position, you assign that to the insert position. Then you are done for that value. You go back to the outer loop, you find the next element in the array to insert. That's the we increment the j increments automatically when you do this in range. And then you start this inner loop again. The value to be inserted, we start at index 1. We don't start from 0 because, like I explained, when we start this whole procedure, we assume the first one is already sorted. Of course, if an array has only one element, yeah, it can be considered sorted. And also one point here is the insertion position is really at I plus 1 after the inner loop, which finds the insertion position. This is because we compared the element at index I. When we exit the loop, the value to insert is definitely no smaller than the element at I. So element at I is not shifted. It needs to be remain at where it is. And the insertion position is really I plus 1, which has already been shifted to the right. Next sorting algorithm is called quicksort. It's a little bit complicated than the previous two simple sorting algorithms because this one has recursion involved. Although, like most recursive procedures or algorithms, they can be replaced by using loops. But here, using recursion can actually help us understand the algorithm easier or better. Now, the idea of a quicksort is at each iteration, given an array, we find a value, we call it pivot. When we have the pivot, when we have selected the pivot value or key, we rearrange the array in such a way that part of the elements in the array are all less than the pivot value, and another part of the array, to the right of the pivot, or having values or keys greater than the pivot. For example, here, if we select pivot value 6, there are more than one way of selecting a key as pivot. But let's keep it simple. We just select the rightmost element as the pivot. So we select this guy as the pivot value. And we do something to rearrange the array such that the left part of the array, or having elements less than or equal to this pivot value, and the right part of the array all having values greater than the pivot. After that, we recursively doing that quick search on these two subarrays. So for this subarray, again, we select a pivot, and we partition the subarray. We select the pivot partition array. So there's another pivot, part of that, the left part of that, all less than that, and the right part, all less or greater than that pivot value. And of course, this first pivot value will remain at the position because this is the sorted position for this key. The recursion applies to the right part of this subarray. We find the pivot value, and then the left part, actually that's the part in between this and this, having elements or the keys less than that, and this part greater than that. Now you can say we keep doing this until we reach to some basic condition of the recursion. We would have the array in an ordered, in a certain order, in ascending order in our case. Now let's do it step by step, see how this quicksort procedure works. And the first iteration, we select pivot, pivot, pivot value 6. So this is our pivot value. And we want to partition the array into two parts. One part is less than this pivot value. The other part, the right part, having all elements greater than that. We do that by scanning the array from two ends. We use I to start from the very left, and we use J to start from the very right, of course, in this subarray. And if we find a value, an element, a key that is less than the pivot from the left, we keep moving. So 5 is still here, but I moves to here. It's still less than that, so keep it here. I moves to the next until we hit a key that is greater than the pivot. So now I stops at element 8. We stop this is because we know for the left subarray we need to have the elements less than 6, the pivot value, and 8 is greater than 6, so somehow we assume the 8 should be moved or swapped to another part of the array, so we stay at here. For the J starting from this position, we do the similar thing. We compare the value to the pivot. If it is greater than the pivot value, we should keep moving to the left, moving the J index to the left, because if the key here is greater than 6, that means it's already in the right partition, the partition that contains the keys greater than the pivot value. Now if it is less than that, in this case 0 is less than that, we stop here, meaning we need to swap the element at I and J, because the element at J needs to be moved to a position at I which will have element less than 6. So we need to do the swapping here, and 0 moves here, and 8 moves here. Now once we move it, we should move I position to the next, and J position to this, because this 3 and this position are fixed. They are in the right partition. Now once we move this I to one more position to right and J one position left, we keep doing the same thing. We compare if the element at I is less than the pivot. If it is less than that, we should move on, because this is the right partition for this element. Okay, and this is 2, keep it there, and I moves on. I will keep moving to the right until it hits an element that is greater than pivot. Okay, now I is at 7, as points to 7, we stop. Now for J, if J is greater, if the element pointed by J is greater than the pivot, we should keep moving J to the left. So here now J is, well, not here, J becomes here. So here, and I is here, J is here now. Now once J hits to an element which is 2 is less than the pivot, J stops. Okay, at this point we can make a decision, because we already kind of scanned, J and I crossed each other. The scan should stop because the partition is virtually done. And one part of that has all the elements less than the pivot value, and the other part has value or keys all greater than that. Now we need to find the position for the pivot value. The pivot value will be copied to this position pointed by index I. So the pivot value will be here. Whatever the element at I will need to be copied to the right index, or the right or the index pointed by, or the index for the pivot or the previous pivot value. So 7 goes here. Now after this iteration, you can say we rearrange the elements in the array, and the pivot value is fixed at its ordered position. This is the position if all the elements are sorted, and this is the position for the key value 6. After that, the left subarray has all elements with values less than 6, and the right subarray has all elements with values greater than 6. So after this iteration, we can perform recursion, a recursive function. We can perform the recursive call to this subarray here and here to repeat the procedure we just did again. In other words, for this subarray, we can pick pivot value, the rightmost element, 2 as the pivot value. Then I starts from this, and J starts from this, and we do this scanning again, and we find until I and J cross to each other. That gives us the position for the pivot value. So after that iteration, for this subarray, we should have something like this, 0, 1, 2. So the pivot value must be here. And we rearranged this subarray such that this subarray, subarray 2 relative to this, has all values less than this, and 5 has values greater than 5 is greater than that, than the pivot value 2. So this is now changed, and this now changed yet. So if we finished the recursion on this subarray, we would end up with an array like this, and we can continue on to recursion on this. And this has only one element here. The recursion will just, the sort can end instantaneously. We do the recursion here the same way. We pick 7 as the pivot value, and then we find that position for that pivot value by scanning, I, J here, but this time it's just this. It ended up just like swapping this. Well, this is called quick sort. So each iteration, we find a pivot value, we partition the array into 2 parts. The left part to the pivot value has all the keys less than the pivot value, and the right array has all elements with keys greater than the pivot value. Now, to analyze the performance of this, it's not as straightforward as the simple sorting. However, you can see the worst case is we somehow have very bad luck selecting the pivot. Each time the pivot is somehow the smallest value. So it does not partition the array into 2 halves. That means each iteration you have one partition almost 0 and another partition having almost the entire elements except that pivot value. and then you have to do the recursion on that 1 minus size subarray. So that ended up almost like a selection sort. Now the ideal case is every selection of the pivot value that will cut the array in half. That will give you the best performance. And in fact, on average case, it performs similar to the ideal case. Let's go over Python implementation of quicksort. The interesting thing about this is you do need two functions for this. One is the outer function. That is the function supposed to be called by the application. So the application wants to sort the array and also decides whether to output the array content at each iteration for debugging purpose. But the actual algorithm and recursion is done by this inner quicksort. These functions are not called directly by the application. But let's look into this inner quicksort. We have an array, and we have the left and right index that defines the subarray you want to partition. Now you should notice the outer function calls inner quicksort by passing the leftmost index 0 and the rightmost index, which is the array length minus 1. That gives you the entire array to begin with. And that is the purpose of this quicksort and this outer function. The inner quicksort operates on the subarray defined by this left index and right index. And we said we want to use a simple pivot selection, which gives you the pivot at the right index. Now the scan begins from the very left index and the index 1 left to the pivot, that's right index minus 1. And this loop is scanning from the left until we have an element that is greater than or equal to the pivot. If the element is less than the pivot, we know there's no need to rearrange them. There's no need to rearrange it. The right scanning is the opposite. If the key is greater than that, there's no need to rearrange it. We keep decrementing j. So this to while loop will dim to exit. You can think about a y. And once these two loops exits, if at that point I is less than j, meaning we need to rearrange, we need to swap an element which is less than the pivot, which is greater than the pivot but is at the left position to the pivot, we need to swap it to the element to the right of the pivot, which is determined by j, and currently it has the key less than the pivot, so we do the swapping. And again, all this implementation can be very easily translated into other languages. So we swap that. Once we swap that, we know we can move on. For I, we can move on to one index to the right, and for j, we can move on to one index to the left. We keep doing that. If I and j cross each other, we would break the loop. Once we break the loop, we know the I position is good for the pivot. The I is really the partition point. And we swap, we copy pivot to I, and we copy whatever the value at I which is greater than or equal to the pivot to the rightmost index. Now the recursion occurs at the end. Once we have the pivot value fixed, the recursion occurs on the left partition to that pivot, which is left index to I minus 1, Remember, I is the index of the pivot. The pivot value is the right position for that key. And the right subarray is one position to the right of the pivot value and on two to the right. Of course, this may not be a valid array range, but that's okay, because at the beginning of this function, we check whether left index is greater than or equal to right index. If it is greater than or equal to right index, either you are out of range or the array has only one element. If the subarray has only one element, there's no need to partition it. All right, this covers our discussion of sorting algorithms. You can generate whatever random values in an array to test these sorting procedures. Let's learn some basic computer graphics programming today. First of all, we want to know how a color is represented in computer. Computer uses RGB format for color. RGB stands for red, green, and blue. These are the three primary colors. A different combination of these three color components produce another color. And each color component can take on a value from 0 to 255 integer value. The value represents the intensity of that color component. 0 means the least amount of intensity, meaning there's nothing from that color, or that color component has 0 contribution to the final color. If the value is 255, that color component is at its maximum intensity, or it is the brightest of that kind. Now we can use tuple with the three elements for each of the three color components. The first element we can use for the red component, the second element in the tuple for the green, and the third one for the color component blue. Each of these elements in the tuple need to have a value from 0 to 255 that reflects the respective color's intensity. So if I put 0 here, 0 here, 0 here, all three color components have 0 intensity. This produces a color black. Nothing. Now, what if all of them at the maximum intensity? So this gives us the result color white. If we just specify one value for one of the color components, for example, we only specify the red, or we give the red a non-zero intensity, and we make the other two zeros, this actually gives us a pure red. Because this intensity is the maximum for that color component, so this red is the brightest red. So in other words, if we keep the green component's intensity 0 and the blue color component's intensity 0, and we reduce the red's color intensity by half to this will make another kind of red, but a little bit darker, because the intensity is somehow less, reduced. Of course, like I said, you can have any value from 0 to 255 for each of the color component. If I make this to red to 255 and green to 255, and blue 0. This combination gives us a yellow color. This is a pure yellow with the brightest, this is the brightest yellow because this and this have the maximum intensity. Now the tuple is one way of representing RGB format. And sometimes you can use a hexi number because 0 to 255 can be stored by a byte, 8 bits. We learned binary a while ago. 1 byte without using the first bit for the sign can store value from 0 to 255. So for color components intensity, a byte is just good. For black, a hexi representation could be is something like this. This is 1 byte, another byte, third byte. This byte is for red, and this byte is for green, and this one is for blue. And for white color is hexi format using RGB is FF. That's the R component, 1 byte, another byte, green, and third byte, FF. That's the blue. Now for a darker red, 0x80, 0000, and 80 is red. This byte green and this byte blue. This is hexadecimal, and this is equivalent to hexadecimal 228. Now with this 3 bytes, 24 bits, we can have a 2 to 24 number of different colors. This is the whole color space using 24-bit RGB format. And this is quite big. We don't use much of it. Next, let's talk about the screen coordinates. Screen coordinates is coordinates of a 2D XY plane used by computer to render graphics. To be more precise, this 2D XY plane is defined for a computer program. Computer programs displaying window. For example, I have a window here. The title of this window is called Graphics Basics. This is actually a Python program. The origin of this displaying window is at this up left corner. This is 0, 0. The X direction goes from left to right. This is X. The Y-axis goes from top to down. So this is Y. The difference from our coordinate system used in mathematics is the origin is at the up left corner instead of at the left bottom corner, and the Y direction, Y-axis, is flipped. The display window is usually a rectangle or square. It has width and height. The width is this, from left to the right. And the height is this. The width and height are in pixels. For example, the width here, 800, each height here is 500. That means the height is 500 pixels, or the width is 800 pixels. Now with 800 and 500, you get 500 times 800. That's the resolution of this displaying window. If you want to draw a line inside this window, you must have that coordinate in this range. If you draw a line from 0, 0 to 100, 100, that's good. It's probably 100, 100 is at here. So this is a line from 0, 0 to 100, 100. Because this is the screen coordinate system, so the line is downwards instead of a slant from left to the right upwards. That's a typically say in mathematics. If you draw something other side of the window, for example, if you draw a circle that has the center is beyond 800 and 500, you would not say it. So you must be very careful about drawing graphics using screen coordinates. Now later we will learn something to transform the screen coordinates into whatever the coordinate system we want. But here, let's stick with the given screen coordinates. The origin is from the left up corner, and x goes from left to right, and y goes from top to down. In fact, this is the fourth quadrant of coordinate system you say in mathematics, just with the y flipped. Now let's draw some basic geometry shapes in Python using a package called Pygame. If you haven't installed this package, Pygame, you can type in the commands pip install Pygame in terminal window. I have installed this package already, so I just need to import. At line 5, import Pygame. Next, import a built-in module, system sys module. The first thing to use Pygame is to initialize the package. We do it at line 9, pygame.init. After that, we define the window size, the displaying window size. 800 pixels width for the window and 500 pixels height. After that, we set the display by passing the window width and height in a tuple. This returns a drawing surface. All the graphics will be drawn on this main window. We also want to give the window a title. We can call it Graphics Basics. For this small application, we can have a frame rate 10. That means we refresh the main loop 10 times per second. The main loop includes whatever calculation, and the final screen updates. We use pygametime.clock to help us track the time. After that, line 29 to line 34, we define a few color constants. And these color constants are in RGB format we just talked about. We use a tuple for the color. The first element in the tuple is the red component. The second is the green component. The third is the blue one. For a color line, red components 0, blue component is 0. The second component, green. RGB, green component will give its full intensity. So this is the brightest green color, lime. And similarly, we define a color for the pure red, the brightest red. And of course, we use 1 byte for color component, and there are 3 components, so the 3 bytes, 24 bits, it gives us quite a bit, more than 60 million number of colors. We don't need all that. However, if you are interested, you can go to this link, rapidtables.com, to find more named color constants. All right, next is the important graphics loop. Everything happens in this while loop. First, in the loop, we make sure the loop does not run beyond the frame rate we want. And second, there's a small for loop within this while true loop. So this for loop is to trap the event, the user inputs. So if the user wants to exit the application, we want to exit immediately without just closing it through the debugger. At line 41, we check if the event type is quit. If it is pygame.quit event, we just want to exit this application. So pygame quit and sys.exit will exit the application. Certainly it will exit the loop. So we have guaranteed a way to break from this seemingly infinite while true loop. By default, the background color for pygame window is black. Now, since I have defined a different background color, so we can fill up that color for the Windows background color. Before we proceed to draw the basics, draw the basic geometries, we run this, see what happens. Run this program. All right, you see we have a window. It's about 800 pixels in width and 500 pixels in height. And also keep in mind this width and height exclude the size of the title bar and the size of the border. Because we haven't drawn anything here, you just see the background color showing up. And of course, we set the Windows title to graphics basics. So this is the Windows title. All right, let's close it. All right, first let's see how do we draw a rectangle. Let's remove the comment. This is the API provided by Pygame to draw a rectangle. The first argument you passed is the drawing surface we created above. We created at this set mode. Like I said, all the drawings happens on this main window. So the first argument you pass to the draw.rectangle rect is main window. And the second argument is the color. And the third argument is the coordinate and dimension of this rectangle. So we want to draw the rectangle at coordinate 30 and 10. 30 and 10 is the left top corner of this rectangle. 30, 10 is the coordinate of the left top corner of this rectangle. And 100 is the width of the rectangle. And 50 is the height of the rectangle. Of course, this dimension, these sizes are in pixels. The last argument here is the thickness of the line. All right, let's run it, see if we can see a rectangle. Run it. All right, now you see a rectangle color green, about that size at the coordinate 30 and 10. It's about right. So let's close this. Next, let's see another rectangle drawing API. And this time, we changed the last argument. And of course, we changed this coordinate of the rectangle's left top corner. We changed the y coordinate. We moved it down to 100. Remember, in screen coordinates, the y positive direction goes from top to down. So this 100 actually moves this rectangle below the rectangle we just draw above. And this last argument, if it is 0, that means we want to fill up this rectangle. Fill the rectangle with the color, which is the second argument. So let's run it. All right, you see the same rectangle size. However, the second rectangle is filled with this color. All right, we are done with rectangles. Let's see lines. How about draw a line using Pygame? We know 2 points define a line. So we need to pass the 2 points for the line to this Pygame draw line API method. First argument still the same, that's the drawing screen. And the second argument is the color, and this time we want to draw a red line. Third and fourth arguments define 2 endpoints of the line. In fact, it is we are drawing a line segment because in geometry, a line really has no ends. We are drawing a line that connects these 2 endpoints. And the last argument is the line thickness. So the line will be drawn at coordinate 30 to 100 to 120 to 100. And noticing the x coordinate is different. However, the y coordinates for these 2 points are the same. So that means we are drawing a horizontal line. So let's run this program. Run it. Okay, this is the red line, a horizontal line from left to right. Let's close it. All right, now let's see, what about another line? Still the same window, the same color, same line thickness. But we changed these coordinates. So this time, for the 2 points, the x coordinates are the same, 30. However, y are different. Now, if the x coordinate is the same but the y is different, we are drawing a vertical line. Run it. Indeed, we are seeing a vertical line. Close it. All right, let's continue. How about I draw a line, inclined line? The same thing, first argument, the drawing surface, the second argument for the color, and this time the coordinates is the start point of the coordinates. The coordinates of the start point is 30, 350, and the end point on the line is 140. So we are drawing a inclined line, a slant. Run it. All right. This is slant. And noticing, I'm not sure if you can see this on your screen, but here you can see this line is not as smooth as the above 2 horizontal and vertical lines. Close it. To deal with this situation, computer has a technique called anti-aliasing to smooth the drawing, to smooth the border, the edge of a graphic. So we can use pygame.draw.aa line. That gives us a line much smoother. First argument, second argument, same thing. We want to move that line slightly below the one we just drew above. And for a AA line, anti-aliasing line, we don't need to specify the last argument. But let's run it. All right, now you see another line with anti-aliasing. So this line looks much smoother. Okay, let's move on. What's next? All right. Use Pygame, we can draw a line that connects 2 points on the screen. We can also use Pygame to connect a series of lines. The API for that is pygame.draw.lines. First argument, drawing surface. Second argument, let's make this line blue. And third argument, well, let's talk about the fourth argument first. The fourth argument is a list of the coordinates that we want them to be connected. And of course, the last argument is still the line thickness. The third argument tells Pygame whether to connect the last 2 points in the coordinates. So this, we have defined a list of 4 points. 1, 2, 3, 4. And we don't want to connect the last points to the first. So we should say a 3-line segment, a blue, in color blue. So let's run it. All right, that's this lines. Similar to draw a AA line, you can also draw AA lines, meaning apply anti-aliasing technique to for connecting all the points. Okay, let's see next one. Next one, let's see how to draw an ellipse. We use this pygame.draw.ellipse. Main window, color blue. And this last argument gives us the bounding rectangle for that ellipse. And rectangle, the first element is the first 2 elements in this list is the coordinate of this bounding rectangle's left and up corner. And third element is the width of the bounding rectangle, and the fourth element is the height of this bounding rectangle. So the ellipse will be drawn within this bounding rectangle. Run it. Okay, now you see an ellipse. Because we did not pass the line thickness for that ellipse, actually that ellipse was filled with the color. It's a filled ellipse. If we want to just draw an ellipse without filling it with color, we need to pass another argument, the last argument, indicating the line thickness. So still you call pygame.draw.ellipse, main window, the color, and the bounding rectangle, and the thickness of the line. Now this way you draw an unfilled ellipse. Now this time the bounding rectangle is the same size as above, so 150 width and 18 height. However, this time we move the rectangle downwards by 100 pixels. So we moved from 120 to 220. Run it. All right, now you see a unfilled ellipse. Close it. Move on. Let's say draw a circle. How to draw a circle? We know to draw a circle we need to know the center of the circle and the radius of it. Mathematically speaking, once we know the radius and the center, we know the circle. And it is true with Pygame. We pass a coordinate that is the center of the circle, 320 and 380, and radius 50. And for the circle's thickness is 1. So run it. And this time the color is yellow. We should see a yellow circle at 320 and 380. Okay, now you see a circle. And of course, if you give a bounding rectangle as a square to draw a ellipse, I'm sure it will display a circle. Close it. Let's move on. What about drawing an arc? For an arc, it's very similar to drawing an ellipse. So you give a bounding rectangle. However, you need to provide span of the angle. The third argument is the starting angle, and the fourth argument is the ending angle. So by specifying a start and end angle, you defined the rotation or the span of that arc in terms of radians. So you need to pass this third and fourth arguments in radians for the start and end angle for that arc. And again, the last argument is the arc's thickness. So let's run it. Okay, now you say a arc. And if you notice, what I specified here is for the arc to start from 0 degrees to 3/4 of pi. Now, the arc is about that angle. Correct. Close it. Next one, polygon. For drawing a polygon, we need to define, for a polygon, we need to pass the Pygame a list of coordinates that indicate the vertices of that polygon. The first argument, the second argument, no difference. The third argument is a list of coordinates. And each of the coordinate x, y is a vertex of that polygon. Let's run it. Now you see here it's a polygon. 1, 2, 3, 4, 5. In fact, when you draw a polygon like this, it connects the last point to the beginning point automatically. So this is somewhat similar to draw lines, but it connects by itself automatically. Of course, the polygon, you can fill it or not fill it by changing the last argument. Okay, last one. Last one is really not, it's nothing new. The last one is nothing new. We want to draw a donut. We draw that by drawing two circles. The first one, we draw using a dark orange color with a radius 70. The second one, this is drawn at the same location. The second circle is at the same location, same coordinate, but a smaller radius. The color is background color. We have to draw the first one, draw the bigger circle first, using a color that is different from the background. And the second one, because it's using a background color, it would overwrite. It would draw on top of the original one. It would actually override the dark orange color with the background color. Now you run it, you see a donut. So the inner circle is using a background color, so you don't see it. But the end result is like a donut. All right, so much for basic drawings. I hope you like it. We have learned some basic computer graphics. We know how to use a Python package, Pygame, to draw some simple geometry shapes, such as a line, a circle, a polygon, an ellipse, a rectangle, etc. Now, what if I ask you to draw a regular hexagon given its size length and the center coordinate of its circumscribed circle? There is no such a function in Pygame directly available for you to draw such a regular polygon. So how to do it? Of course, we need to calculate the coordinates of each of the 6 vertices of this regular hexagon. Once we know the coordinates of these 6 vertices, we can easily use Pygame draw polygon or draw lines to connect them to make a regular hexagon. Now, you can calculate the coordinates directly in its original, this blue XY coordinate system, this screen coordinate system. However, we can choose another coordinate system that can help us make the calculation easier. So long we translate that coordinates to the final screen coordinates, we are still good. So in other words, by adopting a different coordinate system, we can make the whole calculation more obvious and simpler. For instance, I have x prime, y prime, this green coordinate system with its origin. Origin here, 0, 0. Coincides with this regular hexagon's circumscribed circle's center. And the x prime's direction goes from left to right, and the y prime's direction goes from bottom to top. And of course, x prime is parallel to x, and y prime is parallel to y. The only thing is the y prime's direction is flipped. It's going upwards. And in fact, this is the coordinate system we are more accustomed to. With this coordinate system, this green one, the calculation for each of these 6 vertices coordinate becomes simpler. Like I said, we are given the length of the regular hexagon's side, L, and we know the center. Now, because it is a regular hexagon, all the sides are equal. And if we draw a line to connect the origin from the second vertex to the origin of x prime, y prime, this angle is 60 degrees. And the length of this equals to this, and also equals to this. This is a equilateral triangle. And for this one, if we connect, this is also 60 degrees, and this is 60 degrees. Now, for the first vertex, the coordinate becomes pretty straightforward or obvious. So the L, the length of this is L, because this is an equilateral triangle. So that's the x prime coordinate for this vertex. What about the y? So simple, it's 0. Now we can get the first vertex coordinate pretty easily. It is L, 0. Now what about the second one, the second vertex? It's still very straightforward. We can just think to get the second vertex, we rotate this one, the first vertex, 60 degrees counterclockwise. We get this. Or you can calculate using some simple trigonometry. It's very simple. So the x is really L cosine 60 degrees. So this is x. Now the y is L sine 60 degrees. So this is the second vertex's coordinate. The same way we can get the third one, fourth one, the fifth one, and the sixth one. And just for each of them, the rotation, the angle is different. The first one is 60 degrees. For the second one, we're going to plug in cosine 120 degrees. And for the third one here is 180 degrees. Now we know it's very easy to calculate this regular hexagon's vertices coordinates relative to x prime and y prime system. We cannot use this to draw directly because the computer only knows the coordinates relative to this blue one, this blue x and y. So that means once we get these coordinates in x prime and y prime, we need to translate them back to the original screen coordinate system, the blue one. And we know we are given the center of this regular hexagon. So the center is relative to the original screen system, x0, y0. x0, y0 is relative to this origin, the blue 0, 0. How do we find out the relationship between a coordinate in x prime, y prime system and the coordinate system, a coordinate in the blue xy system? We are doing a homogeneous transformation. So the transform applies to every point in x prime and y prime. No difference. The transformation is the same for every point here. If it applies to the first vertex, it applies to the second one. If it applies to the origin here, it applies to any other points. By simple calculation, you say for the origin in x prime, well, let's use a different color, green. So x prime. So if I plus x0, I get the x in this blue coordinate system. We just need to add x0 as an offset to x prime's coordinate. Then we get the x coordinate in this blue xy system. Then what about the y prime? So what about y prime? How do we transform from a y prime to y? Now suppose we have a point here, the second vertex. The y prime is this distance. Okay. And the y0 is from here to here. That's the y offset. So what we need is really this distance. This distance is very easy. It is y0, the offset, minus y prime. Now we get this transformation. We can map a coordinate in x prime, y prime. By adding the offset, we can transform them to a coordinate in xy system. Now we have refreshed mathematics about 2D transformation. Let's see how we do it in Python program. We need to import the packages and modules we need. Pygame, sys, and math. We need the math module for calculating sine and cosine. Line 6, we initialize Pygame, pygame.init. Line 9 and line 10, we define two constants for the displaying window's size, 500 pixels in width and 500 pixels in height. Line 13, we set the window's size by passing the two variables in a tuple, and this Pygame display set mode returns the drawing surface, main window, which will be used for drawing the geometry shapes, in this case, regular hexagon. Line 16, we specify our Windows title, Graphics 2D Transformation. Line 19, we give a frame rate of 10. We don't want our main loop to use as much as CPU. The main loop should execute no more than 10 times per second. That's sufficient. Next, we create a Pygame clock to help us track the time. Line 26 to 31. As usual, we define a few color constants using RGB format. Next, line 33. This is the function that draws a regular hexagon. It takes four arguments. First is the drawing surface. The second is the center coordinate of this regular hexagon's circumscribed circle. Third argument, the length of the side. And the fourth argument, the color we want to draw for this regular hexagon. Before we look into this function, let's take a look at our main Pygame loop. This should be a while true loop, so this way we'll keep the window displaying. First, we update the frame rate, and again we have a small for loop inside this while loop to trap the user input, so that if the user closes the window, we can exit the program gracefully. After that small for loop, we update the display in Windows background with the background color. After that, we call this draw regular hexagon function. So this is the drawing surface, the first argument. The second is the coordinate. We pass the XY coordinate. The third one is the length of the regular hexagon. The fourth one, the color. We want to draw this regular hexagon in blue. Once we draw it, we update the display. All right, now let's look into this draw regular hexagon function. Line 40, we define a variable that is 6 degrees in radians. So this is a variable for the rotation angle in radians. Line 41, we use points list to collect the coordinates of this to be calculated 6 vertices. Like I said, the x prime, y prime coordinate system's origin coincides with the center of the circumscribed circle. The x offset, y offset should take the center point's coordinate, and the x offset, y offset is relative to the screen coordinate. And that is the coordinate we translate to for x prime and y prime. The next for loop, we compute the coordinate for these 6 vertices. And for each vertex, we know the rotation angle increment by 60 degrees. At line 46, it's the direct translation of the formula we described above. So the first element in this list calculates the x coordinate from x prime coordinate. So side length times cosine rotation plus this offset. This transforms the x prime coordinate to x coordinate. The next element transforms the y prime to y. And this makes a coordinate for P, and we add it to the points list. We do this for 6 vertices. After this, we use Pygame draw AA lines to connect all these points. Okay, run it. Now we see a regular hexagon with the center at about 100 and a y to 50. Now, if you want to change this position, you can simply change the coordinate, the center coordinate. How about 250, and we make this size bigger, the length of the side bigger. Stop this and then run it again. All right, now you see we have a bigger regular hexagon centered at 250 and 250. All right, we have come to this far. Let's move one step further. This formula, this transformation formula can be expressed using matrix. xy, this is a row column, equals this transformation matrix times this x prime, y prime 1. We introduced one more dimension here to make the matrix multiplication work. Now the transformation matrix is 1, 0, the offset x0, 0, minus 1 because we flipped the y direction, and this is y0, and this 0, 0, 1. So this transformation matrix times this x prime y prime vector will give you the coordinate in xy plane. Let's generalize this even further. Suppose I want to draw something in x prime y prime coordinate system where the x prime starts from x minimum to x maximum, the y prime starts from y minimum to y maximum, such that I don't have to be limited by the original, this blue coordinate system, where you can only draw a coordinate in the range of 0 to w for x and 0 to h for y. Now in this x prime, y prime coordinate system, the left up corner is really x minimum, y maximum. And the right bottom corner's coordinate is x maximum, y minimum. So in other words, the coordinate x minimum, y maximum shall be translated to 0, 0. And this x maximum, y minimum shall be transformed to w and h. By solving that, we get a transformation matrix. Let me just write down this transformation, 2D transformation matrix. So the matrix is x 0, tx, 0, xy, ty, 0, 0, 1. As x is the scaling factor of x transformation, x coordinate, and as y is the scaling factor of the y coordinate transformation. Tx, ty is the origin, translated origin, or the offset. In other words, the tx is here, ty is here. We have seen this before. Now the transformation is for any coordinate in terms of x prime, y prime. By applying the transformation matrix, we get the coordinate in terms of xy. Sx and Sy are the scaling factors for x and y axis, and tx and ty are the offsets for x and y coordinate. So with this transformation matrix, for any coordinate in terms of x prime, y prime, we can transform it to the coordinate xy in terms of xy. Because we know x minimum, y maximum, and x maximum, y minimum, we know these two coordinates in x prime, y prime are mapped to 0, 0 and wh respectively, so we can solve them to get this transform matrix. There's another transformation, that's the rotation. The rotation matrix is cosine theta minus sine theta, sine theta, cosine theta, and normalize it to 3 by 3 matrix. So this gives you the rotation matrix about the origin. In other words, if I have a coordinate in x prime, y prime, by applying the rotation, we can get another coordinate x prime, x1 prime, y1 prime in x prime, y prime coordinate. So this is rotation about origin. So with the rotation matrix and this translate and scale matrix, we can virtually do any graphics we want. Let's look at a Python example, see how we use this 2D transformation. This time we want to draw a sine wave or sine curve from minus 6 pi to positive 6 pi. Well, first let's run this program, see what we say. All right, so this is a sine curve from minus 6 pi to positive 6 pi. I don't have the grid line or the axis line drawn here, but you can count this is 1 period, 2, 3, and another 3 from 0 to the positive 6 pi. All right, let's close this and see how we did it in the program. As usual, we import packages and modules as needed. This time we import NumPy for matrix manipulation. Line 11, initialize Pygame. Line 14 and 15, define the size of the displaying window. And this time we have to make the width and height the same so that we don't distort the curve. Line 18, we pass the size to setMode function that returns this drawing surface. Line 21 sets the window's title. Same frame rate. The clock, again, the same color constants. We don't care about the draw regular hexagon anymore. Now this is the function, get translate and scale transform. This returns the translate and transform matrix we just described. The drawing surface, the x minimum, x maximum, y minimum, y maximum. These are the range of the x prime and y prime coordinate system where we can draw the curve. So inside it, so I have a description for you to understand how to get this transformation matrix. With this inputs x minimum, maximum, y minimum, y maximum, it's pretty easy to calculate the scaling factor and the offset. With that, we can have this matrix sx0, tx 0, sy, ty 0, 0, 1. This is the right transform matrix we need. Then we return this transformation matrix. For rotation, this is the angle in radians. This is the rotation matrix. The rotation is about the origin. So it's pretty straightforward. All right. Now this one is the transform function. Given a coordinate in x prime y prime system, we want to transform it to a coordinate relative to xy. We need to draw something in the end in the screen coordinate system. I commented the rotation so that we can test the translation and scale first. Okay, now this function get translate and scale transform we just described, but we pass the arguments. The x minimum is minus 6 pi. X maximum is 6 pi. And for the y is the same dimension, the same range. For drawing a curve, we need to make sure the x and y map in the same proportion. Otherwise, you would see a distorted curve when you do the rotation. All right, let's, this is the rotation matrix. So pi, this is a quarter of pi for 45 degrees. So this matrix will rotate the curve by 45 degrees about the origin. Now this is draw sine curve. We start from minus 6 pi and we stop at positive 6 pi. And we draw at a 0.2 radians increment. So we want to draw a point at every 0.2 radians. Okay. Now this is PT0 is our first point, x, and get the sine x, that's y. But we need to transform the point in terms of xy coordinate for drawing. The computer really takes the coordinate in the screen coordinate system. The transform coordinate function actually will return a list with the 3 elements in it. For a coordinate xy, we only need the first 2. So that's why we're slicing the first 2 elements out of the return vector. Now the while loop will compute the coordinate at every 0.2 radians increment. But for every coordinate, we have to transform the coordinate from x prime, y prime to xy. Again, because this returns a 3-element list, we need to slice the first 2 out of it. After we get the point, we can draw a line to connect these 2 points. After that, we assign point 1 to point 2. Basically, we move on to connect to the next point. Run it again. Now you see this sine curve. Okay, now let's enable this rotation. We want to rotate the sine curve by 45 degrees here. We need to apply the transform matrix after the rotation because the rotation would rotate the curve about the origin in x prime, y prime, and then we translate the rotated coordinate in x prime, y prime to xy. So this would rotate first by 45 degrees counterclockwise, and then we translate that into xy. Let's run it. Bingo! You see a rotated sine curve from minus 6 pi to positive 6 pi. Okay. If you're interested, you can experiment by rotating a different angle, and also you can change this scaling. You can change the range that would change the scaling factor. All right, that's enough for our discussion about 2D transformation. It is a little bit mathematics heavy, but it's very useful. By now, we have learned a lot of programming basics using Python. We learned Python types, variables, the operations of the types. We learned functions, control flows, modules, and we can do a lot of interesting things in the combination of them. Next, I'd like to introduce a concept called class. This concept is very common in modern programming languages such as C++, Java, C#, etc. Class is the foundation of doing object-oriented analysis and design, which is a very powerful and intuitive way of tackling a real-world problem, which requires software as a solution or part of a solution. A class is a template for user-defined type. Python has many built-in types, such as numerical types, strings, lists, and dictionaries. Using class, you can define whatever types you want. You can also think a class is a way of modeling a real-world concept, an entity or thing. For example, we can use class to capture the essential characteristics of a convenience store. The convenience store can later be used as a type in your Python program. In Python, we use keyword class to define the class. Here at line 8, we define a class called convenience store. There's a certain convention of naming the class name. For each word in the class name, the first letter should be uppercase. This is sometimes called camel naming convention. It is convention is not a hard Python requirement. Without that, the program would still run. However, by making the class name different from the variable name, it can stand out. For a convenience store, what could be the attributes? A convenience store could have a name, the name of the store, the address, the telephone number, and the manager of the store. And we initialize these attributes in a special method called constructor. The constructor starts with a double underscore, then init, followed by another double underscore. This method is invoked when an instance of this class is created. We'll talk about that shortly. But this method is no different than other methods or other ordinary methods, except the first argument by default refers to the class itself. It's called self in most of cases. The following arguments or just as other regular or other ordinary functions. You can have arbitrary number of arguments for your constructor. You can also have arguments that take on default values. Of course, a real convenience store would have much more attributes than just this 4. At line 12, I have a debug statement. So whenever this constructor is called, I print this line, convenience store ctor-store name. ctor is a short name used by a lot of programmers to refer the constructor. Now let's talk about what is an instance of the class. Like I mentioned before, a class is a definition of a real-world concept or entity. An instance is the realization of this concept. A class can have many instances of it. We have one definition of convenience store. We can use this convenience store as a template to create many convenience store instances. Okay, let's say, how do we do it? First, we want to create an instance and assign it to a store called store A. And you notice when we create the instance, we just call the class name as a function. However, we need to pass whatever the arguments required except the first one. The first one we don't need to pass, we cannot. So the argument we passed here, store A, will actually pass to the store name in this constructor. When we call this under line 19, this init will be invoked. That's why we call it constructor. We don't call init directly. We call the constructor by creating the instance using the class name as a function. And of course, we need to pass the necessary arguments. Run it. All right, now you say we created an instance of the store, and the store has a name called store A. Because I did not provide this value for these two arguments, so this address, telephone number, and manager does not have any value for store A. Like I said, you can create as many instances of convenience store as you want. And this time, let's do another store, and we call it store B. The name of it is store B. Again, we don't pass any argument for the self. The name is store B, and we specify the telephone number for store B. Run this. All right, now we created two instances of the convenience store with store B has a phone number 532 whatever. Most classes will have many operations other than just this constructor. For convenience store, we probably can have these functions. This is just for illustration purpose. Once we create the convenience store instance, we may want to update the store name, update the store address, update the telephone number of the store, update the manager of the store, and also we can have a override special function to print the store's information. Let's look at each of the methods one at a time. For this class method, the first argument, again, is the self that refers to the class itself. Update store name. Whenever you pass a store name here, it would replace whatever the store name it currently has. Why we do this? Well, one of the reasons is sometimes we need to provide certain validation for the input. So if the store name is not a good name or it's zero length, you don't want to update it, you probably can prompt the user to do something or log there's something wrong with this update. You don't want to mess up the current good information. And the same thing with other methods. For example, when we update the telephone, we can do a simple validation. The telephone number has to be in this format. First 3 digits for the area code, dash, and then followed by 7 digits phone number. Of course, this is just an example giving the reason why you want to have a method of updating your class attributes instead of updating that directly. We know here in this example, we can access the telephone number directly from the store B instance. But when we update it, we want to do it through a method. Production convenience store, you definitely would have more methods, more rigorous argument validation. The last method is called overriding method because the Python itself, for each Python object, it has this built-in print implementation. But for us, when we print the convenience store type, we want to return some basic information. For example, here I can return a self name, the convenience store's name and address. This provides a user more readable information. Okay, let's use some of the methods we just implemented. Still, we create a store A, but after the creation, we want to update the store A's telephone number. And then we want to update the store A's address. We want to print the store A's telephone number. And then for the 7, we want to print the store A. Well, this print will actually call this double underscore string underscore self. Like I said, this print would call this, which will give the user a more friendly information. Without implementing this, the print store A would invoke the default implementation of printing the type. The same way we create a store B, we print store B's telephone number, and then we print store B's information. Now to invoke a method, a class method, we should call it instance method. To call this class instance method, we do this. We call store A, which is the instance variable, dot, and the method. As other methods, we need to pass the necessary arguments. For updating telephone, all we need is to provide one argument, the number of the telephone number. Same to invoke the constructor, we don't provide this self argument. All right, let's run this. Okay, let's say the output one line at a time. So this is the print from the constructor. This is from this line. And next, we updated store A's telephone number. So store A telephone number is 001. And store A's address is this, correct? And then the store A at 10 Fushan Avenue, that's from this overriding function double underscore string double underscore. So after we updated this address, when we print store A, it printed user a more friendly information. For store B, the same thing. but we don't have the address for it. So you see the blank information for the address. Now you see store A has its own name and telephone number and address, and store B has its own different number and address, of course the name included. So instance store A and instance store B are different. Changing the value of one does not affect the other. These are two different instance variables, convenience store instance variables. Next, let's look at an example using class to represent a concept, RGB color. And we know RGB color has three components, red, green, blue, and the different combination of the three components produces another color. So in the constructor, here we provide three arguments, RGB. And notice inside this constructor, the attribute for red, green, blue have a leading double underscore. This will make these three attributes private. The private means these three attributes are not accessible directly from the instance of RGB color. We use this underscore, double underscore, to mimic the feature of other programming languages, other OO programming languages such as C++, Java, or C#. Now, why we do this? We do this is, one of the reasons is I want the RGB color immutable once it is created. I don't want the RGB instance changeable after it is created. However, you can access the red, green, blue component through the property, the read-only property. This is sometimes called getter. For accessing the red component, we define a property called red, and this is the Python special thing self. Really, when you call this red property, you don't need to pass the self argument. And it returns the internal private attribute. The same thing with the green and the blue attribute. The last method here, as we explained before, we override this underscore string underscore. This provides a user-friendly version of print of this object. Let's see, how do we create a RGB color instance? Color1 is the instance variable, and we call the class name as a function, but we need to pass the necessary arguments, red, green, and blue. And because this is the constructor required three arguments, we don't need to worry about the first one. We create that. Now we can access the red component this way, color1.red, almost like you invoke a method. But because it's a property as we defined, we don't need to pass any argument. And in fact, we cannot invoke as a typical function, meaning red with parentheses. Now we just call color1.red. This is accessed like a property. Now the print color1 will call this user-friendly print. Like I said, we cannot do this way, color1.double underscore red. Underscore red is not accessible. And also, we cannot change the component. We cannot change RGB component once the color1 is created. This effectively will make color1 immutable after the creation. Let's run it, see what happens. All right, we create color1, and this is a the print from line 26. Color 1 red component value is 0. And this one is from line 28. So when you print color 1, it prints the more user-friendly format of the information of this instance. By designing a class or class attributes as private, this is referred to as encapsulation, which means you access the information through the property or methods. And the property or methods can do certain operations or performing certain logics without you, the caller, needing to know the underlying details. Okay, I'd like now to talk about another feature of Python, a feature of class. This is called operator overloading. The operator overloading applies to a class. For RGB color class, we want to use the plus sign to add two RGB color instances. For example, here at line 37, we create color 2 RGB, okay? And color 3 equals to color 1 plus color 2. So this plus sign here is called is overloaded inside this RGB color class by this double underscore add double underscore. So what that means is when you have this implemented, underscore add underscore, when the class instance sees this plus sign, here it will invoke this method. When this is invoked, you can do whatever makes sense. In this case, we want to add the red component, add the green component, and then add the blue component. And we create a new RGB color instance and return it. Now here, let's go back to the constructor first, because when we add two color component, it may go out of range. So we use this minimum maximum to clip it in the valid range, which is from 0 to 255. All right, the first argument in this operator overloading called self. Self actually is the left-hand side of this operator. And the color 2 will be passed to this other argument. This is the way we can add two RGB color instances. So again, color 1 plus color 2, this plus operator will invoke this underscore add underscore method of the instance of the color 1. In fact, the color 1 is the self, and the right operand right to this plus sign, which is color 2, is passed to this other argument. Okay, this probably is a good time I'll show you how to use debugger in this PyCharm IDE. In the past 20 also lessons, I have never introduced you to use debugging feature, but since you have learned so many, I don't know if you have used that by yourself, but it is a good way to help you understand what's going on in a program. To run the debugger, you can run this from this icon. It's almost like a bug. Debug classes. Run it. Okay, now let's find what's the step into step into, step over, F8 is okay. Now F8, all right, the next line. So let's say, R other is 255, 255, So that's color 2. Say color 2 is 255, 255, Now in the debugger, when we are at here, other is from this watch window, you say other is 255, 255, Now the self, 0, 255, Self is color 1. Color 1 is 0, 255, This is what I told you. All right. One more step. One more step. One more step. Let's check the value. R is 255. R is this guy. And B is this guy is 0. Oh, wow. G is 510. So why G is 510? Oh, it's because 255 plus 255. Yeah, that is 510. Now, by our rule here, when we create this, we clip that inside the range of 0 to 255. We just need to make sure it's a valid value inside the RGB format. Okay. Then one more, color 3. Color 3. All right. That's it. So RGB, red 1 component, color 3, 255, 255, 255. Okay, this covers the very basics of class. I'd like to continue our discussion about classes and object-oriented programming. Virtually all OO languages support a feature called inheritance. We borrowed this terminology from biology. There are some resemblance. Through inheritance, the attributes and behavior of one class can be reused, extended, or modified by another class. For example, we have 2 classes. One class is called student. Another one is faculty. And these 2 classes are for modeling a school management system. And for student, we have an attribute called name. Well, the same thing for faculty. Of course, there could be many other attributes shared by student and faculty common to both of them. But let's keep it simple. Just as they have name attributes. And a student must have a grade in the range from 1 to 12. And a faculty works in only one department. Now, these are the attributes of these 2 classes. Now, notice we have the same attribute for each of the class. We can introduce another class called person. Student and faculty are person after all. And for the person class, we have a name attribute. By allowing student inherit from the person class, now we can remove the definition name in student and name in faculty. These 3 classes create a simple inheritance hierarchy. The person is called base class, and the student and the faculty called derived class. derived class. And sometimes the derived class are called subclass, and the base class is called superclass. So by using class inheritance, we eliminated the redundant definition of the shared attributes for both the student and the faculty class. And of course, suppose we have another class called staff of a school. The staff should also derive from a person, and the staff class would automatically have access to the attribute name without defining the name for itself. Therefore, the derived classes reuse the information in base class. And of course, in most languages, OO languages, they usually have a common base class called object. There's no exception in Python. We could have our person class derived from this object class. So a base class for some other derived classes could be a derived class of another base class. And there's no limitation of how deep this class hierarchy can be. Now, for the person, we might be interested in printing out the person info. So we could have implementation. Let me use this plus sign, meaning they are public attribute or methods. Public means the derived class can have direct access to them. So person info. And a student, if it's needed, can also have a person info function method. The same thing for faculty class. Now this way we have the derived class replaced the base class behavior or implementation of person info. We reuse the name in the base class, but for student and faculty, we override the base class person info function or behavior. Because for student, if we want to print out the person info, we not only need to print the name, we need to print the additional information for student, the grade. And the same thing for faculty, we want to print out the faculty's department. Now you say the base class has information or data common to the derived classes. The derived class has its additional, distinct information from the base class and from the peers. The base class can have an implementation which we call the default implementation. For example, print the person's info. The derived class can choose to override its base class default implementation. Let's look at another example. This is a portion of Python exception inheritance hierarchy. At the very top, we have this base exception. Of course, the base exception derives from the common class object. I just, omitted it here. And we have exception derived from base exception. Down in this inheritance hierarchy, we have an arithmetic error derives from exception. We have another two subclasses overflow error and zero division error, with each of them derives from arithmetic error. There are many other errors derived from this a common base class exception. Now for this class hierarchy, from top to down, the higher at the class inheritance hierarchy, the more abstract the class is. The lower a class is at the inheritance hierarchy, the more concrete the class is. Overflow error and zero division error are very specific errors, and arithmetic error is more concrete than this very general exception. We can use class inheritance to implement a design pattern called a state machine. For example, if I have a real-time strategy game, I have an army. The army has a base state called army state. There are several derived states for the army state. The army could be in attack mode, follow mode, patrol, or maybe other states. Now using this inheritance, each of the state could have its unique operation of processing the information in that state. And depending on the surrounding situation, the state can change from one to another, from attack to follow, or from follow to patrol, or if you have other states, they can change from one to the other. We are not going to the details how to implement a state machine. We just need to know inheritance is used for implementing the design pattern. And in fact, many other design patterns use inheritance. All right, enough theory. Let's see how we do inheritance in Python. Well, person is our base class. As any class, we should define a constructor. A constructor starts with this double underscore, init underscore. And for this person, we have the name. The name shall be common to all the derived classes. And also notice for the name, I have one leading underscore. By defining a name attribute like this, we make this attribute accessible by derived classes. And we know how to define property. For person, we can get a name, and we just return the name. Now, in the base class, we have a default implementation of printing out the person info. Because in person, all we have is a name, so we can print just the name. All right, this is our base class person. The next two classes, teacher and student, are concrete classes. They both derive from person. To derive a class from another, we do this class, the derived class name. In the parentheses, we put this base class name. This way is kind of a single inheritance. We are not doing multiple inheritance. By that I mean the teacher class inherits only one base class. In this case, the teacher inherits from person or derives from person, and so does a student. In teacher's class, it has its own constructor, and we need to pass the additional information for teacher, the primary department where the teacher works. Because the name is defined in the base class person, we need to call person's constructor, and pass the name to the teacher's base class person. This is the way Python calls the base class from a derived class. And notice for the primary department, I have this underscore, double underscore primary department. Like I said in the previous class, by having double underscore, we make this attribute private. Now this means this attribute is only visible to the class teacher. Next, department, we return this. This is a property, a getter. Now this method, person info, notice it's the same name as we defined in the base class. It prints the name from the base class because it's only one underscore, so we can use it in the derived class. We get the name from the base class, then we append the primary department, which is the additional information only in the derived class. This way, we override the base class default implementation of printing this person's information. Now for student class, almost the same. The constructor, it takes one additional argument that is applicable to student only, the current grade. In the constructor, we call the base constructor. In the student's constructor, we call student's base class constructor person to pass the name for it. And we assign the current grade to this private attribute. Now a property, a getter, to return the current grade for the student. The same as faculty, same as teacher. We have a person info which overrides the base class person's default implementation. Now to create the instance of teacher and a student is as usual, the usual way you create the class instance. You create the instance by calling the class parentheses with the necessary parameters or necessary arguments. For teacher, it accepts a name and primary department. These are required arguments to create a teacher instance. So teacher Andy, he works for mathematics department. And we can print, and we want to print the teacher's name and department. And these are accessed through the property. You can do teacher A dot underscore name or teacher A dot underscore or double underscore primary department. They are not visible to the instance of teacher. So you have to access them through the property. Now you notice the teacher A has this property department, but the name, teacher A.name, is really not inside teacher A's teacher's class. It comes from the base class. So you should understand this is a reuse. So teacher A.name gets the name from the teacher's base class, gets it from here. And the same thing for student. Student has this property grade. Student, yeah, here. Student has this property grade. You don't see the student's name property in its class. You don't see the name property in student class. But because student derives from person, and person has this name property, so you can just call student A.name to get the name from the student's base class. Let's run it. All right, you see Andy Mathematics, name Andy, for student, max 10, 10th grade. If you call student A.department, you would get an error because student A does not have a department A attribute or method. It does not have the attribute called department, and that is not available from the base class. The base class has attributes or behavior that common to the derived class. The department is not a common attribute. Now, what if I do this? I want to print the information for teacher A and student A. I can put these two objects in a list. Because they are all person, I can call person.personinfo. Let's see what happens. Run it. Okay, the first 4 lines are from this block. Now this is the print Andy Department Mathematics. That's the teacher and max grade 10. That's the print from this. So now you see when we call a person.personinfo, because each of the instances, teacher A, student A, has override the person info in base class, it knows what method to invoke. For a teacher's instance, it would invoke person info. Here, a teacher's implementation of person info. So you see the primary department, mathematics. And for a student, it invokes this person info. It would it prints the name plus the current grade. If you're interested, you can experiment with a class called faculty that derives from person without overriding the base class info. And then you can call person.info for that staff class instance. If the staff class does not have this override person info method, it would call the base method automatically. Okay, that's all for our discussion of classes. So far, what I have talked are just the very fundamentals of classes and a little bit object-oriented programming. Because this is primarily for high school students and college students who are not CS major or not engineering major. We just want you to have some exposure to the concepts of classes and object-oriented programming. You don't have to use classes or object-oriented programming techniques for a lot of work. I'd like to do a simple program that simulates a projectile motion. The motion about a ball tossed at a certain angle under the influence of gravity only. We know for constant acceleration motion, the velocity at time t equals to v0 plus at, where v0 is the initial velocity and a is the acceleration. For displacement at time t equals to v0t plus 1/2 at squared. And we also know a vector v has magnitude and direction. We can use 2D xy coordinate system to analyze a vector where the projection, the vector v's projection in x direction, vx is the vector's x component, and the projection in y direction is the vector's y component. Given the angle theta, Vx equals to V cosine theta, and Vy equals to V sine theta. We can use this to analyze a projectile motion, which can be analyzed in two directions, x and y, and the motion in each of these two directions is independent of each other. For projectile motion, the velocity in x direction is like this. Vx t plus delta t. The velocity in x direction at time t plus delta t equals to Vxt, the velocity at time t, plus Ax delta t, where Ax is the acceleration in x direction, in positive x-axis direction. And similarly, the y, the velocity's y component at time t plus delta t equals to Vy t plus Ay delta t, where Ay is the acceleration in y direction, and here Ay is minus g. G is the free fall acceleration due to gravity. We ignore the air resistance. We said the whole motion has only the downward acceleration, minus g. Ax here, in fact, is 0. This gives us the object's velocity at any time. Now, what about the displacement? We can apply the same analysis. The displacement in x direction at time t plus delta t equals position xt plus Vxt times delta t plus 1 over 2 Ax delta t squared. This is the displacement in x direction since time t. And we know Ax is 0. In the horizontal direction, the object experiences no acceleration, so it actually is a constant velocity motion in x direction. Now, what about in the y direction? Y displacement t delta t equals yt, the position at time t in y direction, plus Vy t delta t plus 1 over 2 Ay delta t squared. And Ay here is minus g. We use only positive g to denote this free fall acceleration, the magnitude of the acceleration. Because it's always downwards, we use minus g for Ay. And this is the displacement. This is the displacement in y direction since time t. So with these equations, and also given the initial velocity v0 and the launch angle theta, we should be able to calculate the motion, the projectile ball motion at any time. The launch angle theta is the angle between the initial velocities vector and the positive x-axis. We know the screen coordinate starts from the left top corner, and to make our simulation more intuitive, we want to translate the screen coordinate to a coordinate system we are accustomed to. We want to translate the origin to the left bottom corner. So we want to translate 0, 0 somewhere here. In fact, we leave a little bit distance for the origin. The origin will have 20 also pixels to the bottom and also 20 pixels bottom to the left edge. And the x direction in the system goes from left to right, no change. And the y direction moves upwards. So this is our coordinate system we'll be using to calculate the trajectory. This time we want to make our design more elaborate. We want to use different classes to represent the ball object, the 2D vector, the coordinates of the ball and the velocity, and also the transform. We could have put everything in one program, but by using classes to separate the objects into different modules and classes, we make the design more extendable, easier to maintain. Let's take a look at our simple vector 2D class. This class represents a vector with two components, x and y. We use this almost just like a pair or tuple with two elements in it. However, this class can be extended very easily to have other vector-related operations, such as calculating the magnitude of a vector. We can also do something like adding, subtracting vector by overloading operators. But here, we just need to know the xy components for the motion so that we can capture the coordinate and the velocity. This is good. This is sufficient for our purpose. The constructor only needs to know x and y. We make this xy components attributes private. You can only get the x or y through property. That's this part and this part. The method here, update, is useful. We want to change the vector in place. This is used when the projectile motion moves to the next location. So we want to update either the velocity or the coordinate of it. And this override method is for debugging purpose. You can print user-friendly information for debugging. This is good for our vector 2D. We have another class called affine transform. This class captures the transformation from one coordinate system to another. We have used this in previous program where we just define the transformation in a function, and we use that function directly in the main program. But this time, we want to encapsulate the transformation in a class. We do that in the class constructor. We pass the x minimum, y minimum, x minimum, x maximum, y minimum, y maximum. This is the coordinate. This is our desired coordinate system's x and y axis range. We want to map this onto the drawing surface, which is the screen coordinate system. Okay, the usual transformation, we have seen this before, Sx, Sy are the scale factor for x-axis and y-axis. And Tx, Ty are the offsets for the x-axis and y-axis. We use NumPy to create this translate and scale matrix. Once we create that, we store it. So in other words, when this affine transform object is created, the transformation matrix is known. We don't change it afterwards. Now, there's another method called transform coord. we have used this in the main program in the previous class, but here we make it a class method. So the input is coordinate xy. Of course, we use vector 2D type. This is argument annotation. Just to make this more easy to understand, this argument is type of vector 2D. So it has the x component, y component. We just saw in the vector 2D implementation, you have x and y properties. So you can get that. We make it 3-dimension vector. Now we just call the transform. We get the transformed coordinate. We return it as a vector 2D object. And this returned value shall be the screen coordinate. Okay, let's go to our ball class. Class ball represents the ball being tossed at a certain angle. And we want to use this class to capture the projectile motion. In the constructor, what we are interested to know for the ball, the radius of it, the color, the coordinate, initial velocity, acceleration. We also want to pass the transformation to the ball object so that we can draw the ball within the ball object itself. When the ball is instantiated, when a ball object is instantiated, again, it knows its radius, the color, the current coordinate. We want to pass the initial coordinate to it at the time when we create the ball. The same thing with the current velocity. We pass the initial velocity to it, and also the acceleration. And this same time is important. Time returns the seconds since epoch. It's a floating number. So when the ball is created, we record the time is created. We record the time. The trajectory is an array to store the trajectory of the motion. At each calculation, we will add the newly calculated coordinate to it for us to draw the trajectory. The last one is the transform. Okay, a property to return the current coordinate, nothing special. Now the update method. The update method is the place where we implement the physics. Okay, you see this calculation is very similar, almost just a direct translation of what we have discussed at the beginning of the class. Same time. Well, this is the time when we call the ball object to update its motion. Every time you call it, we use time.time to get the seconds since the elapsed since epoch. It will always be a greater value than the last time we called it. So same time minus this self._same time gives us the duration or the delta t, which is the elapsed time since last update. So this is how we calculate the delta t. Once we have that, we know the current coordinate, the current velocity, so we can calculate the current coordinate in x direction. And it is this translation from the formula at the beginning of the class. So this is x position plus x displacement since time t. Okay, and this is the same thing for the y coordinate. Okay, you have the last coordinates position in y and plus this y displacement. And of course, the acceleration in x shall be 0. And the acceleration in y should be minus g. And in our calculation, we make it general. Just you can do a simulation with the acceleration in x not 0. After calculated x coordinate and y coordinate, we update the ball's current coordinate. All right, next, we need to transform the coordinate. Remember, the coordinate is calculated in our desired system. However, we want to transform them back to the screen coordinates for displaying. Okay, so self-transform, transform coord. We get this screen coordinates, and we add it to our trajectory. After we updated the coordinates, we can update this velocity. Well, this is still the translation of the physics. This is the velocity at x direction. This is the velocity in x direction, and plus ax delta t. Well, not much to explain. It's just physics. After that, we update the current velocity. At last, we want to update the time we calculated this motion so that when the next call comes in, you will have another delta t. All right, that's the update method. Similarly, we have an override method, double_string, to return the ball's motion information, current coordinate and the current velocity. This is for debugging purpose. The last method, draw. Like I said, we encapsulated the drawing method within the ball class. That's why we need to pass the drawing surface to this class. The drawing surface is the object returned from Pygame. Well, here, line 51, we want to check whether we have any points in the trajectory array. If we have more than one, we can draw the trajectory using anti-alias lines. Okay. All right. After that, we want to transform the ball's current coordinate into screen coordinate. And then we use this anti-alias version to draw the circle and fill it. We draw it at the screen coordinate xy. This is the center of the ball. Using the radius and the color, we know when the ball is created. All right, let's go to our main program, project_how.py. Well, because we have defined this different things in different classes and different files, so we want to import all of them for the main program to consume. We import some system built-in modules, system, math, import Pygame, and this is our own modules. We import color constants, we import this affine transform, we import ball, we import vector 2D. We import everything from those modules. Initialize Pygame, we define the size of the drawing surface. Okay. Then we create the screen. Here we set the caption of the window, background color, and clock, frame rate. This is all usual. And here the frame rate, we want to use a higher frame rate so that we can make the drawing faster and make this smoother. Okay, now this line 26, it creates the affine transform. This first argument, that's the drawing surface. The next 4 arguments is the desired coordinate system we want. Like I said, we translate the origin to a point that has 20 pixels to the left edge and also 20 pixels to the bottom edge. However, we keep the total distance the same, the total width the same as the screen width, and total height the same as the screen height, so that the scale factor actually is 1 for x, for y is -1. So we don't really distort the display. The scale factors are 1. Let's use 15 for the ball radius. Initial velocity is magnitude 80 pixels per second. Now, the reason we use pixels is for the simulation. Okay, it doesn't matter you use other units, but the pixels is much more straightforward. And the acceleration is vector. Ax is 0. The acceleration in x direction is 0. And in y direction is free fall acceleration. It's -10. Well, just let's use 10. Of course, you can also use 9.8. It doesn't really matter. All right. Okay, next few blocks, we create 3 ball objects. The first one, we create a ball thrown at an angle of 45 degrees. The second ball thrown at a degree of 70 degrees. And the third ball thrown at 30 degrees. And they are all of the same radius and start at the same location, same coordinate. Of course, each of them has different color. The difference for these 3 balls, B1, B2, B3, is just the launch angle. So this is very interesting because from high school we learned for projectile, a ball being thrown at a certain angle, 45 degrees will throw the ball to the furthest distance. We just want to say if that is true. Of course, it is true. This is simulation. Okay, we created 3 ball objects. Let's see. Okay, next is our simulation loop, the main Pygame loop. Nothing unusual, the frame rate, and this event loop. We want to trap the user input. If the user clicked the close button, we want to exit the program gracefully. We set the background color. Now here from line 55 to 57, we draw the horizontal x-axis line. Still, we need to transform the coordinates into the screen coordinate. So we want to draw from 0, 0 to screen width -50, and also y0, that's a horizontal line. You know, the y coordinates are the same, but the x is different. Okay, so this gives us the horizontal line. Next, okay, we draw a small rectangle for the launch pad. Okay, we still need to translate. We want to draw it at 0 and ball radius. So this is the rectangle's left top coordinate, left top corner's coordinate, but we need to translate that into the screen coordinate. Then we draw it. Line 63, we get the time, the current time. So for each loop, for each execution, we set the frame rate to 60, and hopefully we will run this loop 6 times per second. Okay, so this is the time when we want to update the ball's coordinate. We want to update the ball's motion. Because we have 3 balls, we want to update for each of them. We loop through the balls collection, 3 of them. We update with the current time. If you go back to ball, you will see this update is just that physics calculates the current, coordinates, and velocity at time current t. We only update that when the ball is still up in the air. It's not touched down yet. Okay, after that, we draw the screen. Of course, regardless where the ball is, we always want to draw the ball onto the surface. This gives us the ball still being displayed at the end of the simulation when the ball hit the ground. Okay, the last line is just flip the drawing buffer. Okay. All right, let's run this program. Okay, just watch. 3 balls launched from different angles. The green one was launched at an angle of 45 degrees. The blue one was at 70 degrees. Well, it hit the ground the last. And also it hit the shortest distance. Okay, that's the end of the simulation. You can run this many times. I enjoyed it very much, and I hope you too.